Good morning, everybody.
Good morning.
Please, Professor Joseph, your mic is not working.
Can you hear me?
Yes.
Okay.
Okay, just for Professor Joseph, they have problem in his mic. It's not working.
Are you talking to me?
Yes, no, to Professor Joseph. In the list,
okay, Joseph. Yeah.
Panelist, the mic is not working. I don't know if he has or not. Professor Joseph.
I am here. I'm ready.
Yes. Okay. We start the webinar now.
Hello, Professor Zaz. Do you hear me?
It's
Christian Nikita. Do you hear me?
Nikita. Yes.
Yes. Okay. Thank you.
Welcome.
Nikita.
Just to verify with Professor Shakib Alawi, the same. Yes, the mic is working. We're waiting for Professor Rashid. Rashid Uschiri. Yes, he's there. Professor Rashid, are ready? Please switch on your mic and your cam.
Activate. It's okay now?
Okay. Little bit okay, it's good.
Good morning.
Good morning.
Good morning.
Okay. We will start the conference to now is still hold. We will start the conference to allow participants to access. Okay.
Oui.
Professor Rashid Bashiri, you are ready?
Are you talking to me?
To Rashid Bashiri.
Yeah,
Are you ready?
yeah. We'll
Okay.
begin
Okay.
in 2 minutes.
Excuse me. Good morning, everybody.
Hello.
Today is the 4th day of IRSEC. We'll begin this morning with the special session entitled Wind Energy, Electric Production and Grid Integration that will be shared by Professor Rashid Bashiri from High School of Technology, Fez, Morocco. Thank you very much, Professor. The floor is yours.
Yeah, thank you. It's a pleasure for me. Our session will begin now with an interesting keynote conference by Dr. Ahmed Zahidi. Dr. Ahmed Zahidi is an associate professor with the James Cook University, Queensland, Australia. He has over 30 years experience in teaching renewable energy and power engineering at different levels in this university and other universities in Japan and Europe. Dr. Ahmed Zahidi has published more than 200 papers, including 4 books, and has trained 21 PhD candidates. He has also completed 15 industry-funded projects. Dr. Ahmed Zaidi will begin with a conference entitled Wind Farm Factors to be Considered for a Successful Project. It's for you, Dr. Ahmed Zahidi. You are welcome.
Okay. Thank you very much, Professor Bashiri, for a nice introduction. And thank you for inviting me to share with you some of my experience with wind energy and wind energy design or wind farm optimization and wind turbine operation. And I would like to share my experience in 20 minutes with you, and I hope that you find it useful. Let me share my screen with you. This will stop. Can you please allow me to share my screen?
Yeah.
Okay. So, can you see my screen, please?
Yes, we can.
We can see.
Okay, very good.
Switch
very good.
full screen.
So I can actually start talking, and I would like to talk about a little bit about wind farm and how to make it actually wind farm a successful project.
Excuse me, switch to full screen.
I have already shared the screen.
Full screen. Switch to full screen.
Full screen, like this.
Control L. لا أدري خدام PDF.
Is it now full screen?
Control plus M. Control plus M. Control plus L. L. Control plus L.
Control plus L. Yeah. Is that okay
Yes.
now?
Yes.
Okay, sorry for that. Look, wind power is now very popular and very important. And some people believe that this wind energy or using wind energy for electricity generation is now a success story. And this is actually, there are many evidences from international organization report saying that the installed capacity or the use of sort of wind energy has increased very rapidly, has grown actually very rapidly, you know, but from, say, for example, from 6 gigawatt in 1996 to 650 gigawatt in 2019. And this has been actually shown by the organization of Global Wind Energy Council, that shows that how a fast growing technology for electricity generation has been this wind power. And there are actually some countries that are more active than the others. And for example, China is very active. In the past few years, Germany and the United States, they were two countries on the top of the list of using power, but now China is on the top of the list, and they have actually installed a lot of new wind farms. And I have to mention here, there is you know, I think that China has gone very fast. The reason for that is I have I have read some report from international organization that some of the wind farm, some of the project, they are not operational because they have been very fast in construction, but they have been not actually fast enough to upgrade the electricity network to be able to absorb electricity from wind power. That is just a comment I have heard from one of the international organizations, but I'm sure probably they will fix this issue. And these are actually the top countries that they are very active in using wind energy. And it's a very, when we look at the price, when comparing the electricity price from wind power compared with the other actually technology, is really cheap. Is really provided that the location site is carefully selected, and also there are a huge number of wind turbines available by different manufacturers, but it is important actually to find the most appropriate wind turbine for a selected site. And I want actually to draw your attention to this, and that choosing actually carefully the site and also suitable wind turbine is very important. And as an example, only 1% increase in wind speed expected 3% increase in energy generation, and also 1% increase in diameter or size of wind turbine will increase 2% energy production from wind farm or wind turbine. You can actually see how this actually important factor in choosing that. And math actually tell us that the power that the power in the wind is related to a couple of factors that I want actually to draw your attention to two of them, which are very important. One of them, speed of wind, and which is actually the power is proportional to Q factor of to power 3 of the wind speed, and also the area swept by wind turbine blades. That's actually, we will see very important. As an example, I want actually to show you this map of Australia just as an example, which actually shows which location, which part of country, and actually it's valid for any country, which part of country is more suitable for using for constructing, building wind farm. And as you can see here, that that the dark blue is, it says the average annual average wind speed is about 10 or more than 10 meters per second, which is extremely good. And according to this equation, as you can see, if one wind turbine is installed a location with the, say, for example, 4 meters per second, and same wind turbine is actually installed where the wind speed is 8 meters per second, just twice, the amount of power will be increased by factor 8 because of this wind speed to power 3. And no surprise that, so again, example, Australia, why so all wind farms Australia are actually constructed near the location where the highest wind energy resources are available. It's just because to maximize the power, to increase the capacity factor of the wind turbine, and also make this electricity cheaper. And the other factor is the size, because again, the power in the wind is proportional to area which is pi r squared. That is why the wind turbine manufacturers they are making bigger and bigger and bigger, because they want to increase the area to maximize the power. And as I mentioned before, a huge number of wind turbines are available worldwide. You know, there are actually more than 40 large wind turbine manufacturers in Europe, in China, in USA, in US, in India, in Germany, everywhere. You know, there are actually more than 15 countries worldwide are very active in making wind turbines. But for someone who wants actually to invest in wind energy, wind farm, they want to know which one is suitable. You know, so many options, so many, wind turbine available, but which one is good? And so I want actually to share with you some of the factors that important for wind farm developer or investor or anyone who is interested in that, is important in choosing the making a wind farm project successful. One of the weakness of wind power is its efficiency. It's very relatively low efficiency. Is it minimum is 24? Anything below that, forget it. You know, if wind farm is working as a efficiency under 20, it's the wrong place, wrong wind turbine. And the maximum theoretically is 50, but unfortunately is not reachable. And why is not reachable? Why efficiency is very clear? Because wind and air or wind is moving towards wind turbine, has a certain amount of the kinetic energy, and this kinetic energy is just because of the wind speed. And when air or wind is moving away from wind turbine, it still has some kinetic energy. So this is wind turbine is not able to minimize the amount of energy that wind has when it is leaving wind turbine. So this is impossible for wind turbine to stop the wind after actually giving, or after wind turbine has recovered or captured the energy. So this is one of the reasons that efficiency is very low, and the maximum theoretical efficiency is 60% for this reason. So this is actually depends on the ratio of wind speed of wind leaving moving away from wind turbine divided by speed of wind moving toward the wind turbine. So efficiency is, so these are actually the reason that the wind farm is considered as a low efficiency technology for electricity generation. But it has actually many other advantages that makes it popular, make it so popular and so economical to use it. And obviously, the new technology conversion of, another reason for low efficiency is because conversion of energy from wind energy into electricity, there are more than one steps. One step is conversion of energy, wind energy into mechanical power, and the second one is mechanical power into electrical power. But the second step is very efficient. These days, manufacturer of generator, they make very good, very high efficient generators to convert mechanical power into electric. And the other problem is the wind is not actually constant. The wind speed is not constant. This is what power companies hate to see that, because they don't like this one. But technology, this is actually not focus of my talk, but the technology is available to improve this weakness of wind power. Now, as an engineering point of view, now we would like to do the performance prediction, site selection, wind turbine selection. We'll have to do some engineering job. But what you can actually see in this figure, these blue bars, they are actually measured. It's like you can assume that this number of hours in one location in 1 year has been measured, that the wind speed has been 0 or 1 or 2. You can say in a city like Melbourne, in 1 year, the wind speed is measured from 0 to 25, and anything above 25 is not actually relevant, and no one is interested in that, because it's the speed of, it's about 90 kilometers per hour, which is very outside the interest of the manufacturer. So this actually blue bar, they show the number of hours that in one location that the wind speed has been, for example, at 5, 6, 7, 8 meters. And it is very close to something that this Swedish mathematician has actually said that offered or invented this equation, which has proportional, or is depends on many factors. But we are not interested from the wind power analysis. We are not interested in those factors. We try to find what is this most suitable one to this. And look at this equation, and because of the factor here, this factor make different shape, different curve, and so on. As you can see, this actually for C equal to 8, but the reason I have chosen C equal to 8, because C equal to 8 is very close to realistic wind average, annual average wind speed of 7.1 meter per second annual average. So you can actually see with the shape will be different, but we are not interested in we are interested for our analysis the one which is very close to experimental one, which is actually this one. And as you can see, we can use this Swedish invention using this equation and make it. I don't need to explain how to get this one. But as you can see, this is the probability of wind speed depend on annual average of wind speed, any location. In Morocco, in Australia, in Europe, and you can actually guess or estimate the probability of any wind speed from 0 to 25. And as I said, the probability of very high wind speed is out of interest. And so depend on location. For example, I know that Morocco is not a windy country. Some places they have very low wind speed, say 5 or a little bit more than 5 meters per second as annual average. This would be the probability. And when we move to a windier area, that wind speed is 7 or 9, or like in south of Australia, which is more than 9 meters per second. So the shape will be different, and the probability will be different. And then the probability multiplied by number of hours in 1 year, which is 8,706, gives you the number of hours in 1 year of any wind speed. This is very important for us as a renewable energy engineer to do the analysis, to find what is the actual power from the wind turbine, and trying to play with the factor to maximize. One of the factors, one of the important things that is important from the researcher point of view, important from the investor point of view, or wind farm developer point of view, is capacity factor. Capacity factor is ratio of the ratio of the actual energy generated in 1 year by wind turbine or by wind farm divided by rated power. And I'll tell you something. This is the very confusing is wind power or the size of wind turbine. It's very confusing. When wind turbine says 2 megawatts or wind turbine says the manufacturer says 1 megawatt, it doesn't mean that 2 megawatts wind turbine can generate more power than 1 megawatt wind turbine. So this is a little bit confusing, but we can actually try to find the best one, the best wind turbine for the best location. When you look at the wind specification of any wind turbine manufacturer or wind turbine model, they give you this curve. It doesn't matter if you visit the Vestas, Danish wind turbine manufacturer, or Chinese one, they say talk about this curve. They say actually not interested in very low wind speed because wind speed is very low, and usually wind turbine doesn't operate because the cost of maintenance is more than energy that the wind turbine can produce. And there is another zone that wind speed is above 25 meters per second, that none of the wind turbine that I have actually checked can work above that because it's very dangerous when damaging. So there will be one flat area and one area, curvish area, which is proportional to the wind speed of the to the power of 3 of wind speed. So in order to find the good or the reasonable or predict the reasonable capacity factor of wind turbine, we have to consider some of this. This actually figure here shows you that, as I mentioned before, when we look at the specification of wind turbine, when it says 2 megawatts, 5 megawatts, or 3 megawatts, but the manufacturer, they say rated wind speed as well. It means when manufacturer says 2 megawatt, it means at rated wind speed of 14 meters per second, it means if wind speed is 14 meters per second, the wind turbine can generate is nominated or rated power. So now you can actually see that wind turbines how the energy produced by wind turbine depends on its rated wind speed. So this is actually example of, I don't want to mention the manufacturer, but is one of the manufacturer, European manufacturer, making 2.5 megawatts for the average of wind speed of 8 meters per second. As you can actually see, the capacity factor is going down as the rated wind speed is increasing. And this one shows the similar thing in terms of cost. You know, as you can actually, you know, again, I have actually compared 4 different wind turbines of different size for a certain location with the 6 meters per second of annual average wind speed. As you can see, the wind turbine which has a smaller wind power or a smaller rated power can generate as much as power that much bigger wind turbine can produce. For example, the one on the right hand side, the rated power is 2.7 megawatts, and the one on the left hand side is just 1.5 megawatts. And you can see that the smaller one can generate as much as power in 1 year as the larger wind turbine can produce. And also the installation and the cost does dollar per kilowatt hours or cents per kilowatt hour I have written here, and I don't want to confuse you. This is just installation. And you know, wind turbine, when we want actually to do the cost analysis, life cycle cost analysis, and so on, we have to consider many different costs. But the many different costs depends on many factors. You know, how close is wind farm to the electricity network, how you know, easy is to connect it, and how easy is the installation of that, or how much is the operation cost, maintenance cost. There are many costs that we as engineers need to consider when we want to do the cost analysis. But this is just the cost of product installation. It's just good, not the other cost. And as you can actually see, for this performance of the generation or the cost of wind turbine, when same wind turbine have been actually installed where the location has 7 meters per second, and also continue doing for 8. And as you can see, the generation, you know, and as you can actually see in here, this actually 1.5 megawatts wind turbine was very suitable for low wind speed, but now is not suitable for higher wind speed. Yeah, so it can generate less power. So you know, there must be actually in terms of the choosing wind turbine for a wind farm, for a location, we have to consider. As you can see, this one was good. 1.5 megawatt wind turbine was very good for a low wind speed, but not as good as it was before. And what I want to show you one more example for the different average wind speed. Yeah, it's a one single wind turbine of 1.5 megawatt. That's if it is I was showing you before. And this 1.5 megawatt has a rated wind speed of 12. It means when a wind speed is 12 meters per second, this wind turbine can generate 1.5 megawatts of power. And as you can see, as the annual wind speed is increasing, the generation or the capacity factor is increasing, and the cost is going down. This is the ideal for wind farm developer, wind farm investor, that to try to find the suitable size, location, and appropriate the suitable wind turbine. One more example, as the last example I want actually to show you, is another wind turbine with 2.5 megawatts, and assume that this is installed where a place, a site that has a 8 meters per second is annual average of wind speed, and rated wind speed is between 10 and 15. I want to show you that how important is, you know, to look at the rated wind speed of wind turbine. I'll give you I show you with this example. You know, this is actually what I have produced by using a MATLAB program. And what the one in green, it shows actually the when wind speed is 8 meters per second for our location, can be anywhere. This would be the number of hours per year of that particular location that the wind speed was 1, 2, 4, 3, 4 until 25. Yeah, and the one on the right hand side and blue color one is actually what is known as power curve. And this is what actually manufacturers they give us. And for example, this is manufacturers of this 2.5 megawatts wind turbine said rated wind speed is 15. Now, and this red color one, this shows annual energy production. And I have on table below, I have written the numerical value of that. And interesting is the last one, this curve, the curve number or the figure number 4. The red color is the probability. Yeah, probability from 0 to 0.12. If you multiply this probability by number of hours in 1 year, you will get the green color curve. Yeah, but that's the only difference. And the blue one is the power curve that is actually given by manufacturer. Now, I have actually in order to show you the important effect of the rated wind speed, I have done I have performed this calculation for 4-5 different rated wind speed, and I want you to show to look at this corner of the curve, blue curve, and the top of this red curve here. Yeah, as I decrease the rated wind speed, they become closer. Yeah, they become closer, and this green color becomes bigger. It means more power is generated, and it's a little bit further, and making a smaller rated wind speed. The gap becomes smaller, and the energy produced or generated is become bigger. And this is actually for something about 13 meters per second. If I decrease it to 12, it's become even, the gap becomes closer and energy becomes bigger. And as a result, the capacity factor or the performance of the wind turbine becomes better and better. And you can actually see for the 11 or 10 the gap is very small. And so the energy is at the highest. So the lesson we can actually get from this is, when we look at the wind turbine, specification of wind turbine and the location, you know, the red one is to represent the location. The blue color curve represents the wind turbine performance. The closer they are, these 2 points, the pitch point, they actually perform better. And as a final slide, I have done similar calculation and analysis for one of the places in Morocco. And I don't know if I'm not sure if I am pronouncing properly. Is Al-Soira, something like this. That actually is according to the investigation or research I did, this location is a good location in Morocco for using wind energy, and is about 7.5 annual average, something about 7.5 meters per second. And so if that particular wind turbine of 2.5 megawatts is selected for this site, Now, the best actually would be the rated wind speed that would be smallest, which is a 10, which gives actually the highest energy production per year and the highest capacity. As we the wind turbine with the bigger or larger rated wind speed is chosen, the amount of energy produced per year, annual energy becomes smaller. As a result, the capacity factor becomes smaller, and cost will be small. Cost will be bigger. So it just, again, I mentioned this is just installation cost. And this is for the same place, same similar wind turbine for different rated wind speed. As you can see, the wind rated wind speed is increasing, the capacity factor is decreasing, and the price is going up. Yeah, and this one is, again, capacity factor is decreasing and the price is going up. This is just one I wanted actually to conclude with this example from Morocco, and I hope that I was able to offer something useful for you. I'm happy to answer any question if there is any.
Thank you, Professor Ahmed Zahidi. Your conference was very interesting. I want to thank panelists, which are my colleague Christian Nikita from France. Hi, Christian. And
hello.
yeah.
Hello.
Hello. And Professor Shakib Alawi.
Hello.
From Ahmed University. And Dr. Youssef Errami from Faculty of Science, El Jadida, Morocco. Professor Youssef Errami, you are there? We will begin by some question from persons who are in the who are in the conferences, like Mr. Subhasi Makriji. He asks how ambient temperature impacts on the wind farm performance. Is there an important factor, temperature?
Yes, this is actually a very good question because according to the physics behind that, the pressure is proportional to temperature. And then so when in a hot area, warm area is wind speed is relatively low compared with colder area. The best example is Australia. North of Australia is warm, South Australia is relatively cold, and most of the wind farms are located south because the temperature is lower, pressure is higher, and if you look at the equation I was showing you, the power is proportional to density of air. When temperature is lower, air is denser, and more it produces, rho is bigger and produces more power.
Yeah, thank you for this answer. And he answered too, what is the playback ROI considering both CapEx and OpEx?
This is actually, I cannot actually say any figure number for that because it depends on many factors. But I cannot give any number on this. I haven't done any research or investigation on that because it's very complicated and it depends on location, depends on manufacturer, depends on type of wind turbine and so on.
Yeah, our follower from Algeria is Ahmed, and his question is about stall speed, how to predict it. Yeah.
There are, there are two ways to predict. There are actually many software programs these days available. They can predict for example, tomorrow's wind or direction of wind or wind speed. There are actually, this is something is now is known to industry, that how to predict the wind speed in next 24 hours. And this is actually what for the power company is important, especially when when it comes to a spot price and or the generators of any type on a technology, they have to offer in their price in 24 hours before in advance. So there are many software programs that can actually predict the wind speed or future wind speed, or at least in 24 hours in advance, by using the historical data and also the annual average wind speed.
But I think errors on forecasting must affect the cost of kilowatt hour.
Again, it actually depends on many factors, but for the examples we are doing for our research or for our at university, we are doing that, the price is under 10 cents per kilowatt hours. Australian cents per kilowatt, including considering installation cost, and installation cost is going down, and also considering the other factors, how close the wind farm is to the electricity network, because transmission line, cost of transmission line is very relatively high, and when wind farm is located in a good area with high wind resources, but is far away from electricity network, the cost of transmission line will be very expensive. So, and also there are some, unlike solar energy, solar farm, wind farm, they need some maintenance costs, operation costs and maintenance costs. For those, actually, if we consider all these costs, calculating the life cycle cost, and in the average of the cost will be about 10 to 12, 15 Australian dollars per 12 Australian cents per kilowatt hours.
Thank you for the answer. For a given wind turbine, is it an optimal rotational speed? Optimal in the sense of power projection?
Sure.
Yeah.
Yes. Can you repeat your question again?
For a given wind turbine, with his dimension and his power rated, is it an optimal rotational speed where it produces a maximum?
Obviously, the maximum power is, the flat zone of power curve. When anything between rated power, when rated wind speed to 25 meters per second. This is actually generate the maximum, the maximum power. This is a flat region of power curve, but never happen. It very rare happens that the wind speed is in flat region, But interesting is that wind turbine these days, the technology, the advancement of technology is so, the electricity generated by wind turbine is in AC form. But because the machine used to generate electricity is induction machine, induction generator, and induction generator doesn't have a synchronous frequency, and it's not suitable for the grid. So there are so many technologies these days, a power electronic technology, that make it actually, no matter how the speed of wind turbine is, what is the speed? Is it 3, 4, 5 meters per second or 20 meters per second? The output power connected, the power connected to grid has a fix of frequency of 50 hertz. Make it suitable, otherwise will be rejected by the power network.
Thank you. I will take the last question from followers.
Professor Bashiri.
Before we move to panelists to add their remarks or their questions, the last question for followers is from Mr. Mohammed Illouh about the technology trend, synchronous generators versus asynchronous generators, which is more efficient for large powers?
When you talk about technology, you know, there are many different technology available. And Danish model was the relative oldest one. But now the very modern and up-to-date technology are available, which is a doubly fed induction generator. This is actually work perfect at any window speed and generate power, AC power at constant frequency. And because of the power electronic devices and because of the advancement in the power electronic, they can actually make generate power at a constant rate and the constant frequency connected to grid to make the grid owners happy.
Thank you. Now we will move to panelists. They can add informations or other question. Perhaps I will begin by Professor Nikita Christian.
Do you hear me?
Yeah.
Yes. Thank you, Professor Zaidi, for your very interesting presentation. So there are a lot of things about the criteria for the performance power of wind turbine. So some little remarks about two things. In order to obtain maximum power, because there are one question about it, we must have, in order to control this maximum power, we must have what we call the characteristic power in versus rotation speed of the shaft. The problem is that these characteristics, this notion are difficult to obtain from manufacturers because there are a lot of things about the secret of fabrication of the blade. So if you have, for example, this familiar characteristic power function of rotation speed, we can have easily we can have the maximum, the optimal speed that you must improve with your control speed. It is possible to obtain that I respond with to this question. So in this case, the main characteristic of power production, generated power as function of wind velocity. So we can run, we can have points, optimal points in zone 2. In zone 2 where we can develop the power with what we call MPPT, maximum power tracking. In the case we have what we call also the variable speed strategies. But in this case, I think we must have what we call pitch control of the wind turbine. So many of the manufacturers with this mechanical regulation within correlation associated to what Professor Zahedi says with the control of electrical generator to obtain finally what we can say theoretical maximum power in the shaft of on the shaft of the wind turbine. So one of criteria of a good performance of a wind farm will be also the choice about this mechanical regulation and electrical regulation or electrical control. And in this case, we must choose what strategy fixed speed on the shaft or variable speed on the shaft. So we can obtain more energy, evidently, with the second strategy, but what the Professor Zahedi highlight previously, the choice of the site is very, very important because it is possible to obtain this optimization with variable speed if in fine previously the site was well chosen. Thank you.
Yes, your remarks were very interesting. I think we will perhaps hear from Alawi
Yes.
Shakib, and we will
Yes.
come back to Zahidi for a final conclusion.
Thank you. Can you hear me?
Yeah.
Yes.
Yes. Well, thank you very much. I would like to thank Professor Zahedi for his very interesting presentation. Although I have a little question remark. Now, we know that for horizontal axis wind turbine, the theoretical limit was established by Bed's limit, which is the 59%. I guess it is like some 16/27 or something. And this is a very theoretical value that was established using a simple math. And well, it's established its theoretical limit. However, well, I'm interested to see the real limit on the field, because this limit was established on a smooth running air in some kind of wind tunnel where everything is controlled. But better yet, I'm more interested in the vertical axis wind turbines and their limit, because we know that if we compare 1-to-1, we know that the horizontal axis is much better than the vertical axis. However, if we look at a wind farm, now when we establish a wind farm with horizontal axis wind turbines, we have to take into account the turbulence, which makes higher distances between the turbines increasing, because and we see after at the end of the day that's only the front of the wind farm, from where the wind blows. Those turbines are the ones who get the most of the wind, and after that the wind gets turbulent, and then the following subsequent wind turbines get much less flow of laminar airflow that they want. However, we think that the vertical wind turbine, how they respond better to turbulence because of their shape, because of their axis of rotation. That's why we think that on a wind farm scale, there may be some potential to have a good result installing vault. Maybe because I saw some companies in the US starting to mix the two, because you have a wind flow with tall structures. They make rotate the wind turbine, and then they create some turbulence, and this turbulence is exploited by a vertical axis, the a much cheaper and much smaller vertical axis turbine to get more energy. So I would like to hear some feedback from Professor Zahidi. Thank you very much.
The panelists have another keynote after. If you,
yeah, I will speak about that a little more, but I would like to exploit some know-how in this.
Ahmed Zahidi, if you have some conclusion.
You know that there are actually many differences, many factors affecting you. I give you one example. We had actually one vertical axis wind turbine in the city where I live, and we also had one horizontal axis, and in North Queensland. And North Queensland is subject to cyclone. It means turbulence. Sometimes in the wet season, we have very high wind. But the horizontal axis wind turbine could actually survive, but the vertical axis wind turbine damaged, completely collapsed. So from this point of view, you know, I actually personally, I have seen that, I have observed that vertical axis is more sensitive to high wind speed. And because I have seen horizontal axis survive cyclone, but vertical axis collapse, couldn't survive, couldn't actually.
Thank you, Dr. Zahidi.
Can I
all panelists, and we will
make a little remark
for the next
about this?
For the next program.
Excuse me, you have to close this session because the other session is will start just now. The last word.
Well, thank you very much to all of you.
Discuss this afternoon, perhaps. We have some time this afternoon to continue.
See you this afternoon.
Thank you, Professor Rashid Bishiri. Thank you, Professor Ahmed Zahidi, for your wonderful keynotes. Now we switch to the next session, next workshop 6. Digital technologies in solar energy. It will be shared by Professor Ali Ahitouf from Faculty of Science and Technology, Fez, Morocco. Professor Ali, the floor is yours.
Thank you.
Thank you very much, dear colleague. Good morning, all of you, and welcome for this session. Thank you for organizing for our organizer to give me this opportunity to moderate this interesting workshop. And I'm going to go directly to the program. And the first talk will be given by Professor Joseph Guerrero. It concerns living microgrids. And to introduce the professor, it is difficult to introduce this huge professor because he has a huge CV, and I can't summarize it quickly. Just to tell you that he is a full professor now at the University of Center of Research on Microgrid at Aalborg University in Denmark. He received his base degree in telecommunication engineering, the MS degree in electronics, and the PhD degree in power electronics. His research interest is oriented to different microgrid aspects, including power electronics, distributed energy storage systems, hierarchical and cooperative control energy management system, smart metering, and Internet of Things for DC, ADC, and DC microgrid clusters. Prof. Guerrero is an associate editor for a number of IEEE transactions. He published more than 600 journal papers in the field of microgrid and renewable energies, which are cited more than 50,000 times. He received a lot of awards, and I'm going just to cite to cite the last one. He received the best paper award of the Journal of Power Electronics in 2016, and during 7 consecutive years, from 2014 to 2020, he was awarded Clarivate Analytic from Thomson Reuters as a highly cited researcher with 50 highly cited papers. In 2015, he was elevated at IEEE Fellow for his contribution on distributed power system. Dear Professor, I'm sorry if I forget something, but the floor is yours.
Not necessary. Yeah. Thank you very much for the introduction. I'm going to share my screen.
Yes. Yes.
I don't know if you can you see it well? And
yes.
In presentation mode?
Yes. Yes.
Yeah. Excellent. So thanks a lot for the introduction and the invitation to give this lecture about living microgrids. You have more information, by the way, in our Center for Research on Microgrids. This is the website, ETAUDK, and you are welcome also to take a look on that. Let's talk about what is a microgrid. Microgrid is indeed a concept in which we can have renewable energies and, let's say, energy storage systems and consumption all together. So let's say as close as possible. This concept right now has been expanded to many other areas, like, for instance, water. They call micronets. Also food production, also when we talk about the 0 kilometer production of food and consumption and storage, and also closed ecologic systems, which I will talk also today. So I think it's a very nice concept in which we can rethink the way that we are generating, consuming, and storing the energy. This is a picture of our members. So also thanks for our 50 members in our research center. Because part of this presentation is thanks to them. Here you can see also our microgrid laboratories. We use a number of cabinets to emulate microgrid systems and grid AC and DC grid emulators also. So we basically use what is called also hardware in the loop concepts. From MATLAB Simulink, we are able to develop controllers, compile, send to digital signal processors, and then implement our ideas over hardware. And you can see here some smart meters. I will talk about that. So basically, we use what is also called power hardware in the loop. The only part which is virtual are the generators, batteries, and loads, but all about the power converters, smart meters, relays, transformers are physically in our laboratories. And also, we can make tests, because this laboratory is a multi-microgrid system laboratory. We can make tests of multi-microgrid clusters and also virtual power plants. These are some pictures of these laboratory facilities. Right now we have here an amazing lecture about wind generation. So we have also, of course, in Denmark, a lot of wind, also solar, and we have also developing prototypes also for companies, like, for instance, Zonen, which develop battery systems for homes. And we have also collaboration with Typhoon Hill to develop also all these platforms that finally has to go, let's say, in the real systems. That's another hardware in the loop systems that we have also in our laboratory facilities. Our research frames in our center are basically 4. The first one is microgrid clusters, how to clusterize microgrids. The second one is digitalization and Internet of Things. Fourth, and very important, maritime microgrids in ships and ports. And number 4 is space microgrids. Space microgrids, I'm going to talk a little bit about this. Microgrids in satellites, and also closed ecosystems for future Moon and Mars bases. So here you can see some pictures of our demonstration house, in which we have a number of appliances, some of them with IoT capabilities. Again, the picture from the rooftop. This is our demonstration smart home with the kitchen, the control room, the living room, And here's some pictures. You can imagine that we have lots of sensors here and monitoring all the electric system as well, thanks to Zigbee interconnection. So we have developed together with another company in Denmark called Debelco. There are smart plugs that are connected through Zigbee to our central controller. You can see here a picture of some of these Debelco meter in which we are measuring the wind turbine power, and we have a switch also. And then we have, this is the typical smart meter that we have here in Denmark. The same I have here at home, or many other people use this. And here you can see also our power generation changes inside by taking just the measurements from the smart meter and all the other monitoring, let's say, sensors, temperatures, air quality sensor also, which is becoming more and more important here. And what is very interesting is that from smart metering, we can also observe which is the appliance that we have connected. For instance, from an aggregated, let's say, measurement from the smart meter, we can disaggregate the information and we can know that there is an electric heater connected or a microwave or a fridge. Yeah? This is also called non-intrusive load monitoring because we don't need to put a sensor in each of our appliances. Yeah, and thanks to that, we can also develop home energy management systems. And when we think about integrating smart meters, some people think about electricity, but we have also meters of heat, meters of water, meters of gas, and all these things are integrated in our houses here in Denmark. So it's really a very holistic approach when we talk about the smart metering. And of course, when we have a number of smart meters, here, for instance, in Denmark, we can take up to 500 houses, collect information for the utility, and then present the information, especially power quality. The important thing is that not only the utility can take it from the blue line here, but also you can get it from home. So you can use your own signal through an optic eye that you can plug to a laptop by using a USB. So it's kind of very easy. And these are real measurement from a three-phase system. Here in our houses, we have three-phase. So you can see one of these phases are unbalanced. So that's very interesting to observe. And also, depending on the hour, there is some under voltage or over voltage. So we can know exactly if we are inside the limits. And I will say that this is amazing, especially now that we can see more electric vehicles plugging inside our system. Yeah. So this is how looks our IoT demonstration home, together with all the appliances and also the district heating floor system. After years researching microgrids, I decided to also become a prosumer myself. So this is my house. I installed solar panels, 2.4 kilowatt. And this is my car. It's a Nissan Leaf that have a 30 kilowatt hour battery system. And I install as well an electric vehicle charger of 3.7 kilowatt. So I did like a doctor taking your own pills. Yeah. For instance, one of my favorite doctors is Dr. House. Maybe you know from his series that normally the illness is lupus. And I will say that when you try to study control of electric systems, normally what you need is maybe a PI control. No? So I will say that this is very interesting also from the TV series. And I hear that it's also an Arabic statement. We say, if you really want to do something, you will find a way. Otherwise, don't worry, you will find the excuse. Yeah. So I think that now is the moment that we have to find the ways to integrate also ourselves more renewables. And many people right now are talking about artificial intelligence, right? But do we really know how our brain works? Because that's very interesting to see that we have really three brains. We have 80,000 million neurons in our mind, but it has been discovered that also in our heart, we have 40,000 neurons in our heart. And in our gut, all the digestion system, we have 500 million neurons, the equivalent of a brain's head. of the cat's brain. So it's really a distributed system. If you look at, for instance, the Indian idea of the chakras, they have some centers of energy. And I will say that they coincide very well where we have these neurons, right? Brain, heart, and gut. Yeah. So that's really amazing. Another thing is that how much we use our brain. We have here that normally we use maybe 5%, 10% of our brain, and so forth. We have to be very relaxed on that. We use 100% of our brain. It's been demonstrated. However, simultaneously, due to limitations of glucose and oxygen, we only can use it 2% at the same time. Yeah, at the same time. This is 4 watt exactly of electricity. We have electric brain, 4 watt of electricity simultaneously. However, we normally use similar neural network paths. We used to use the same paths. That's why it's difficult to change sometimes, right? We want to change our behaviors, but it is difficult. Yeah, very interesting also. Looking at the brain, we can see that we have indeed inside 3 levels. We have the reptilian brain, this brain more action, reaction, searching for opportunities, 500 million years. Then we have the limbic brain, which is more for mammals, you know, like dog, cats, etc. 200 million brains. This is more the emotional part, where we feel the emotions. And then we have the neocortex, only 100,000 years. This is what defines us as human beings. And I will say that the most amazing part is the frontal part of this neocortex, which allow us to go to the future, anticipate what will happen, and come back to the present moment to take a decision. This is something that other animals cannot do. And this is really amazing, right? This is in the neocortex. However, major part of our decisions are taken in the limbic brain by emotion. Yeah, so emotionally, we take a decision. And then the part of neocortex, the rational part, comes with the justification. That's also something complicated to deal with. Another important thing, we hear that stress is not good. Stress. No, indeed, many studies demonstrate that moderated levels of stress are good, and you can generate dopamine and noradrenaline, so you can activate more your skills of learning, attention, and so on. However, if the stress is very, very high, then of course efficiency curve goes down and appears anger, violence, syndrome of burnout, I will say. Another important thing, how our heart communicates with our brain. There is a bidirectional communication between our neural networks that are in the heart and the brain. However, it has been discovered by HeartMath Institute in Germany that there is more information going from the heart to the brain than from the brain to the heart. So sometimes I wonder who's the boss here, right? You can see here also some heart rhythm paths. Some people think that heartbeats must be constant. This is not true. What is happening is that heartbeats are changing all the time in order to maintain the blood pressure constant. So what sometimes we measure is the average. You can see here when we have feelings of frustration, anxiety, worry, irritation, how this heart rate has a lot of harmonics and a very non-coherent, non-periodic signal. However, when we feel positive emotions, appreciation, love, courage, you can see how we have a almost pure sinusoidal waveform in this heart rate. So that I will say that is also something very really amazing about this field. And that's finally about the heart, knowing that it has 5,000 bigger electromagnetic field than the brain, and this signal can be measured in more than 3 meters at a distance. So it's something that some people also study heart synchronization. Sometimes it can happen to people that feeling love together. They can synchronize their hearts even without touching each other. That's amazing. Let's talk about also microgrid control. And you can see here the primary control, which is more like this action-reaction brain, right? Like the, yeah. You can see here the Drup controllers, which reacts again active and reactive powers. But today we have a lot of equipment that already use these concepts, like you can see Fronius or Victron, that have really these frequency control systems and allow us to implement real microgrids. Yeah. So here you can see also the control of a microgrid system. We have the primary control, which it's like, I will say, like this reptilian brain action reaction. Secondary control, which tries to restore not only frequency but also voltage, because we are in a microgrid system. And I will say that this is kind of the limbic brain. And then we have the energy management system in the tertiary control, this brain that allows us to go to the future and then come back to the present moment and take actions, like our neocortex, which is this tertiary control. So that's something nice. We can also have controllers more centralized or more distributed. There is no a single solution. So sometimes we kind of decentralize more the lower levels and more centralize the higher levels of control. And this also allows us to interconnect microgrids together, so we can have higher levels of control, which are without disconnecting, let's say, all the communication systems that has been developed. Another important effect is the whack-a-mole effect. This is a game in Korea, very famous. So people is whacking a mole, and the mole appears in another part of this table. This happens a lot when we try to, for instance, compensate harmonics in some parts of the grid, and then these harmonics appears in other parts. In Japan, they have a lot of experience about this, installing active filters, and then, yeah, kind of trying to find where is the optimum point. And then talking about Japan, also we have some microgrids there. This is a DC microgrid system in Sendai, and that's a number of solar panels with gensets and fuel cell system. And this is very close to Fukushima. And what happened the day of the disaster, now almost 9 years ago, it was March 11, 2011, yeah. And it was the earthquake, and at that moment, the microgrid was working in island during 3 days. This microgrid was supporting the hospital, so you can imagine that that day was a big mess, and also supporting the telecom, so people could call home, etc. So it's important thing, because we can see how renewable energy systems could support a disaster from other kind of energies. And if we go also a little bit at home, we can see that many technologies are appearing. This is just one picture from my Nissan Leaf, in which you have a fast charger here on DC, and then the slow charger is integrated inside your car. So we have several levels of voltage, etc. And you can see also that right now we have the possibility also of using the battery connected to your house in a bidirectional way. So right now there are more companies developing this concept. And I will say that because right now we are expending a lot of hours working at home, it makes more and more sense than installing stationary batteries. Other places in which more electric systems are appearing is electric vehicles. So we have aircrafts, of course, cars, ships, and other existing. So in the case of aircraft, we have, for instance, the Boeing 787, which have some parts on electric. Of course, the main drivers are not electric, but they have auxiliary starter generator units that are pure electric. And you can see here that we have a number of AC microgrid systems on 230 volt on the airplane. And then we have a number of DC microgrid systems, bipolar ones, plus, minus, and 0 to 170 volt in DC, integrated with battery system. So it's becoming really a microgrid as well. Another place in which microgrids are appearing is in ships. So you can see more and more ships having electric systems and batteries. And this is happening here also. For instance, we have in the south of Denmark full electric ferries and hybrid electric ferries as well. Some of these technologies are moving also to DC. So we have more and more ships moving to DC technologies also. However, the problem here is that even though the efficiency could be higher, then we have problems with the, then you can have problems with the protection systems. Some developments has been done with Siemens and ABB, so you can see that you have a DC bus, and then of course the higher is the distance, because in some ships these lines are really long. Then of course you have more losses, so you have to increase more and more the voltage levels beyond 1000 volt. You start to have chips moving to 3.3 or 6.6 kilovolt. So then, as I mentioned before, protection system is really a problem. And why some ships are moving from AC to DC is not because DC is more efficient, which is basically not true, not a general statement, but because our synchronous generators are more, let's say, efficient in some point of operation. When we move to AC, we have 50 or 60 hertz, so they are fixed in this operation, and that means that for different operation conditions, efficiency can change a lot. You only have one optimum operation point. However, if we move to DC, we can adjust the rotation speed according to which is the load that is demand. So you will have a more flat consumption. Talking about also ships, we have more problems with the, or challenges to the ports, let's say, because some ships arrive to the port and they start burning diesel or oil to generate electricity, because, for instance, they arrive with a freezer with a lot of fish. Because of that, we provide them more and more in Europe dock stations, so you can plug your ship to the main port. But this, of course, is a challenge because we need different voltages and different frequencies, and we need to increase the electric infrastructure in our ports. That's why these kind of configurations are appearing, especially here in the north of Europe. So a number of inverters working on 50 or 60, depending on the ship, where it comes from, different voltage levels, and then a common DC microgrid system, which is connected to medium voltage. So rectification, and then just choosing which is the appropriate ship. Another challenge point are the cranes. Some of these cranes are still burning diesel, and this is another point of CO2 emissions, very important to reduce in the next years. So that's why we are substituting also all these diesel generators by connections to the main point of electricity. On the cranes, once you need to lift up a container and appears the ship, lift up, you need to inject energy. However, when you lift down those containers, you can convert this motor to a generator. So instead of burning the electricity in dummy resistors, you can reuse it. And according to the last studies, you can get between 40 and 50% of energy recovery. This is a lot, I can tell you, this is a lot. So you can reduce also the power, the energy consumption in the port, and also reduce the peak of electricity needed. Finish with the marine systems, we go to the space, and you can see how more and more in nanosatellites we have also DC microgrid systems, including photovoltaic systems, battery systems, and also very pulsating loads, cameras, communication systems. Here the challenge is that we have cosmic radiation. So this means that the sun is radiating protons and many other particles that deteriorates the photovoltaic systems and also can hang up the microprocessors. So it's very important here that all those controllers are analog controllers. The microprocessor is only a supervisor because it's very easy that can be hung up. So here, analog electronics becomes very, very important. And this is big news because we thought that analog electronics was almost dead. And here we really need good analog electronics designers. Yeah, so that's an amazing field of research, I will say. And finally, I want to show you one example of how we can implement some ideas that we have been developed for electric microgrid systems be translated to closed ecosystems. This is a project together with the European Space Agency and the University Barcelona, Autónoma of Barcelona. And in that case, what we want to do is give a life support system to the astronauts, provide oxygen, water, food, etc. This is to create a small ecosystem. We have been seeing that this small ecosystem, we provide water and CO and oxygen to the crew members. And of course, we have waste. So from this waste, we are, you can imagine, we can get also nitrates and minerals. And then here, what we do is we subtract the CO2 and get the oxygen. Of course, you have some photosynthesis here from the microalgae and from some higher plants. This is the plant, which is placed in Barcelona from the European Space Agency, the nitrification compartment, bioreactor, and here is the plant compartment. And in our case, the crew compartment, in that case, are rats, because we are still making the test in the laboratory. And here is very important to fix the oxygen in a very tight requirements of around 20%. Otherwise, if it's higher or lower, the crew members can die. So that's very important to fix it. So this becomes a closed loop system. However, it's very difficult to control because here we have hundreds of state variables with high non-linearities. So it's really a very complex system. Yeah. So what we did here is we observed that microgrids and closed ecosystems has some parallelism. You know, when they make the photosynthesis, is kind of similar as our photovoltaic system. When we store oxygen, it's similar than when we store electricity. And then here we have microbial fuel cells, which are similar as our hydrogen fuel cells. So we could develop similar control systems. And right now we are testing with very good results by using the same hierarchical control structure that we did for microgrids. So what we did in the past, controlling the primary control voltage and current, here is mass flow regulation. In the secondary control, it was voltage and frequency restoration. In that case, is corrective actions, prescriptions for the flow dispatching. And the tertiary control, which is the energy management system of our microgrid, in this case, is a level of control that designed the long-term optimal operation set points for the entire plant. So I think that's an amazing thing because we can control one closed ecologic system the same way as an isolated microgrid. So that's, I would say, a very nice result. Just for finalize, give you thanks, and I would like to finalize with this statement from Arnold Schwarzenegger, which said, "The future is green energy, sustainability, and renewable energy." Thank you very much.
Thank you very much, Professor Guerrero, for this nice presentation, interesting presentation, and already we have some questions from
Thank you.
daughter who asked if you can share your slides.
Yes.
The discussion will be at the end of the three presentation, and now I'm going to move to the next presentation, which deal with the role of power electronics in providing a sustainable energy supply by Professor Saad Makhlief from the University of Malaysia. Saad Makhlief is the Dean of the Faculty of Engineering, University of Malaysia, Kuala Lumpur. He was seated by Clarivate as sorry, because the screen is moving on my computer. He was seated by Thomson Clarivate as one of highly engineering researcher in the engineering researcher in the world, and included in Thomson Reuters, the world's most influential scientific minds during 2018 and 2019. He is actively involved in the industrial consultancy for major corporations in the power electronics and renewable energies projects. His research interests include power conversion technique, control of power converter, maximum power point tracking, renewable energy, energy efficiency, smart grid, microwave, and wireless technologies. He's he is an associate editor of various sub-journals in I3E, Transaction on Power Electronic, and the Journal of Power Electronics. He is also a professor at the Department of Electrical, Faculty of Engineering, and University of Malaysia since June 1999. Dear Saad Mkhalif, I hope I will introduce you, and the floor is yours now. And thank you very much.
Thank you very much, Professor Ali, for the introduction. Thank you very much. And I just would like to ask how much time I have?
30 minutes. Sorry, 30 minutes. Yes.
30 minutes. Okay. Thank you very much. Okay. So good. We are afternoon. So good morning there in Morocco, and good morning in Europe. So we have now we are almost 5:20 in the afternoon. So my presentation is about the role of power electronics in providing a sustainable energy supply. I think the previous presenters have shown the increase of power electronics in our modern grids and also our modern utility supplies. So I'm going just to enforce this. Okay, so the outline of my presentations will be energy and environments, challenges in energy, sustainable energy, and then challenges in energy conservations, and the grand challenge. Okay, as we all know, the world populations is growing, and it will be around 9 billion by 2050. So this is a fact, taking the current growth rate. Also, what is very important is the energy consumption will be double by 2050. So the world population will grow by almost 30%, but the energy consumption per person will increase significantly. And this is a fact also, because if we look into our daily use of energy, is increasing day after day. If you look 30 years back or 40 years back, the energy consumption per person is very limited. However, we can see nowadays that every person, the consumption of energy is increasing. You can see every person have a laptop, every person have a mobile phone, every person, every home have washing machine, air conditioning system, everything. So what does this mean? It means that our energy consumption is increasing, and it's going to be continue increasing. What is else also very important, 65% of global warming is coming from energy generation and energy use. So the way how we use the energy, the way how we generate energy is not efficient enough. Means there are a lot of emissions still are still generated during the process of generation and the process of utilization. Okay, also we see this some of the impact of greenhouses. You know, we see that there's extreme weather conditions. I say extreme means you can see there is winters, very harsh winters, or sometimes very warm winters. We see sea level rise. There are many locations around the globe which sees what we call sea level rise. And also we see in the past 50 years, the world has lost more than 25% of its topsoil and forests due to human being activities. What is most importantly, at the emission, the current emission rates, the coral reefs and the polar ecosystems will be severely affected by 2050, and it becomes irreversible. It means after that, whatever you do will have no major impact. Okay. Acid also is not actually infecting only the ground, but also affecting the seas and the oceans. The acid levels is continuously increasing, and you can see here the acid levels 30 years ago, now, and what will be in the future. The darker color means the acid level will be increasing and increasing. Okay. So whenever we open our TVs every day, either we see these kind of pictures, floods in many locations which never experienced flood before, or we see these pictures. We see a drought where many areas are having less water access in areas which used to be very green. Earth temperature, also earth temperature is increasing. I think the last Paris summit has already notified this, and it continues to increase. And even some very cold places, Europe. Europe used to be one of the coldest places, you know, but it's not anymore. In 2011, more than 20,000 people died of heat waves in Europe. Okay, so this actually shows the increase of the temperature on the Earth, you know. So we need to do something about it. So the challenges is renewable energy and energy conservation. Renewable energy, I think we are all well versed, and also it's well known, and also it's already shown it can replace the conventional sources. But what is missing here? It's the energy conservations. We have less people talking about energy conservations. Energy conservations is something that we should do before start thinking of renewables or something of other sources. Energy conservations is the use of energy efficiently and effectively. That is the most important, because we may think, okay, yes, we want to go for renewables. We want to install certain amount of PV panels, certain amount of wind turbines, but the way how we are still consuming and using this energy is not efficiently. It does not make any difference, because the total consumption will increase. So energy conservation is a practice that we should always do. And I really like this statement by the ex-US President, Jimmy Carter, not the current one. The current one, you know, is totally the opposite. Energy conservation is an act of patriotism. Means if you really love your country, if you really care about your country, you should do what you call and practice energy conservation. Okay, so that's the way. The way is, for example, if you want to turn on an air conditioning systems, why you have to set the temperature at 16 degrees or 17 or 18? We know the comfortable temperature is 24 degrees or 25 degrees. So that's how, if you leave a room, you should switch off the lights. Yeah, so that's the way how we should think. For renewables, okay, I think God have given us a large amount of resources. You can see the amount of energy available only from the sun is more than 2,850 times. The wind, 200 times. It means if we use only 0.5% of what is wind provided, it's enough to supply of what we need, energy globally. And I always show this picture. This picture is actually an aeroplane which took off last year from Abu Dhabi, and it makes one big round across the globe and land back. This shows actually this one day maybe some part of our airplanes, and now most of the new airplanes are more electric. Maybe some parts of it will be powered by renewables. Doesn't matter what types of renewables, you know, it can be a biodiesel, it can be solar, can be whatever, you know, but it's some of the energy consumed. Maybe it will be from okay. And this is the interesting study done by a manufacturer of solar cells, Qcell. Qcell is a Korean solar manufacturer. This Korean solar manufacturer done a study in 2017. And if they found out actually, if we install this amount of solar, I think this is near Morocco or Algeria, if we install this amount of solar panel, it's enough to supply the whole world of electricity. If we install this amount, it will be enough to supply the whole EU, you know, the European Union. If we install this, it's enough to supply the whole MENA region, the Middle East and North Africa. Maybe they are just doing a promotion for their solar panels, but for me, let's make this double or triple or maybe 4 times or 5 times. It means it still makes some sense. It means there is a lot of resources that we can still use. And nowadays we can see there's a large amount of solar also moving into hybrid, where, for example, we have dams, and on the top of the dams where you can have solar panels. So we can generate, we can optimize the space and the area used, because one of the problems with solar is the space utilizations. And also there is, you can see there is a very bright future actually. The improvement of the solar cells efficiency is keep increasing year after year. Also the cost of the solar panels is decreasing also year per year. And just to show you this is quite important figure, you know, it's on the role of power electronics in photovoltaic system. You can see whatever range from watt level, from 50 watt to 100 watt to 200 watts up to kilowatt levels, all requires power electronics interface. Okay, so whatever you use or whatever you do in photovoltaic systems, you still need power electronics. Without power electronics, all these devices will never work. And also when you want to interface with the grid, the same things, we need the power electronics. Wind, also the same wind turbines. I think the recent wind turbine, the 9.5 megawatts wind turbine, the largest in the world, you know, 9.5 megawatt. And is a growing 30% every year. And these wind turbines are 100% now powered by power electronics converters. Okay, and also it's increasing year after year, the capacity. And this shows the use or the introduction of power electronics in the wind turbines. You can see recently 100% of the wind turbines or the power is processed through the power electronics converters. Yeah, I think there is a lot of research also on the type of wind turbines which can be used especially on the rooftop of buildings. And this shows also that the role of power electronics in renewables is in wind turbines is also an important component. Yeah, this is how the existing and the future potential configuration of wind farms. You can see nowadays most of them will be full-scale power converters, AC, or either AC or DC grids. Both of them requires what we call power electronics. So we can conclude from these two, the main major renewables are dependent on power electronics devices. So to go back to our main objective of the emissions and the generations, if you this is a study done by this paper published in Science on the relationship between the generations and also the emissions. And here you can see, if we continue business as usual, the generations will continue to increase as linearly. You can see here, it's going to increase linearly. But if we decided, for example, to stop or to maintain the emission level constant, all right, we need this what they call the green color triangle here, which is call it the stabilization triangle. This stabilization triangle will help us in continuing the emission, continuing the generation, increasing the generations, but the emissions remain constant. Okay, so what is required? And this is the base year. The base year depends, whatever year you choose. If you choose, for example, 2020, so the triangle will be this, all right? So what is required to stabilize the emission and continue the generations? This is what we have to do. 1, install 1 million 2 megawatts wind turbine. Okay, 2 megawatts means almost 300 times the current capacity. 2, install around 3,000 gigawatt peak of solar power, or what is equivalent to 215 times the current capacity. 3, install 700 gigawatt of nuclear power plants. Okay, one nuclear power plant usually of the size of 1 gigawatt. All right. Well, you may ask questions, why do we need nuclear power plants? Nuclear power plant is one of the most reliable so far source of electricity generation. And we need this kind of energy mix in order for us to maintain the stability of the system. Increase the fuel economy of 2 billion cars from 30 to 60 miles per gallon. So our current IC engine, the internal combustion engine, is not efficient. We need to improve the current IC engine, or maybe shift to more electric cars, either hybrid or electric, because simply because the emission levels cut the emission from the building by 25% by 2025, and also introduce what you call carbon capture and storage of almost 800 gigawatts coal-fired power plants, which is equivalent to 800 nuclear power plants. So my question is this doable? If you ask me personally, I think these numbers are too big. You know, it's too big. You know, too big and too costly to implement, because it's something very, very huge. 300 times the current capacity. It's not easy. You know, to reach the current capacity, it took us 20, 30 years. To double or to make this double or triple, maybe, but to make it 300 times looks. So it's not it's impossible actually. So what does mean impossible? Means the emission level will continue to increase as we increase our consumption and our generation. All right. So let's look into this. Give you a simplified what you call figure of our current energy supply system. Okay, if you look into here, the left-hand side is the generations, and this is the load or the use. What you can see here, we are seeing more power electronics in everything that we use. Solar, as we said just now, it's more dependent on the converters. If you have storage, we need power electronics. Wind, you need power electronics. A fuel cell, a hydrogen-based technology, which requires power electronics. So what does it mean? The generations is almost 100% dependent on power electronics at this moment. And that the same things applies for loads. For example, if you go and purchase a fridge today, yeah, you need a inverter-based fridge. You buy a TV. A TV is an LED TV, which is power electronics driven. You buy lights, which is an LED lights, a motor drive, robots, a phone charger, laptop, desktop, whatever, just name it. All are power electronics driven. So the idea is here, if we make an efficiency improvement of all these converters and inverters that's used either in the generation side or in the distribution side or in the load side, a small percentage will be very significant improvement. Because if you ask, maybe we can, if, for example, if we do the improvement of an LED driver, which drives an LED lights by just 1%, multiply that 1% by billions of light bulbs exist in the world. And you can see the amount of saving that can be generated from this kind of technology. So that's actually my main focus point. My focus point is how we can use power electronics to provide a sustainable energy supply. Actually, through this, by we seeing this from the generation side and from the load side, you can see actually there is a huge potential for power electronics to play a major role in providing sustainable energy supply. Yeah, wind, as we know, the interface from the wind to the grid is all power electronics. I think I have mentioned this, but it's whatever power you see. Maybe because of the time, storage, whatever is all power electronics interface. Even for power quality improvements, we need what you call STATCOMs, which actually power electronic devices. Okay, let's take this, the total energy consumption on the world. You know, current, it's around 40% of the current energy consumption is electric. 60% is still non-electric. Okay, so most of the energy that we use today is still non-electric. Okay, because you have to see the factories, because 60% of the energy is consumed in industrial sector. So most of it is still non-electric, 40%. Okay, what does this 40%? In 2012, which is 8 years back, which is quite old, we have consumed more than 20,000 trillion watt hour of electricity worldwide. What does this mean? This is a nuclear power plant. An average nuclear power plant, usually a nuclear power plant of 1 gigawatt, able to generate around 7 trillion watt hour of energy per year. 7 trillion watt hour per energy. So if you divide 20,000 per 7, you will find, means in 2012, we have consumed more than what's produced by 3,000 nuclear power plants of electricity. So it's some huge amount of consumption. At the moment, 2020, you just simply multiply it by another factor of 1.5, easily. All right. So if we break that 40%, you can see it's mainly consumed in the motor drive, which is actually industries, the IT, light, and others. Okay. So if we just make 1% efficiency improvement in these others, we can actually save what's equivalent to 23 nuclear power plants, which is almost the total power generated by wind in 2012. You can see the current system. This is the current system. Usually what we have the grid, we have the PV, we have the wind, we have the storage, we have electric vehicles. So what we do from the solar, we convert from DC to DC, and then from DC to AC, and then connect to the grid. And then when we want to use them, then we have to convert from AC back to DC, and then convert, because most of these are already power electronics driven. So what you can see, we have an inverter here, we have another rectifier here, and so on and so forth. So every conversion, as you know, we have losses. Every inverter have a losses. There is no such inverter which works 100% efficiency. Even 99%, there is no inverter works at any load at 99%. Inverters has an efficiency curve, and this efficiency changes depends on the load. So there is no an average efficiency on inverter. Maybe the best would be around 90 or 85% efficiency. So if we can remove all these inverters and convert it to a DC bus, you can see the amount of efficiencies that you save. Just imagine how many inverters from the solar, how many inverters from the wind, how many inverters from the storage, how many inverters from the electric vehicles, and the same thing goes to the load. You can see it's a huge amount of saving. IT, you see IT, we can see there's an increased number of IT devices nowadays. So there is an increase of more, if we just improve 1% efficiency improvement, so it's able us to save almost 20,000 trillion watt hour of energy, which is equivalent to 3 nuclear power plants. And you can see there's a large number of data centers nowadays, and there's a lot of demand of this cloud computing and so on and so forth. Actually, I have to skip this, but yeah, because I'm running out of time. So I'm just giving you this example. This example actually, it's the power supply of our laptop chargers. This is the previous hard switching charger. Sorry, this is the hard switching charger, and then we have the soft switching charger. And you can see the improvement of just moving from soft switching to hard switching. You can see the amount of efficiency improvement from 85% to 95% within the span of 4 years. And this is saved us almost 60 nuclear power plants, because you have to multiply how many laptops around the world, and then how much the efficiency improvement of each one of them. Okay, so also the data centers, most of data centers now are moving into what I call DC data center. This is the traditional AC data centers. Okay, so the current one, which is start moving, one of them is Google, is almost moving to DC data center. And you can see the amount of conversion that we have reduced. which is almost 5% of energy saving, which is equivalent to 15 nuclear power plants. Light, one of the very important components. Light. If we just switch from this bulb to this bulb, we can save between 4 to 5 times of energy. If we switch to LED, another 4 times. You imagine how many light bulbs are around the world. There are billions of light bulbs. So we can save almost 450 nuclear power plants. Motor drive, one of the biggest one, the red color one, the big one. So as you know, if we assume 40% of the motor drives are already having VSD, maybe around 60% only needs a VSD or variable speed drives. So if we install the VSD, you can save almost 30% of energy. So it is equivalent to what is generated by 300 nuclear power plants. So let's look into the industries, the same. I think we have seen just now. If we move to more electric cars, more ships, more aircraft, buses, and so on and so forth, we can save a lot of power electronics. And how about if we, you can see this 60-40, if we switch to this, we can easily save almost 1,000 nuclear power plants. Means moving from non-electric to electrics, actually, we can save a lot of energy. I think the previous presentations also mentioned this in many locations, okay? And this is another example which is proof this. So if we have an IC car, which is internal combustion engine car, and then we do the oil, a refinery, and then we boot, and then this usually take us around for 670 miles per barrel of oil. 600. If we do the same, we just change this car to electric, we can go to 1,100 miles more. So it's almost 65% energy saving. How about if this switch to wind? That's a huge amount of saving that we can introduce. And this is just to show you that the world is moving more to electric. I think this is the energy flow diagram of the United States in 2009. You can see the percentage of electric is only 40%. The other 60% is non-electric. This is what they plan. They are planning for the next, by 2035, 80% of their energy consumption will be electric. 20% will be non-electric. Okay, I think, so my questions is, do we still need more power electronics or more nuclear power plants? And I think I'm ready to take some questions. Thank you.
We don't hear you, Professor Ahitouf. We don't hear you. Please unmute.
Sorry.
We don't. Yeah. Okay.
Sorry. Thank you very much. Thank you again, Professor Saad Mkhlif. Sorry for this problem.
Thank you very much.
For this interesting presentation, and we will go to the presentation of Professor Said Ahzi, which concerns multiphysics analysis for the prediction of performance, degradation, and fatigue failure of PV panels. And to introduce Professor Ahzi, it is a real pleasure for me because he's started his studies from the University of Metz, from which he held both the PhD and the habilitation in 1995. After that, he moves to the United States of America for the postdoctoral research. Afterwards, he moves to the University of Strasbourg. In the University of Strasbourg, he holds a position of distinguished full professor. After that, he moves to the College of Science and Engineering in Hamad bin Khalifa University at Qatar. This is. Also, he holds a position in Georgia Institute of Technology. Said Ahzi is a member of several professional societies, including the Mineral, Metals, and Materials Society, the American Society of Mechanical Engineering, the European Association for Dynamic Behavior of Materials and its Application, Material Research Society, MLS, the French Association of Mechanics, and he's an associate editor of 2 international journals, Journal of Engineering Materials and Technology, and International Journal of Theoretical and Applied Multiscale Mechanics. His research interests in the general area of material science and processing with application to energy, environment, nanotechnology, biomedical, and industrial application. That is not all his CV, but not all his resume, but I stop here. Otherwise, I'll take much time. The floor is yours, Professor Said Ahzi.
Well, thank you, Professor Haytouf. I did register my stuff, so I will be going through the registration, and I explained the reasons actually because I am in the middle of moving from the current house to another house, so maybe I may be disturbed a little bit. So, but I will answer questions. I'm listening. I've been working the last few years at Qatar Environment and Energy Research Institute, where this work has been conducted, and in collaboration with Shahzada Pamir Ali and Nicola Bart. And I would like also to thank Dr. Yusuf Zaz for inviting me for this presentation, which is on the multiphysics approaches and analysis for the prediction and performance of degradation and fatigue failure of PV panels. As you all know, there are certainly many advantages for solar energy, such as abundance, distributed almost evenly worldwide, and also less maintenance, some small scale and large scale possibilities. However, there are also disadvantages, such as the fact that we cannot harvest at night. The power production is greatly affected by the weather conditions, and I will talk about that particularly for desert conditions, because we are going to in this analysis I will be presenting, we are looking into the effect of desert conditions in terms of temperature and wind and so on. And of course, another disadvantage is commercial production and requirement for large areas. So the PV system performance can be decomposed into four actually parts, which is the part on the performance due to radiation and optical, and also the thermal performance, so which measured through the temperature of the cells, and the electrical performance, which in fact is measured through the maximum power of the PV cell or the module. And then also the structural performance. These PV modules, they will fatigue over time, and certainly they will degrade, their efficiency will degrade until they fail completely. So these are the three measures of performance, and I will talk about a few of these things. Actually, all of them. I will talk about the 4 parts in terms of modeling and simulation. Now, in terms of multiphysics modeling motivation, we wanted to, there are certainly a lot of models out there, but are not necessarily accurate, are not necessarily all physically based. There are a lot of simplifying assumptions, and may not be accounting for full transient situation. So we wanted to develop a model that is fully transient for temperature prediction, and also accurate enough, and that is coupled between radiation and optical modeling, thermal modeling, electrical modeling, and structural modeling. So that's why in each there is a different physics, and that's why we call it here multiphysics modeling. And also there is a strong coupling, as you can see in this chart in here. We have the radiation modeling, and we have the thermal modeling. Radiation modeling is connected to electric and connected thermal, and thermal is also connected to the structural modeling. So the motivation is for better visualization and assessment to mitigate prediction error in each model, and to reduce computational time, and also to improve reliability and credibility of the simulations and predictions. So now for the first part, this is radiation plus optical modeling. We proposed some time ago a simple model to compute the absorbed solar radiation, which is given by this relationship here, S as a function of the global measured radiation, which is plane of array in this case, and of course weighed by these two parameters, which are the effective absorption of the PV cells and the average transmittance of the glass. And this is given in fact by the average transmittance of the glass is given by this relationship, which depends on the glass properties such as glass extinction coefficient and also the glass thickness, and of course depends also on the incidence angle and transmittance angle as shown in this picture in here. So this is a model that accounts for the global radiation throughout all the wavelengths, and this is different from certainly many models that exist in the literature. So the heat equation, this is thermal modeling, and for the thermal modeling we use the generalized heat equation, which is given by this relationship where rho is the density, C is specific heat, T is time, capital T is the temperature, K is thermal conductivity, and Q is internal heat generation. And these are the elements of the PV panel, the glass, the EVA, which is the polymer, PV cell, and the EVA again, front EVA, because these are the cells are encapsulated using the EVA, which is a polymer material, and also we have the Tedler or backsheet. In these first calculations, we are neglecting the anti-reflective coating. It's very thin. It's not going to change much the results. And in the first part, we are also neglecting the presence of interconnect ribbons, which are copper ribbons. But again, they are very thin, but we will come back to this. We are going to include them later on in a later phase for the degradation or mechanical degradation or fatigue degradation. Just to show you some of existing models out there. This is not exhaustive, but we're just listing some of them, and we're listing actually here the disadvantages of these models, and show also that the need for a more accurate and more inclusive and generalized model out there. Especially, it has to be the model that we would like to develop has to be fully transient, has to be simple, it has to be computationally feasible. So we worked on 1D finite difference model, one-dimensional. Then we extended it to a two-dimensional finite difference. We use also 2D finite element model, and we use 3D finite element. However, we focused mainly on, in this work, I will focus on the 2D finite difference and 2D finite element using ANSYS code, but he is using our code, which is we use MATLAB. But I will show also some results maybe from the 1D finite difference, just to give you an idea of how it does compare those results to how do they compare to 2D. And I will show also some 3D finite element, especially at the last part for structural analysis. Now, again, the continuity of the thermal modeling. So here I'm gonna look at the loads and boundary conditions. First, the heat generated or internal heat at the PV cells. So the internal heat generated the PV cell given by this relationship here, where S is the incident PV cell irradiance that we calculate from our proposed optical modeling. This is the area of the PV cell, and this is the volume PV cell. And eta is an important factor here. This is the efficiency, which in fact decreases with increase in temperature, as you see according to this linear relationship here. Okay, and then also the internal heat generation at the front glass, which is also given by this relationship, where we have the global irradiance measured, and we have the area of the panel or the glass and volume of the front glass, and this is the coefficient, which is the absorption coefficient of the glass. The other thing also is the heat transfer modes. We are using conduction. We are using considering convection, okay, free and forced and combined in one model. And then we are also, of course, using radiation, sky and ground radiations, as you can see from this schematic in here. Now, one thing we did to improve the accuracy of the modeling is to look at the heat dissipation and look at what's in the literature, and all of the existing models use this schematic here for the heat dissipation. Okay, and what we did is with this we were not able to accurately reproduce the experimental results, so we looked at how we can improve this, and by just looking into the boundary conditions, the sides and the top and the bottom of the PV panel, we decided to redefine these boundary conditions in terms of sink temperatures, as you can see here at the bottom, at the top, and also on the side. And by doing that, we were able to improve the results quite a bit. Here, one of the first results, these are the inputs from the measured data at the testing facility at Kiri, outside testing facility, where we measured the ambient temperature and incident POA. They are given here. This is the incident POA in blue, and this is the ambient temperature for one day. And this day was May, during May 2013. And this is the wind speed during that day. These are all measured, and these are inputs to our modeling. And then the output, we looked at, one of the output is look at the temperature at the back sheet, predicted temperature in blue versus measured temperature at the back sheet in orange. And this is using classical dissipation modeling. The results are close, but not that great. Actually, as you can see from the root mean square error, it's 3 point something. Whereas here, when we introduced our new dissipation, heat dissipation modeling by changing or by correctly defining the heat sink, the sink temperatures on top, bottom, and sides of the PV panel, we improved drastically the simulated result. They are very, very close now to the experimental, with a root mean square of 0.8. We took different days with different conditions: a sunny day with clear sky, a sunny day with cloudy sky, a rainy day with overcast sky, and another two consecutive days, and to see how the model will perform. And in all of them, as you can see, the model performs really well if we compare the measured temperature at the back sheet against the predicted temperature by using our model. Now let's go to the 1D finite difference. We also looked at the 1D finite difference that we presented before at IRSEC, and we also improved the results by just changing the heat dissipation modeling, especially the top and bottom and side boundary conditions, or heat sinks, or sink temperatures, sorry. As you can see from this 1D finite element, again, these are the inputs from one day in July 2014 in terms of ambient temperature incident POA, and this is what we predict in terms of the temperature prediction. Another day, a sunny day with cloudy sky, a rainy day with overcast sky, and as you can see, the predictions compare really well in the three cases with the experimental results, which means that if we are just looking for temperature at the back sheet or even at the cell, one-dimensional model is sufficient. However, it all depends what you need. If you need to have an accurate distribution of temperature throughout the panel in the two-dimensional and three-dimensional, you have to go to two-dimensional, three-dimensional, and I will show you that two-dimensional is probably enough, okay? But one dimensional, it all depends on the application. If I'm just looking for temperature, one dimensional is more than enough. Now, we also performed two-dimensional and three-dimensional finite element simulations. As you can see here, the first row is 2D finite element, and second row is 3D finite element. And in both, we show the CAD model. And this is the NOCT, which is steady state analysis, but the transient analysis by taking 1 day during the by taking 1 day and simulating in Qatar and simulating the temperature of the backsheet, if the panel that is considered, we can see that we have very good accuracy with the root mean square of 0.8 and 0.6 in 2 dimension and in 3 dimension. So 3 dimension is a little bit more accurate, but not. We don't need to go there because it's computationally heavy and expensive. And I think the 2-dimensional is more than enough in this case. Now I go to electrical modeling, and the electrical modeling is used to estimate the maximum power. The inputs are the PV temperature or the cell temperature, and also the global irradiance. Now there are two ways of looking into this, either using simple power correlation, and there are plenty of models that exist there, or relationships proposed by different authors, or use a detailed electrical model that gives complete IV curve and calculate the maximum power, as you can see from the IV curves here. Now, we decided to go this way, and we used before I go to what we did, just to show you how many correlation relations that exist in the literature actually to calculate the maximum power. Plenty. But is this good? Well, certainly it all depends on the application. It all depends on the type of PV that you are considering. In our case, by the way, or probably did not mention it, we are using here the panel that we are considering is polysilicon based panel. So now the electrical model, we use the classical one diode model, one diode circuit model, which is given by the current is given by the relationship here, and the parameters in red are the 5 unknown parameters, which are the light current IPH, or the diode dark saturation current, or series resistance, shunt resistance, ideality factor. So these are usually calculated through iterative methods or optimization techniques. All right. However, these are also dependent on temperature. All of these 5, and temperature of the cell, and also on the global irradiance. So to include the effect of temperature and radiance on these, one can use an existing approach by De Soto and co-workers, where they propose the translation equations to give the photocurrent, for example, which depends on the irradiance and temperature, but the other parameters depends on only one, either temperature or irradiance, or constant, like here in the series resistance. Okay, so we developed a new idea based on methodology called the shift factor based method. Again, this is the one diode model as previously shown. The parameters 5, we call any parameter is called P, could be any of the 5 parameters, and the variables we have both the irradiance and the cell temperature, TPV here. In order to develop a generalized way for shifting these 5 parameters function of both the irradiance and temperature, we tried to fit the results from this one diode model to several IV curves for different irradiances, okay, and different temperatures. That's in this example from 25, 50, and 75, and here 200, 600, 800, and 1000 watt per meter square. And by fitting, then we were able to determine how each parameter will evolve with temperature, or with the irradiance by fixing temperature, or with the temperature by fixing the irradiance. And from this analysis, we were able to come up with this unified model that gives you any of the 5 properties here, how it will shift as a function of both temperature and irradiance. This is a very fully coupled model. And this is actually the first time that this type of modeling has been used in this area here. Now, if we look at the comparison between our proposed model and the Soto method, we are comparing here the Soto method to our model. As you can see, either for varying G and keeping the temperature constant, or varying temperature and keeping the G constant at 1000, in this case here 1000 watt per square meter, and here for temperature fixed at 25. So let's look at 25. I think the photocurrent, it seems to be following the same trend as the Soto, but not the others. They're completely different. But now if we keep the irradiance constant and vary temperature, again, the photocurrent is almost the same as the Soto, but the 4 other parameters are completely different. And let's just take these examples that are circled in red here. You can see that the Soto keeps the, in both cases, I mean, varying temperature, varying irradiance. The shunt temperature, the series temperature, sorry, is constant, okay, by the Soto, but it varies drastically by our model, which is physically sound, actually. Now, if we look at the comparison of our model to the Soto for the IV curves for different irradiances, okay, you can see here that our model predicts very well the IV curves for all ranges of irradiances. The Soto works well for 1000, close enough for 800, but it deviates completely for others because it was fit to these 2 only. In ours, by using a few, you fit, and then you can predict very well throughout all ranges of irradiance and all ranges of temperature. And now the last part, which is the structural modeling. In here, we are interested in estimating the lifespan of the PV panel. Of course, the loads that are used for this are various. The wind, for example, mechanical load, wind, snow, and so on.
Here's the sound.
It stopped.
Yes, it stopped.
Yeah. Yusuf, do you have an idea why?
Yusuf is not with us. Sorry for this.
Yeah, I don't know what happened. Well, I can, yeah. Yusuf, is Yusuf listening or not? Yusuf, do you hear? Can you solve the problem from your side, Yusuf?
Yeah, I can hear it well.
Yusuf?
Few seconds, we are solving the problem.
Okay, thank you. Thank you for waiting. Yeah.
For others, because it was fit. Hello, everybody. Different irradiances model and the Soto method. We are comparing here the Soto method to our model. As you can see, by lifespan, of the PV panel. Of course, the loads that are used for this are various. The wind, for example, mechanical load, wind, snow, and weight. The thermal load is extremely important, and actually we're going to focus in our work on thermal load. Okay, there are also radiation loads, which also degrades the UV, and there are chemical loads that just add moisture and heat speed up corrosion. So we are not considering corrosion or radiation degradation or mechanical load degradation. We are considering only thermal. Okay. By the way, we are interested in looking into one part of the PV panel that would fail. If you look at this chart here, you can see that most of the failure comes either from corrosion or from the breakage of the copper interconnect, which is 41% corrosion. So we are focusing here on the interconnect. So we are going to see how the failure can come from the interconnect. And you can see on this small picture here, the interconnect in the red between the cells, green cells, okay? So for this, we one can use a fully three-dimensional finite element, which is very expensive actually computationally, but we reduce this by looking into a method that we proposed recently, and that is called an approach that is based on two steps: 2D global simulations and 3D fully 3D simulations once we know where the higher stresses are. So let's go back to here. We used one string only rather than the entire panel, and we simulated this one string for 2D simulations, and from that we were able to see where the maximum stresses or maximum deflection actually occur. If you look at here is the interconnect between two cells, okay, and it does occur in this central here part, which is not surprising. Okay, so we know that the higher stresses or deformation are here, so we focused on this and we used 3D finite element simulations to calculate stresses and strains and so on, as you can see from this three-dimensional finite element mesh. For this, we need to define the constitutive laws for each of the elements of the PV panel. So obviously, the silicon was taken as linearly elastic, the glass as well. The CTEs of silicon is varies with temperature. As you can see, the values, the variation, we included it. The CTEs of the copper vary also temperature, and we did include this variation. And the EVA, which is a polymer, it's a viscoelastic material, and we took also the effect of temperature on this, and we adopted a viscoelastic model. For the copper interconnect, which is of great interest to us here to see how it fails, we took an elastic plastic model. So we have elasticity, then we get to the yield or beginning plasticity, and the material plastifies with hardening, and this is kinematic hardening, which is widely used and a must actually for analyzing fatigue. Okay, now the other thing we did is since we are focusing on this copper interconnect and central part, we wanted to know what are the initial conditions actually that comes from the processing or the making of the panel, and that is the lamination process. So lamination process consists globally of heating and then cooling to 150 degrees and then cooling. But when you cool, well, you have developed thermal stresses, and you can see that the thermal stresses are really high, 158 megapascals, whereas the yield of the copper, the yield point is only 90. It is written here, I think. It's only 94 megapascal. It's not written here, but anyway, that means that during the lamination process, the interconnect had, especially in this central part here, did undergo plastic deformation. Now, in order to simulate fatigue, because we have cyclic loading, every day you heat and then at night you cool and so on. This is cyclic load. So if you apply a cyclic loading, which in terms of temperature, well, you will get a plastic deformation, which is also cyclic, and the amplitude of the cycle is given by delta epsilon plastic. And this amplitude of the plastic deformation is related to the number of cycles to failure by using a model called Coffin-Manson model for fatigue and fatigue for ductile materials. Okay, this fatigue model involves two parameters, which are the fatigue ductility and fatigue ductility exponent, which we got from the literature. They were measured experimentally by different authors for copper. And now, how to simulate this cyclic thermal loading? Well, we chose one day, and then we repeated it many times to have a cyclic loading. So day, night, and so on. And you can see it from here. This is, we choose one day in June, but we also choose one day in January. So two extreme cases in Doha. And this is what we measure in terms of, or calculate also in terms of temperature during this day of the panel in the cells. And this is for January, this is for June. And these are the stresses during the same day. The stress, how it goes, it does relax because temperature increases, then it decreases and so on. That's why you see this relaxation, because of temperature increase. And the same thing here for this other day, okay, which is in January. Again, you see the evolution of stress for the same day. What we did, we took this situation and we repeated it 25 times, okay? And then we measured the, so 25 days, in fact. So we measured the plastic deformation, and as you can see, it is cyclic, and the amplitude becomes smaller and stabilizes. And it is when established in fatigue modeling that you have to go beyond 20 to at least to 20 cycles to stabilize the amplitude of plastic strain to use the fatigue model that I showed before. And it stabilizes after, in our case, even before 20 days or 20 cycles. So now by using that model, as you can see from here in this table, if you can concentrate here, the fatigue cycles, the number of fatigues is given by 7,904 for July, I think they are actually mixed up here. This is for January, 4,070, and this should be for June, 7,000. But if you convert this into years, so this is wrong. This is the wrong way. Okay, this should be June and this should be January. But if you convert to years, this is correct. 21 years for January and 11 years only for June. And if you compare to the manufacturer, actually lifetime given by the manufacturer is 25 years PV panels, which are based on silicon or polysilicon, where here if you take the average between the two is only 16. So it is not surprising. We are in a desert area, the harsh conditions in terms of temperatures, and that's why we found less in terms of lifetime. And this is very important for designers to know about this, designers of PV panels. So now, in conclusion, so we have developed a radiation plus optical model in a unified way and simple. We have also developed a thermal model or improved thermal model, one-dimensional, two-dimensional, an electrical model, and we proposed a novel concept for shift factors to capture the effect of temperature and radiance on the parameters of one diode model. And we have developed a structural model based on 2D global modeling and then 3D local modeling to predict the lifespan of PV panels, and we found that it is much less than the 25 years given by manufacturer when you are in areas like in Qatar or any desert, any equivalent desert areas. So overall, we have developed unified sample approaches. We increased accuracy of the prediction of the modeling, and we also reduced drastically the computational time. And with this, I would like to thank you, and I'll be ready to any questions from the audience. Thanks a lot.
Okay, thank you very much, Professor Ahzi.
Yeah, can I just say something, Professor?
Yeah.
There was I got mixed up in the last table. I was saying that the number of cycles was wrong. No, it's correct. Everything is correct on that table. So I just got mixed up by reading June and July and so on. So 7,000 or more than 7,000 for January. That's the number of days, in fact, and that's what gives us 21 years. and then 4,000. That's what gives us the 11 years. So the table is correct. I was just mixed up.
Okay. Okay, thank you very much, Professor Ahzi. And now we will take time for some discussion with the previous presentation and the last one, obviously. And if there is some question, please, the floor is for all of us. Thank you very much. We have some, maybe some question. If you have some question, please, you can send a message and or you can take the microphone directly. In waiting and go.
Please see your question and answer in the bottom of your screen. There are some questions already posted.
Yeah, okay. I'm going to try to read all of them. I start at my question to Prof. There is a question to Prof. Saad Makhlif. The revolution of power electronics using in the renewable energy is the micro power inverter and especially the solar micro inverter. Also, it is important to integrate the digital smart technology in the PV system. What is the best to integrate an IoT or blockchain technology? This is a question from Boaziz. I don't know if he's a man or a woman. There is another question from Abdul Ilam Hamdi. Professor Saad Makhlif, thank you for your presentation. I wonder if machine learning can compensate efficiency problem or of electronics, equipment, inverters, and human behavior, saving energy, or it's depend on it. Thanks. I don't know how you want to process. Can you take these questions and we go further, or I read all the questions?
Yeah, I can answer these questions, you know, I can answer this.
Yeah, you can.
Yeah, okay.
Yeah.
So for the first question is about the use of microinverters and especially the solar microinverters. It's also important to integrate digital smart technology. Yes, I agree. Actually, the inverters nowadays are becoming more smarter, not only to convert from one form to another form, but actually it's used to communicate with each other. The inverters do the communication, do sending data, sending informations. So there are many, what I call technologies that can be used. IoT is one of them. Actually, it's because most of the inverters now, they have a port, which is either they can operate on Wi-Fi and also an internet port, which you can send the data. So I totally agree. Most of, not only the inverters actually for PV systems, but also the wind turbines, any renewable energy systems now, we have a power generated, plus we have also the data that we use to analyze. Okay, the second question is about wait a second question.
Abdul Ilam Hamdi. I wonder if machine learning can compensate efficiency problem or electronic equipment.
Yeah, the machine learning, maybe it depends on where you want to apply machine learning, because machine learning is just a tool. And this tool can be used, we use machine learning, for example, for prediction of power, for PV systems, for wind turbines. We use machine learning to predict what will be the amount of power that can be generated from photovoltaic systems, for example, tomorrow, or what will be the amount of power that can be generated from wind turbines. But as all the AI and all the machine learnings, data information, data analysis, all of them are very important actually in modern renewable energy systems. Because as I said just now, it's not only the power that is important, but also the data that comes with this power. We want to know at any point of time, what will be the power that generated by this inverter? What is the active and the reactive power that generated by these inverters? What is the amount of load that is connected to this microgrid, and so on and so forth. So there is what you call a very huge actually amount of informations that can be processed together with this data. Yeah.
You have another question?
There's another question.
How to find the small signal of microgrid?
Life assessments of power electronics. Improvement variable because solar energy examples important ensure the total amount of energy is spent during the manufacturing process. It's a similar approach for energy saving throughout the power electronics.
Regards Sidi Ibrahim. How to find the small signal of microgrid composed of RES, ESSS, and DEG, which method can be used for modeling these components, I think.
Professor Ali, do you want me to answer the question, the last question by Yusuf?
I don't know. It is for you, maybe, because
yeah.
Composed.
That's. I would like to answer the last question, which is from Yusuf. Okay, so is the life cycle assessment of the power electronics improvement favorable? Yes, it is, because the current, for example, if you look into the PV system, the warranty of the PV modules, the current warranty, which is around 25 years. Now, for the inverters, there are companies which offering up to 20 years warranty. Means actually the return of investments or life cycle assessments for these components are also favorable. Yeah, it's improving, and I think especially with the introduction of this silicon carbide and GaN devices, band GaN devices, the improvement of the lifespan of the power electronic devices is becoming, it's improved significantly, especially with integration of fault detection and fault tolerance devices within the inverters, especially with the introduction of multi-level inverters, which we use multi-level inverters for central and the large systems, which actually helps in improving the lifespan of these power stations.
Okay, thank you. Maybe we can move to two questions for Professor Ahzin. For Professor Ahzin, I have a question from Faisal Mehidi. Does this proposed model not significantly affect the electrical properties of the PV system? And maybe we can read another question.
I can answer. I read two questions. One was about the soiling, and one was about the parameters plus different shapes and so on. So for the first one, yes, soiling is neglected in what I presented today. However, it must be there, especially in desert conditions that I mentioned from the beginning. Soiling is an important factor, and it will contribute to degrade actually or reduce the efficiency. So it is not included in the model as I presented it today. However, we are doing some work in Doha, and that was part of that work was presented last year at IRSEC 2019 by Nicola Bart, who is one of my co-authors. And so he's collecting information about dust effect on the electrical yield and so on. And we have some ideas now that to include this into our modeling, but we have not done it yet completely. So yes, it is possible to do it, and we must do it for sure. And we looked at also, because we have some cleaning scenarios in Doha within this outdoor testing facility. There are some panels that are not cleaned at all. There are ones that are cleaned every week or every 2 weeks, just to see what is the best scenario. So based on that, we're gonna certainly include the dusting effect in the future in our modeling. And it is extremely important to have a better prediction and to take account of the full extent of the environment in Doha and other places, obviously. Second question was about the different shapes and so on. Yes, we can include different shapes. What I showed here was simple, especially if you look at the interconnect, we use one of the oldest designs. So there are some new designs, and we're looking into checking the fatigue analysis for new design of these copper interconnect. And the design will certainly affect the fatigue behavior. Mechanical behavior depends on how you apply the load and how what are the defects that you may have in the material, and how the material is designed somehow in terms of the shapes and so. Yes, so the model can be extended. There is not much to be done, except that we have to use a CAD model that represents correctly the shapes. The second is the parameters. Well, if you look at what we have, I will not call, I think the number of parameters is very limited. Okay, this is very few. I mean, I know I did not count them, but one that is really a parameter is how the beta parameters in the degradation of efficiency as a function of temperature. We took linear. We took a beta that is 0.5% per degree Celsius. Well, it all depends on the panels. For polysilicon, this is what everybody is reporting in literature. So that could be considered as a parameter. The others, if you look at optical modeling, we have two parameters, but these are material properties that could be measured. So I make difference between parameters and material properties. So most of the parameters we have are material properties. We have maybe 2 or 3 parameters that cannot be measured, okay? Or not easily measured. So the number of parameters, or we don't have much of fitting parameter, except maybe for the beta that I mentioned for the degradation of the efficiency. So, and again, it could be also measured. You have to, there are a lot of things reported in literature. So we don't have fitting parameters if you want, okay? All of these parameters that I presented are measured or measurable parameters.
Okay, there are some questions, some other questions. Sorry, I have one comment, and for all of you, when speaking about microgrid, it is not time to speak about local grid with only DC component, because only this work deals with conversion of DC current to AC current, and this is a huge consumption, as Professor Michalef says. Maybe we can work and think about only DC components, and this can be a huge revolution in the energy consumption. What do you think about this, Professor, all of you? Maybe Professor Guerrero or
Yes.
Sad?
Yeah, I think that there's a little bit confusion about the AC and DC, because also someone asked in the chat, also someone asked about DC and AC efficiency, and this of course change from case to case. You know, we had a study looking at how efficient will be if we convert our homes to DC. And we made a special case study in Denmark. We saw that if you have solar panels and battery system, maybe you could reach maximum 10% if you change to DC. However, if you still have to exchange some power with the grid, so you don't have energy storage as solar panels, efficiency could even drop 10% minus, because you will need a big rectifier in the input of your house. So you have to consider which is the different, the different applications. You cannot generalize and say DC is good because I think it's good. You have to really look on the different cases.
Yeah.
That's my viewpoint after working on many projects on DC microgrid. Yeah.
Okay.
Thank you.
Professor Michalef, maybe you have something to add?
Yeah, I think I agree. I tend to agree that actually the future, maybe it's for DC. If not DC, maybe it's hybrid, means we have a DC and AC grids working together, So because if you look into even very small DC microgrid house, for example, we can see most of our appliances at home are DC based. You see induction cooking, fridge, TV, air conditioning, everything's almost is a DC. So that's why there is a lot of studies actually of moving towards DC and trying to harmonize the relationship between AC and DC, And that's actually will introduce a lot of saving, a lot of power reductions and improvement in efficiency. Yeah.
Okay. Maybe there are some questions or some comments. Yusuf? Maybe your micro is not activated.
Is it for me?
There are other questions.
I don't know.
On the question
On the
and
chat.
answer.
For Professor Said, which model was implemented in MATLAB Simulink?
The three first models, the coupling between optical, thermal, and electrical. They were all. That's where we put MATLAB. Now the structural, it's all finite element. However, the input comes from the MATLAB, the input of temperature and temperature distribution. Okay, so the combination of the coupling of optical, thermal, and electrical is MATLAB. Yes, 1D and then 2D. We don't have 3D in that, just 1D and 2D. And it all depends on the applications. But in fact, the input from the 2D in terms of temperature distribution, because we are considering as load at the end, only temperature load. We did not consider other things. But it could be, I mean, the weight, also the weight that comes now, or all the dust also, dust can put additional load that's actually on the panel. So yeah, that's how we couple things.
Okay, we have another question. It is possible to apply optimization method to improve models, for example, genetic algorithm or PSO?
Yes, and let me maybe correct something that I answered earlier for parameters. The most important parameters, actually, I forgot to mention that, is the in electrical model, we have this one diode and it has 5 parameters. Those are parameters, yes. So, and that's we use usually optimization techniques, and neural networks can be used. So those are the most important parameters. And again, and we can call them fitting parameters somehow, because we calculate them by fitting to the IV curves from the manufacturer. So so to complete my previous answer to the parameters, yes, we have 5 parameters that are not measurable. Correct, to be correct. And all the rest are measurable. And those 5 parameters are from the electrical model, and any optimization technique that can help get that can be used, including neural networks.
I have a question.
Panelists can ask questions.
Yeah.
Such all panelists involved in this session are invited to ask questions. Panelists can ask question directly with voice.
Yeah.
Professor Baghdadi has a question.
He can activate his micro if he has a question.
Professor Baghdadi.
Good morning, everybody. Good morning, my friends, my colleagues, everybody. I am sorry I didn't have time to attend this session at the beginning. I just joined the meeting now. So I would like just to ask my friend and colleague Professor Ahzi about the Solin phenomenon. I would like to ask him whether at Doha platform for research and innovation, is there some news, some new output from your research? I mean in Morocco, especially in Rabat, we have performed some experiment and some research on this topic, and we are now trying to test the possibility to export the dew for cleaning solar panels, photovoltaic solar panels. So we are now trying to do this. We are trying to test what is the possibility, what is the potential of dew to clean the front surface of PV panels. And I don't know whether you did some similar tests at your platform in Doha. Is there some news on this topic? We would like just to share our experiments, our both experiments and our both exercises on this topic, please.
Yeah, we have plenty of new results, and actually one of my co-authors, Nicola Bart, is the one in charge of collecting all the data from the outdoor testing facility, and by analyzing the data several months ago, we came up with also a cleaning schedule, and I tried to find out the paper that he published. Maybe in IRSEC 2019, I'm not sure if we published that in or maybe somewhere else, and I can share that with you. So there is also, so based on those results, yeah, we came up also with a cleaning schedule, okay, by doing also some economic studies and so on, and optimizing based on total cost. So we do have plenty of results. However, not all are published, and the reason is our current executive director and is working with some industries that are bringing their panels to our outdoor testing facility, and they are really not into publishing quickly these things. So we have to get some authorization in advance and so on, but some are published, and I can share anything published. I can share that with you. Please send me an email, and my email has changed. This is just use azi@unistra, University of Strasbourg, azi@unistra.fr, and which is in fact written in my presentation if you saw it from the beginning. Use that email, and I will share with you whatever we have. Okay. The other thing is we can also work on your data. This is really a good idea. Why not collaborate and use your data for soiling, and you combine it with our modeling, and so it will be great. And by the way, I'm moving from Kiri. I'm no longer with Kiri, so I'm not bound to work only on the data from Kiri. So I can work with others. And I'm going to Texas A&M as visiting professor here in Doha. They have a campus, Texas A&M. So yeah, we can also collaborate and use your data from Morocco. That will be really nice.
Okay. With pleasure. Okay. With pleasure. Thank you, okay. Professor Ahzi. I will send you also some copies of our recent papers. Okay. We have recently published on this topic.
Okay.
Thank you.
That will be great. Thank
Professor,
you.
Professor Ali Ahitur. We
Yes.
can give a floor to some attendees who you can ask question using voice. There are someone, Mohammed Louzazni.
Okay, thank you. The floor is yours,
yes.
Professor.
Mohammed Louzazni.
Yes.
Please, your question.
Thank you. My question is for Professor Said Ahzi. It's only about the RS, the series resistance of solar cell. I want to know why you take it RS equal RS reference and not in function of temperature and radiance. Because in the last publication of Giovanni Spaniolo, he used it in function of the temperature and irradiance. And I'm also working in this topic. All the literature use this resistance like a constant, but actually is not constant. Can you please tell me why you use it RS equal RS reference? Thank you.
No. Yeah, no. Okay. I think this is you. If you go back to the presentation, that's De Soto. De Soto took it as constant, and we did not. So it is not constant. It depends on both temperature and irradiance. And I can, if you send me an email, I can share with you the paper in which we came up with this unified model to shift all the 5 parameters of the one diode model as function of both irradiance and temperature. So it is not constant in our model, but maybe the confusion came from the fact that I showed that RS series is constant by De Soto, not ours. It was just to compare to De Soto proposed shifty relationships.
Dr. Rahitub, there's another question. I think another participant, Fuad Dihlo, asked to want to ask question.
Yes.
Do you hear me?
Yes.
Yes.
Good day, either morning or evening. I am Professor Dihlo from the United Nations University, associate member, but actually I'm at home in Morocco. My question comment will take maybe less than 100 seconds. So I'm asking and putting question to everybody. Is it not time now to be more, I'm sorry to say, more honest and follow what big countries are doing? I'm talking about nuclear. Nuclear is a renewable energy, maybe, but with a very long time. Everybody knows that. But also nuclear is a non-carbon energy. So if we see China, if we see Japan, if we see, for example, ITER, which is fusion nuclear, a lot of people are putting a lot of money for the future of humanity, because nuclear, there is no waste, and also almost with no money, $0 for nuclear. But also with SMR, small modular reactors, can be done for next generations. So maybe I'm not waiting for a quick answer now, but I would like to make everybody thinking about the nuclear. But if somebody in the panel can give a small comment, I would be very happy. Good day. Thanks.
Thank you, Professor Fuad Dihlo, and you are welcome in your country and with us. Maybe if there are some comments on this question.
I have some comment.
Yeah,
thanks. I also want to be very honest, and we have to be very honest. That's necessary. In Denmark, we have right now more than 50% of the electricity production coming from renewables. We never had nuclear, and I don't think that nuclear will be in the agenda. Otherwise, who's proposing nuclears in Denmark, it will be politically defeated. So we demonstrate that it's possible to run in high levels of renewable, and we have the target to go 100% in 2050. So right now we are growing from 60% and will be 70, 80, 90, and we will reach the 100. We are doing the same with other countries, helping to shut down the nuclear, for instance, with Taiwan, in which they want to shut down the nuclear plants, and they are planning to put offshore wind farms in the level of 10 gigawatt in the next few years. So there is a first stage in which Taiwan will grow 5 gigawatt in the next 3 years, and the next 6-7 years later will grow to 10 gigawatt of offshore wind. They will shut down all the nuclear plants, and they are mixing this with hydro power plants that they have inside the island. So we really believe that the way to go is to shut down the nuclear plants and to grow on offshore wind farms. For instance, not only in Denmark, because we are a little bit special, right? But all Europe is right now thinking that the energy transition is going to be to put a number of around between 300 and 400 gigawatt offshore wind farms in our seas, and then combining this with energy storage. So we are taking this very seriously. Germany also shut down the nuclear plants. And if you take a look right now also what you mentioned about Japan, if you look at 9 years ago, the disaster that I present in my presentation, when it was the tsunami produced a big problem with nuclear plant, and still there are people affected by that. So is it the way that we want to go? I think that in Europe, we have very clear that the trend is to go as higher as possible with renewable energy. And we cannot accept that nuclear is renewable. It's basically not renewable. It's a problem, and I think that we have to defeat it. And we have to do it together, not only universities, but also companies like we have here in Denmark, Vestas, CIP, Ørsted, and many other organizations that are pushing for going to this. Yeah, that's all I wanted to say.
I think
Okay,
Professor Ali, it's time.
It is time, yes,
yeah.
yes, it is time. Thank you for this comments, and thank you for all participants. Now it is time to move to the short presentation of a researcher. Please, by message.
Before going to the next presentations, I don't see if Professor Saad Mutahar is there.
Yes, yes.
Yes,
Saad
Saad Mutahar. Normally, for this session, he proposed selected authors will be invited to prepare the full version of their paper to be considered in the Journal of Sustainability, MDPI journal, the special issue. And Dr. Saad Mutahar is the guest editor. You can go to the website to see details how to submit your paper to this good papers to be considered in this special issue.
Okay. Okay, maybe we can move to
you have about eight presentations.
Yes, of 5 minutes. Maybe we can start?
Yes, you can present the author before start.
Yeah, okay, we can start by Fatim Zahra Hasnawi, Idrisi Khalil, about Eliadora 2 projects ID. Yeah. The floor is, you have 5 minutes for your presentation, please.
Good day, everyone. We are the Minraba Solar Team, a group of 12 Moroccan engineering students from the National School of Mines of Rabat, whose mission is to promote solar energy by making eco-friendly solar-powered cars and honorably represent Morocco in the most prestigious competitions in the world, such as the Moroccan Solar Race Challenge in Morocco and the United Solar Challenge in Egypt. Ever since its creation in 2014, our team managed to design and build 4 solar-powered cars, Eliadora 2, the one in the picture, which is our latest invention and whose name means a gift from the sun, had seen the light in 2019. Regarding our solar panels, we are using SunPower's 3rd generation Maxon solar cells owing to their strength, durability, and efficiency. The following figure is a technical drawing of Eliadora 2 solar cells. The electrical characteristic and main reason of our choice could be summarized in the next table, which is primary efficiency. Our car was constructed following specific international competitions regulation, which requires, for example, approximately 4 square meters of solar panels, and each cell occupies 15.625 square millimeters, a total of 256 cells. The solar panels in our Eliadora 2 are placed as follows. Moving to our power tracking technique, we are using the MPPT Nano manufactured by Nomura code-type output 2337 volts, which is specially dedicated to solar race cars. And since the battery voltage varies, we wanted to choose the number of MPPT in series in order to make the solar panels charge our batteries regardless of their charge state. So we used 4 ones in series in each line, and since we got 2 lines in parallel, that makes 8 MPPTs in total. The table sums up the entire wiring system for the both lines. It shows which block is linked to which MPPT in which line and all the other information on the number of cells in each block. Our energy storage system was also designed to respond to the competition rules, which requires the installation of a safety system in case of failure and also fixes the weights of the battery cells and many more. Here's an extract from the technical regulations that kind of determines the total allowable cells mass in kilogram. As mentioned before, the weight is one of the biggest challenges, so we opted for technology that offers a maximum gravimetric energy density that lasts long and that provides a higher voltage. It is the lithium-ion batteries. The weight is determined in our case for 20 kilogram. However, its main disadvantage is the need for a proper management system to guarantee safety, otherwise the unmanaged cells can catch fire and explode. And here steps in the battery management system. Taking this into consideration, performance, capacity, the protection, and ability to manage the high power circuits based on the battery need, we are using the Orion 2 size BMS 36. The box for assembly is made of slatted wood and the plates on the left and right are made of the red wood to be able to withstand 20-gram acceleration. And here is Eliadura 2's main circuit, and this is our battery pack. Moving on to our mechanic aspects, our car's chassis was designed in order to minimize the energy consumed due to mechanic frictions. So we built it using 1661 aluminum, which is characterized by its rigidity and its low density. Its weight is 17 kilogram. Our suspension system is made entirely of aluminum 7074 so that we could benefit from its lightweight characteristic. And last but not least, the shell, which is often mistaken for a chip shell, was designed to significantly reduce the aerodynamic frictions and was made of carbon fibers to keep it as light as possible and of course as safe as possible from the regulations view. One of the main keys to win a race is to establish a good strategy. So our strategist's main mission is to analyze the speed of the solar car so that it could reach the finish line as soon as possible within the limits of the battery and actually give the driver the areas in which he could speed and others where he should slow down. The dashboard is important for the drivers as well, as it controls the panel of the solar car. It provides the driver with the necessary data on the speed, the power, the current, etc. The following sheet highlights the importance of optimizing the design in terms of the car speed and time saving. As for the telemetry, we are using ZoomLink, which is an embedded system used in military application due to its 10-mile range. Thank you.
Just a remark. Please, keep with us to ask questions also to all presenters. Thank you very much. Now we go to the next presentation.
Okay. Now the second presentation concerns the main factors affecting silicon solar cells. Cells performance in the hot desert climates. Younes Kahul, Labid Shekal Afari, à vous la parole.
Hello, my name is Younes Mohammed, PhD student from University Mansouri Constantine. I will be giving a short presentation on main factors affecting silicon solar cells performance in the hot desert climate. My presentation is structured as follows. First of all, the objective of the work, then the introduction, and I will focus on the challenges related to desert climate, finally conclusion. The main objective of the work is to understand the challenges related with operating silicon solar cells in hot desert climates, and the prediction of performance degradation and fatigue failure of standard photovoltaic panels under this climate. I will start by the introduction. These regions are recommended by one of the most suitable places in the world for the photovoltaic installation due to the high solar radiation levels and long exposure periods. On the other hand, desert climates are considered as harsh climates for their extreme conditions, which is characterized by a hot and dry climate, therefore pose a challenge for solar energy applications, particularly photovoltaic installations. In desert climates, photovoltaic cell modules are subjected to several challenges represented by various climatic and operational stresses, which can strongly affect their performance and efficiency as high temperature accompanied by high ultraviolet radiation, thermal cycling due to temperature change, and dust accumulation. The failure of PV modules was found to be dependent on operating conditions. In fact, extreme weather conditions play an important role in the performance and the reliability of the standard panels. Consequently, discoloration of PV module encapsulants accompanied by delamination above the cell and certain degree of corrosion are the predominant degradation modes in the desert environment. Accumulation of dust makes layers on the module surface that conduct to sun blocking, leading to panels soaring and even damage of PV module. Challenges related to desert climate. I will focus on two major challenges. Firstly, heat accompanied by high ultraviolet radiation. The major external parameters which influence the structural EVA integrity are temperature and ultraviolet radiation content from sunlight transmitted throughout the EVA encapsulant. Long-term exposure to the combined action of EVA radiation and temperature increase have sufficient energy to break chemical bonds in the main chain of the polymer and initiating invented reaction since the degradation process are temperature dependent. Moreover, polymeric bonds causing degradation to PV modules, promoting its discoloration, yellowing, or growing. Dust accumulation. Accumulation of dust on the front side of the PV module exposed in field prevents solar irradiation. It makes serious challenge for the panel's performance. This factor causes rapid performance degradation and a big drop in output power. The effect of soaring is to reduce the transmittance properties of the modules by decreasing solar irradiation falling on the solar PV cell's surface. Finally, conclusion. Hot desert climates create challenges for PV module performance and reliability. Heat accompanied by high ultraviolet radiation responsible for the physical change of the encapsulant EVA properties, highlighting by yellowing or browning, and accelerate the degradation process. Dust accumulation considered a serious challenge for the panel's performance, which drive to reduce the solar irradiation transmittance. The awareness about the environmental challenges at this hot desert climate can give an accurate prediction for lifetime, an approximate warranty period, and the performance of these panels before failure. Reference.
Thank you very much.
Thank you for your attention.
Thank you very much. Thank you very much. Yunus, sorry. And now we will move to the modeling and optimization of renewable energy system using artificial intelligence technique by Khadija Al-Misri, Samira Al-Shaba, Muhammad Ali Jalal, and Abdul Wahab Zarwal. The floor is yours. Can you stop this video, please?
You are skipping the presentation of Yusuf
Solar, no? Solar, sorry. Yes, we will speak about, sorry, Yusuf, sorry. Solar cell parameter identification using differential evolution. Sorry,
Today, I will be presenting to you the work that we've been doing this year at University Abd Malik Saadi as part of a master thesis, which is about the identification of solar cell parameters using differential evolution. Let's get started. So the importance of accurate solar cell modeling cannot be understated due to their wide range of uses and applications. The two most common models that are used for photovoltaic solar cells are the single and double diode models. The double diode model is precise but incorporates 7 parameters, which increases algorithm complexity. The single diode model, despite its simplicity, provides more than adequate precision in most cases. The goal here, in both cases, is to identify the parameter values that allow us to best fit the experimental data for a given cell or module. Let's talk very briefly about differential evolution. It's a relatively recent evolutionary optimization method. It has the familiar population initialization, mutation, and crossover techniques that you may recognize if you're familiar with evolutionary optimization methods. The diagram on the right here shows the mutation operation, which uses a differentiating scheme, which is where the name differential evolution comes from. So as part of the master thesis, we wrote an implementation of the method in the Python programming language in order to perform our calculations. In this specific example of a 36-cell polycrystalline module, we can see that differential evolution fits the experimental data very well. And the graph on the right here shows the deviation from experimental data through each iteration, which shows us that convergence occurs at around 50 iterations roughly. We were able to validate our code and compare with other implementations using similar techniques on the same solar modules and cells. This table compares the parameters and performance that was yielded by our code against similar techniques in literature. Each technique's deviation from actual experimental data is quantified by the root mean squared error here, which tells us that differential evolution is slightly more precise than the other techniques. So every evolutionary algorithm has a set of control parameters which affect its behavior and convergence. Two of the most important ones in differential evolution are the mutation factor F and the crossover rate CR. There are a few recommendations and guidelines in literature that generally lead to good results, but these are by no means universal, and one may need to build experience by resorting to trial and error. This is because there have been plenty of instances where the best results were obtained by parameters that do not fit these recommendations. A method that we propose to get around this issue is meta-optimization, meaning we'll use differential evolution on a higher order to optimize our standard differential evolution. This results in higher time complexity, but since we're only optimizing 2 parameters, the higher order search space dimensionality is not significant, which allows us to use a minimal number of iterations. So these are the convergence curves associated with a commercial solar cell with and without meta-optimization of differential evolution. The curve on the right is obtained using the recommended control parameters in literature, yet we can see clearly a significant improvement in terms of convergence speed using optimized control parameters. This is the same comparison, but in this case for the previously mentioned 36-cell polycrystalline module. Again, we see an improved convergence speed, in this case within 25 iterations. So we know that standard differential evolution is on par with, if not slightly superior to the other state-of-the-art techniques for the estimation of solar cell parameters, but we introduced a meta-optimization technique and successfully improved differential evolution, specifically in terms of convergence speed. We should note that the time penalty that is accrued in the initial execution that allows us to find the optimal control parameters is compensated for by the improved convergence that is yielded in subsequent runs, assuming the IV characteristics do not change drastically between runs, of course. In fact, in applications involving a significant number of runs, the time penalty can become practically negligible as it's only scheduled in the first run. Thank you.
Thank you very much.
Hello.
I'm sorry for
Today I
thank
will
you
be...
very much. I'm sorry for this announcement. Now we will move to the next one.
Hello. Today
modeling and optimization of renewable energy system using artificial intelligence technique. Khadija Al-Msli. Okay, the floor is yours.
Hi everyone, I'm Khadija Al-Msri, electrical engineer and PhD student in first year from University Simlaliya Qadi Iyad. Before starting my presentation, I would like to thank the organizers of this scientific event. So the subject of my presentation is modeling and optimization of renewable energy systems using artificial intelligence techniques. The outline of my talk is firstly introduction, problematic, results and discussion, conclusion and perspectives. As you know, renewable energy is energy that is collected from renewable resources which are naturally replenished on a human time scale such as sunlight, wind, rain, tides, waves, and geothermal heat. In order to increase the percentage of use of renewable energies in overconsumption, it is necessary to remove the difficulties associated with his employment. One of these difficulties is the optimization of the combination of several energies such as the sun, the wind, etc., and the use of storage devices to compensate for the intermittent nature of these energies. It is in this context that our PhD work takes place. Design and optimize multi-source systems to meet electricity needs. So the problematic of our work is that how to optimize the sizing of renewable energy systems, how to optimize the energy management of a microgrid. In phase of optimization, we will integrate artificial intelligence techniques, especially genetic algorithms. The environmental component is integrated with the objective of reducing the dependence on fossil fuels as well as greenhouse gas emission tight. Our main goal is to modeling and optimizing a microgrid composed mainly of PV system, wind turbines, storage systems, and loads. But in this presentation, we will present just a part of our results which we have attended. The first step in our work is to study the meteorological data of the state where we are going to install our system. We mainly need temperature data and irradiance data. At this level, we have developed a PV model which we use to analyze the influence of irradiance. So, for a constant values of temperature, we remark that the current and the power of PV system are proportional with solar irradiance. For influence of temperature, we can remark that the effect of their temperature decreases voltage and power. In this work, we present a general explanation of our research topic and the results of simulation of a PV model. This model calculates the current and power for a given voltage from solar irradiance and temperature values. Finally, the model development was used to show the effect of meteorological parameters, especially temperature and irradiance. The final objective is developing a general model to simulate the electrical behavior of the PV systems in a microgrid system application. In addition, we will integrate artificial intelligence techniques to optimize this type of system. And thank you so much for your attention.
Thank you. The floor now is to Hanan Yagoubi, the revolution of 3D printed solar panels.
Hello everybody, so I'm Hanan Yagoubi, PhD student in Laboratory of Applied Mechanics and Technologies at ENSA Taraba. So today my presentation is about the revolution of 3D printed solar panels. So today I will talk about creating solar panels thanks to 3D printing, how is it possible? And I will talk about future of 3D printed solar panels and how 3D printing could revolution the solar energy industry and the advantage of these 3D printed devices. For starters, for those not familiar with 3D printing, it's the ability to make three-dimensional solid objects from digital design specifications. In other words, 3D printing is really smart prints that create objects layer by layer through additive manufacturing or deposits of materials such as glass, silicon, plastic, resin, and ceramic by following a virtual blueprint or animated software. So first of all, what is the definition of additive manufacturing according to standard AFNOR? Is a set of processes allowing to manufacture layer by layer by addition of material, a physical object from a digital object. You may be asking why I'm so positive on its relationship to solar power. Well, that's easy right now. There is a huge lack of energy storage. Therefore, future production of solar cells must be more sustainable. This has me interested by the potential 3D printing can have on solar sector. So, creating solar panels thanks to 3D printing, how is it possible? So new 3D printed solar cell technology already exists. This technology could be a game changer for solar energy industry. Here are some examples of companies using 3D printing in order to create solar panels or researchers looking for the best options to develop good solar cells. So at the Commonwealth Scientific and Industrial Research Organization, they are using industrial 3D printers to print rows of solar cells. These Australian scientists succeeded in creating 8 sheets of solar cells that can be used on any surfaces such as window or building. These are functional and efficient solar panels. These solar cells are the largest ones and they are created with flexible, lightweight plastic. The scientists developed photovoltaic that they drop off on flexible plastic strip. This whole process includes gravel coating. Additive manufacturing helped them to produce an accurate system. So here we will see if 3D printed solar panels could be a low-cost solution towards energy crisis. So for example, in the University of Newcastle in Australia has involved a printed solar demonstration site, one of just 3 comparable sites in the world, to test its printed solar panel technology, which could provide cheaper, more convenient solar energy solution to Australian homes. Manufactured using standard printing press, the ultralight panels are produced by printing in advanced electronic laminated sheets, and the panels are so light that they can be attached to walls or roofs in large laminated sheets using simple Velcro strips, which would potentially make them far more convenient to install than conventional panels. So to conclude, the 3D printing could be the revolution in the solar energy industry. They are more efficient, less complex, and cheaper. 3D solar cells can also capture more sunlight than conventional PV models.
Thank you. The next presentation will be given by Yahya Zifri. It deals with the visual RGB and thermal diagnosis of PV plants through UAV photogrammetry best practices.
Hi, in this presentation, we're going to talk about best practices for photovoltaic plants diagnosis through RGB and thermal infrared UAV imagery. The presentation comprises a concise technical guide tackling material choice, image acquisition, and processing. We also present insights from our ongoing research activities regarding the addressed thematic. The PV global capacity has witnessed a remarkable increase during last years, taking the world's global to about 627 gigawatts. Almost half of this capacity is detained by China, the United States, and India, whereas the rest of the world shares the remaining portion. Due to manufacturing imperfections and environmental factors, PV modules are affected by various defects that induce degradations, electrical power losses, and safety risks. Nowadays, PV plants are deployed on increasingly large scales, which challenges the electrical-based inspection techniques, pushing towards the use of imagery-based inspections. However, manual on-field imagery is costly, time-consuming, and not practical. As a consequence, unmanned aerial vehicles have been implemented in this context as an alternative autonomous solution that saves time, costs, and human resources. The use of UAV can reduce up to 85% the time spent performing thermographic inspections in large-scale PV plants. So, we want to conduct a PV inspection using a UAV. The first question to answer is which material to choose. For the UAV choice, we have fixed and rotary wings models. The latter are the most suited thanks to their stability and maneuverability. The UAV has to be equipped with a GNSS and an IMU. The maximum takeoff mass has also to be taken into consideration. For the RGB camera, it has to be a high-resolution one that captures sharp and correctly exposed images. For the IR camera, specific ranges of the spectral response, the thermal sensitivity, and the resolution have to be taken into consideration. Additional requirements can be found in the reference below. The market also proposes cameras with dual sensors that can capture RGB and IR images simultaneously. After acquiring the necessary material, we should know now how to capture field data. The first step is mission planning. Here, information about the plan to inspect and the flight authorization have to be obtained. A prior material verification has also to be carried out. We start by the flight zone delimitation and mode selection. We determine the flight height, the takeoff and landing points, as well as the overlaps. For RGB imagery, we recommend an overlap of 70% and a GSD, which is the ground sampling distance of at least 2 centimeters per pixel. For the IR imagery, we recommend an overlap of 90% and a GSD of at least 5 centimeters per pixel. Specific conditions regarding the climatic environment and allowed tilt range as listed below have also to be fulfilled. To process images, we propose a digital photogrammetry workflow structured as follows. The first step is initial processing, where the internal and the external camera's parameters are calibrated. Next, there is the point cloud densification, where a 3D dense point cloud is computed. And the last step is the generation of the digital surface model, followed by the orthomosaic of the individual images. In order to detect defects, digital image processing, machine learning, and deep learning classifiers are implemented. We started our research activity in 2017, where we have conducted our first field experiments. Interesting results were obtained and published in the 5th IRSEC edition and the MDPI Drones Journal. In 2019, we have started the Smart Drone for PV project, where we're actually working on developing smart inspection solutions for PV plants. Our latest publication tackled automatic PV panels extraction using object-based image analysis and machine learning. We are conducting flights to collect field data from various PV sites. RGB plus thermal images are collected at the same time from modules in different configurations. Images are processed according to the photogrammetry workflow presented previously, and the processing results are exploited to develop algorithms that are based on digital image processing, machine learning, and deep learning for defect detection, localization, and classification. We'll be delighted to share with you in upcoming opportunities the latest results of our research. Thank you for following and stay safe.
Thank you very much. The next presentation will be done by Mustafa Dar. It concerns the performance degradation assessment of the 3 silicon PV technologies.
Hi everybody, I am Mustafa Adar, PhD from Sultan Moni Slimani University. In this presentation, entitled Performance Degradation Assessment of the 3 Silicon Photovoltaic Technology, we will study the rate of the degradation of 3 silicon photovoltaic technology installed in the rooftop of Sultan Moni Slimani University. In this presentation, an introduction and PV system description and PV performance metrics, then statistical methods to assess the degradation rate, results and discussion and conclusion well done. Our photovoltaic systems consist of 3 silicon technologies, monocrystalline, polycrystalline and amorphous crystalline, installed on the rooftop of the Faculty of Science and Technology in Beni Mellal city. The direct performance ratio is defined as the ratio of the array yield to the reference yield is chosen to study the performance degradation rate in this study. The statistical method used to calculate the degradation rate are the linear regression method. By applying this method, the annual rate degradation is determined as shown in equation 1. The second method is classical seasonal decomposition, which are used also to determine the annual degradation rate following the second equation. The third statistical method used is the Holt-Winter exponential smoothing method. Holt-Winter exponential smoothing adopts the general additive model as shown in third equation. Its elements are shown in equation 4 and 5 and 6. Linear least square fitting is used to quantify the observed decreasing trend of pair DC time series as previously described. The rate of performance degradation of monocrystalline silicon is around 0.57% per year. For the amorphous, the degradation reaches 0.46% per year. The polycrystalline marked the small value of degradation rate with a value equal to 0.15% per year. The result obtained from applying the Holt-Winter's algorithm to the performance time series of the 3 PV systems are depicted in these figures. The monocrystalline photovoltaic model performance degrade at rate of 0.41%, while the polycrystalline model degrade at a rate of 0.16% per year, whereas amorphous PV modules lost their performance by a rate of 0.42% per year. Applying linear regression of the time series trend components reveals that the amorphous system has experienced the highest degradation rate 1 with value closer to 0.51% per year, while the monocrystalline system shows a qualified annual performance degradation rate of 0.41% per year. The polycrystalline technology has shown a low annual rate of degradation of about 0.14% year over the same 5 years period. In order to compare the results obtained with those found in the published literature. This figure presents an effort to summarize the degradation rates given in the literature. According to this figure, the degradation rate of the PV module can be reaching 4% per year, but the median and the average degradation rates are only 0.5% per year and 0.7% per year, respectively. According to the usual statistical method, the degradation rate of the amorphous system has been confined between 0.42 and 0.55% per year, and the RD of the monocrystalline system is confined between 0.41% per year and 0.57% per year. For the polycrystalline is found to be between 0.14% per year and 0.16% per year. Thank you very much for your attention.
Thank you very much. And the last presentation will be given by Ahmed Azam. It concerns a new technique of fuzzy logic control applied to the PV SAPF system.
Hello, my name is Ahmed Azam J. In this video, I will give a short presentation on a new technique of fuzzy logic controller applied to the PV SAPF system. I have divided my talk into the following main areas. I'll begin by introduction, then I'll give a description of the PV SAPF combination. The third part deals with the proposed new fuzzy synchronous reference frame technique. Some simulation results are given in part 4. And finally, I will underline my presentation by some conclusion. The photovoltaic generator has become as prominent contender due to its ability to generate power with low environment impact. It can provide grid-connected systems where the need for energy storage devices is waived off. On the other hand, the widespread usage of nonlinear loads causes harmonics injection and results in several detrimental effects on power system components. So, a multifunctional PV SAPF can be used not only for electrical energy generation, but also for ancillary services as reactive power compensation and harmonic currents mitigation. So, the question is how to produce and inject this clean energy into the electricity grid while ensuring the quality of energy under varying climatic conditions, nonlinear and online varying load. So, the objective is to enhance harmonic currents extraction by using a new fuzzy synchronous reference frame technique to ensure high dynamic performances under solar and system parameter variations. Now, PV SAPF combination incorporates AC grid, nonlinear load, and PV SAPF. The nonlinear load consists of the thyristor bridge rectifier with ohmic inductive load. The PV SAPF incorporates PV generator, boost converter, and the 3-phases inverter-based SAPF. For the command, we use P&O algorithm for MPPT, a new fuzzy controller for harmonic extraction, and hysteresis current control for SAPF command. Power transit of the static system is divided into 3 modes. So, during the sunshining period, when the PV power is deficient for the load, the AC source provides the power required by the load. When the PV power is larger than the load's demand, the PV SAPF provides power to the nonlinear loads and injects the excess into the grid. During no sunlight period, the AC source supplies to the loads all of the request power. Now, let's look how to identify harmonics currents. Figure 1 gives the schematic diagram of the proposed new fuzzy synchronous reference frame technique. Conventional strategy uses the low-pass filter to extract the harmonic components of the load's currents. Nevertheless, this method gives a slow adaptation to sudden changes in the system parameters and systematically affects the performance of the PV-SAPF system. So, in order to overcome this type of problem, a novel harmonic current extraction technique is proposed. It includes one input, the ignition angle of the nonlinear loads, whereas the desired output is the fundamental current. For the simulation, the studied system is simulated under solar and system parameter variation. Clear that the proposed controller gives a fast and accurate harmonic extraction results in contrast to the classical method, and the overshoot is reduced as well as the response time by using the proposed method of control. In conclusion, a new fuzzy technique is developed in order to extract harmonic currents. It gives a fast and accurate extraction and ensures a good dynamic performance. That brings us to the end of my presentation. Thank you.
Thank you very much. Thank you. Now we have we take some questions for the presentation. I don't know if you have some questions, some direct question, or not. Are there the participants all here, please? Okay.
All participants are here.
Okay, thank you. Are there any question from the public? I have someone. Maybe I can start. For the first project, for the presentation deals with the car. There are some questions.
I see that attendees have raised his hand. I allow him to talk. Mohammed Louzasni.
Yes, thank you. I have a question for Yusuf Kharshouf. My question is why you are using differential evaluation? Because this algorithm has been used in 2010 by IRSEC and by Da Costa, and actually we are in 2020. For me, I used the Pfeiffer algorithm at 2018, and I compare with the recent published paper. I see he compare only with 2019 algorithm. Actually, there's many algorithms or many published paper. Why you don't compare with the new algorithm? And as you use the DA, you need to compare with Da Costa and IRSEC, and the last paper, the last year, using also the different evaluation for the Xing from China. Also, to conclude, your algorithm is the best, or you need to compare the RMSU with other algorithms, not use only with meta-heuristic or not with meta-heuristic. Also, my second question is for
one question, please. One question, please.
Okay. Okay.
One question.
Thank you. Thank you.
Thank you. Can you give the response, please?
I'm not sure if you can hear me.
Yeah.
Okay. So we've used a couple of different solar panels and solar cells to get the data with which to work with, and with which we're going to apply our differential evolution technique. And we've compared it in the thesis. We've compared it with plenty of other works, including the one that Mr. Mohammed cited, Ishaq and the paper from 2010, but mostly we compared with other papers using differential evolution and other similar techniques like particle swarm optimization, etc., that were published in 2018, 2019, etc. But the point of the work is to improve the method, because the techniques that we've seen using the method of differential evolution are pretty standard. They use some sort of modifications, but the modification that we introduced, the novelty that we introduced in the work was meta-optimization, because running differential evolution requires the knowledge of certain parameters like the crossover rate and the mutation factor. But we use differential evolution to find the optimal parameters in order to run differential evolution. So it's a two-layer kind of optimization. We optimize our optimization algorithm in order to find the best results. So that's the novelty of the work that we've done.
Okay. Okay, thank you. We have a question for Asma Azam from Faisal Mehdi. Can you give your question, please? Faisal Mehdi, you have a question?
Professor.
Yeah, I can read it. How are FLC learning calculated? Is this from experiments or what? This question is to Asma Azam.
It's for me?
It is for... yeah.
Okay, my question is for Asma Azam. I don't see any new technique for your fuzzy logic. What kind of or modification you use? For example, if you see the work of Kamal Tariq from Cadiz and Turkey with the Professor Luis Fernandez Ramirez, he used the fuzzy logic, explain fuzzy logic with the Lagrangian. This is the new technique, but I don't see any new technique in your. Can you please explain me your technique? Thank you.
Asma. Maybe she's not here. Asma Azam.
Can you hear me?
Yeah, yeah.
Okay. For my new technique, I take for the input the ignition angle of the thyristor bridge rectifier, and for the output, I take a fundamental current. This is the difference between the other techniques.
Okay. Are there any other questions? Maybe I can just have a remark concerning some presentation. It's only to discuss if for instance, if we take the modeling and optimization of renewable energy system using artificial intelligence, what we see is the application of genetic algorithm to make an estimation of the current and the power of the panels. But for the speaker, I just want to say that it is known that the power of the panel is dependent of the irradiation and the temperature. It is well known. Okay, what do you want to present today? Is just the beginning of some works, or why do you speak about artificial intelligence technique? Question is to Khadija Al-Misri, if she is here. Also, I have a remark in waiting from Khadija. I have a remark concerning the work for main factor affecting silicon solar cell performance in hot desert climate.
Turn on your mic, please, Khadija.
Khadija. Khadija is not here, maybe. For the paper 602, What are the specific factors you want to speak about? Because Solin is well known. I don't know what is the specific new camps of the paper. See, Yunus, you are here? Okay, see you, Zaz. Maybe you...
Yes. There is from a keynote speaker. If you have questions to participants.
Yeah.
Just a remark for project 1, 601. The holder of the solar car, is very good initiative. I will be glad if you can introduce some new techniques to optimize the orientation of solar panels in cars, to optimize the production of electricity in your vehicle. Do you have any idea how we can optimize the production of electricity? Yes.
Hello, sir.
601 Fatima Zahra Hasni or Khalid Idrisi Khalid.
Yes, I hope you could hear me.
Yes.
Well, first of all, I would like to properly introduce myself. My name is Hasnawi Fatam Zara, and thank you. And I would like to thank the organizing committee, the professors for their presentation and their interest and information provided during their researches. Regarding our solar panels, in fact, we've conducted many surveys to come up with the most efficient solar panels, the one that could provide us with the best energy quantity. And we come with using SunPower's third generation maximum solar cells, as mentioned in the previous presentations. Because, well, these solars are known for their because they are highly efficient, and they provide us with so many strength, especially for our cars to go as far as possible. I hope I could.
Thank you very much. I encourage you to introduce some. If there are something new, you can. I encourage you to put patents in some part of your project to be more visible and more competitive.
Yes, well, our team is still working on how to improve our car even more, either on the solar cells parts or on the energy stockage technique or the mechanic aspects of our car. We're still working on it, and we've actually learned so much from your presentation on how we can improve our solar consumption, especially in Eliadora 2.
Thank you very much.
Thank you. Thank you.
I think Miss Misri Khadija is online. She can answer.
Yes, I'm here. You can hear me?
Yes.
Yes.
Okay. Do you have a question for me? Hello, mister.
Yes, I was putting a question. Why do you speak about artificial intelligence technique in your presentation? You use the genetic algorithm, and it is well known that the power of the panels depends mainly on the irradiation and the temperature. Yes. What do you mean with the artificial intelligence technique?
So for us, we use the technical of intelligence artificial for in phase of modeling. Especially we use genetic algorithms to optimize the energy optimization, energy production for our system. So the meteorological data is the output of our model.
Okay, okay. Thank you.
Thank you.
Thank you.
Hello, sir. Can you hear me?
Mohammed Yunus.
Yeah, I'm here, sir.
Yes, yes.
Excuse me, it's problem of connection.
No problem. You have a comment?
Thank you. Yeah, about my presentation.
Yes.
You asked me what's the new or what's the perspective of my presentation. Yeah, sir. Actually, right now I'm the perspective of my works is to study the effects of heat accompanied by high ultraviolet radiation on the performance of silicon solar cells in the desert area. And I have taken out the data from the field of Algerian Sahara, specifically exactly in Adrar, which represents the real harsh environment which can affect the performance of silicon solar cells and lose their performance and reliability, and don't respect the warranty time, which is predicted of 20 years.
Okay, thank you.
You're welcome, sir.
Thank you. Are there any questions? See Yusuf?
I have question, Professor Haytouf.
أستاذ البغدادي تفضل.
Yes.
Allez-y, Professor البغدادي.
Yes,
Sorry.
I have just, I would like just to comment the answer of Miss Khadija Misri about your question, because you asked her about some details or some information about what she's doing in this implementation of artificial intelligence techniques for modeling and optimizing renewable energy systems. So I didn't understand what exactly she is doing now, and what about using these artificial intelligence techniques to understand well or to model the energy systems. I didn't understand what she is doing really. I would like to ask her some more answers or some more information about her research and her work.
Khadija, you are here?
Bonjour. Je peux répondre en français?
Please.
Yes, yes.
Okay.
No French, please. Only English, because there are many nationalities that can understand French. Please, only English.
If there is a problem for you to speak English, speak in French, and I'm going to try to make a translation.
D'accord.
The idea is she gives his idea, okay?
Donc, maintenant, je suis en début de mon travail. Je suis en première année de doctorat. Donc, notre idée concernant notre projet, c'est de faire la modélisation et l'optimisation des systèmes à énergie renouvelable. Donc, pour nous, l'intelligence artificielle et spécifiquement les algorithmes génétiques seront utilisés pour optimiser la combinaison de différents systèmes à énergie renouvelable. Par exemple, utiliser plusieurs systèmes, par exemple le PV, l'éolien, etc. Donc, on va avoir donc plusieurs variables donc pour optimiser la fonction objective qui est composée de plusieurs variables. C'est mieux d'utiliser les techniques d'intelligence artificielle parce que ils sauront donner des bons résultats par rapport aux autres techniques d'optimisation. Donc, c'est ça l'idée. Donc,
Okay. Okay, Khadija, okay.
vous avez compris.
Okay, thank you. I'm going just to make a translation of what Khadija says before before to continue the discussion. She said that she is in the beginning of his PhD project, and the main idea is to use the artificial intelligence, what she called artificial intelligence, to model the output of PV panels on the renewable resource, mainly for the moment, mainly by using algorithm genetic, and the procedure is to fix an objective function with several variables, and using this optimization technique, she can give the prediction of the renewable performances. That's all. C'est ça, Khadija. That's all.
Oui, c'est ça.
Voilà. And okay, now I'm going to continue the discussion on your. Those are algorithms for optimization. These are methods for optimization, and I'm not sure that we can call them artificial intelligence for the moment. I'm not sure.
Les algorithmes génétiques, c'est un type des techniques d'intelligence artificielle.
Yes, but okay. Donc, that is Professor Baghdadi. I think you have your response.
No, yes, but I am not really. I didn't understand well exactly, but because she's at the beginning of her PhD thesis, maybe in the next future we will receive some news about this new topic, and we will learn more about what she is doing.
Okay. It is clear. It is clear what she is doing. She's, for example, you have some. You have to put a panel in somewhere, and you have to choose between inclination. Sorry, it is difficult to define the main objective of, because what he tried to model theoretically what is the output of solar panel given a temperature, a position, and meteorological condition. No? C'est ça, Khadija?
Oui, monsieur.
It is that you try to use which parameter for your main objective function.
Donc, pour l'intelligence artificielle, nous aurons l'intégrer dans la phase de l'optimisation, c'est-à-dire, par exemple, après qu'on fait la modélisation de chaque système, dans la phase d'élaborer la stratégie de gestion de notre système qui est composé par plusieurs sources d'énergie et une charge. Donc, pour faire la gestion de notre source, on va intégrer les techniques d'intelligence artificielle, spécifiquement les algorithmes génétiques. Donc, on va se concentrer sur les algorithmes génétiques pour faire l'optimisation. Donc, c'est ça l'idée.
D'accord. She's saying that she will use the artificial intelligence, the gestion for the management of the multi-source energy system. Okay. Are there any questions for all the presentation, please? Because it is time, maybe. Professor Zas?
Time to conclude.
We will conclude, and I would like to thank harmfully all the professors with their plenary session, plenary conference. Professor Saïd Ahzi, Professor Ad Makhlif, and Professor Joseph Guerrero. I would like also to thank the students, the young students for their presentation, the auditorium, all the connected people for their availability, and also I would like to thank the organizer for this nice conference. Thank you very much to all of you, and have a good weekend for me.
Thank you very much, Professor Ali Ahitouf. Thank you very much for our participants. Thank you very much for Professor Baghdadi, for Professor Joseph Guerrero, for Professor Saad Makhlif, for Professor Saad Ahzi, and Professor Saad Motahar. And see you in a few minutes for the next session. Thank you very much. And hope to see you also in the next edition.
Thank you.
Okay. Bye-bye.
Bye.
Je ne sais pas quel est
Bonjour Daniel.
Bonjour.
Bonjour. Bonjour tout le monde. Et pourquoi il n'y a pas de son?
See Yusuf, Professor Zaz. So are you hearing me?
Yes, we can hear you.
Okay. So thank you very much. Ladies and gentlemen, good afternoon. My name is Mohammed Bali. I am Professor of Physics at the International University of Rabat. And this afternoon, I will share the session on Magnetocaloric refrigeration. So, you know, this topic is a topic that attracts a world with interest in this context characterized by energy resource scarcity, as well as, you know, the ecological issues. So, in this afternoon, I will try, me, Professor Daniel Touchard, and my colleague participating in the session to give you a broad idea on this emerging technology, going from materials to some practical aspects. I would like also particularly to welcome the undergraduate student from the International University of Rabat. So in this session, we will begin with the two keynote presentation, followed by discussion, and then after, we will continue our session with 7 presentations covering some aspect of magnetocaloric materials and magnetic refrigeration. So the first keynote speaker in this session is Professor Daniel Touchard from Institut Grenoble. We are really very asked. So Daniel Touchard of functional materials He is Emeritus Director of Research at CNRS, working at Nile Institute on different aspects of functional materials, going from magnetocalorics to the storage of hydrogen in solid-state metals. Daniel Fouchard has published in the field of materials, listen, about more or less 1,000 papers covering, several aspects. A little bit. Let's say more or less. Let's say about 1,000 papers covering different aspects, fundamental aspects and practical aspects of a wide variety of materials. He also contributed to more than 20 books and 14 patents. He is also founded and co-founded several companies, including the famous company Microgrid Energy, specializing in the hydrogen storage in metals. He also the founder of the company, I forgot the name. Can you remember me the second company, Daniel, you founded recently?
Yes, I can speak.
No, 1 minute. Okay, so he founded the Microgrid Energy, and the Holy allows a company specializing in materials and energy. In the 80s, Professor Daniel Fouchard was also associate professor in Oregon State University. Finally, Daniel Fouchard was also my PhD supervisor. I spent very, very nice years in Renewable, working on Magnetocaloric materials with him. And today, he will talk us about some practical and fundamental aspect of a very interesting family of intermetallics that belongs to the iron phosphorus type compound. So, Daniel, the floor is yours.
Thank you very much.
And again, thank you very much for accepting our invitation.
Okay. Now I can go to the presentation?
Yeah, of course.
Okay. So thank you very much for this very nice homage and introduction. So I like to thank the organizer of IRSEC to invite me. Last year, I have been very interested to visit you in Morocco, but I have some difficulty with my heart, but now it's okay. And so I like to deliver a lecture on magnetocaloric materials and today's, okay, you see?
Yes, we can see your presentation.
Okay, I will increase the size, okay. It's okay, Momo?
Yeah, it's okay. For me, it's fine.
Okay.
Please switch to full screen.
If I open the full screen, I cannot use the pointer. Okay.
No problem. Just to have more, can see better in full screen.
Can zoom a little bit.
Is it better?
This is okay.
No.
Okay. Zoom in.
110 maybe, it would be good.
Okay. This is okay?
Yes.
Okay, yeah.
Okay.
Yeah, that's fine. That's fine.
Okay, it's fine. So today I will review on the magnetocaloric properties of system, well-known system, iron 2p type of compound, with two examples. One is a more or less complicated materials, manganese, rhodium, ruthenium arsenide, with intricate fundamental magnetic properties. And the second one is in online of promising cooling application is based on manganese, iron, phosphate, silicium. And this work has been done in Grenoble for a part, in collaboration with Mohamed Bali, and so with colleagues in Poland, Tobola and Zar. So you have a picture of what we dispose in Grenoble, the synchrotron and a neutron factory, and also the Néel Institute. The building is there. Okay. So the history of magnetocaloric materials and application and efficiency. First, it was discovered 150 years ago but it was explained by Weiss and Picard some 50 years after. And at first, it was a fundamental interest and used only for adiabatic demagnetization at very low temperature. And in 1984, it was possible to activate this material because of strong magnets, neodymium iron boron, for example. And Geschneider and Pecharsky discovered a very giant magnetocaloric materials, gadolinium, silicon, germanium materials. Why we have interest in the magnetocaloric materials? We have interest in magnetocaloric properties and application for domestic and industrial refrigeration, air conditioning for building and car, for example, and cooling for integrated system, for example, your laptop. And the main advantage of this technology, this new technology, is very high efficiency, much more than gas compression refrigeration use actually. This leads to compact machine, silencious operation, and reversible. You can use this type of material to build heat pump, for example. But the very big interest now is there is no greenhouse gas in this technique. No freon, for example. So the material are now discovered and studied for application. And so first, effectively, to build a machine without greenhouse gas, very energetic system, and more silencious. So the principle is that one. You have a magnetic material, specific magnetic materials, and you can magnetize and demagnetize, for example, using a permanent magnet. And when this material is demagnetized, you have disorder of magnetic species. But when you magnetize, you order the material. And this specific material can be magnetized and demagnetized by using very low field, 1 Tesla, for example. And so when I go to the principle of entropy, the main part of entropy of this type of system is magnetic and lattice entropy. If, for example, you consider adiabatic work, you have to consider magnetic entropy and lattice entropy. So when you increase the magnetic entropy, so you demagnetize, so you cool down. And when you decrease the magnetic entropy, you order the material, you produce heat. So you have two sources, heat and a cool source. And it is exactly the same principle as the classical refrigeration by using gas compression and depression. So you have two sources, two hot points, one cold and one hot. And so during the cycle, you can produce heat and you can produce cold. So the magnetic material can be used for magnetic refrigeration or having MC effect, or material exhibiting transition between, for example, antiferromagnetic to paramagnetic or ferromagnetic to paramagnetic, ordering, disordering. Reference to ferromagnetic states. So in the literature, in the fact, we have two types of material, one with a smooth transition second order type of transition, and one type of magnetization disappeared abruptly for the first order magnetic materials. And if now we apply a magnetic field in this range of temperature, we can order or disorder, disorder the material. First order is a sharp phenomena, and we have a high variation of magnetic entropy. Second order is smooth. So you have a sharp, on a limited range of temperature, change of magnetic entropy, and for the second order, you have a wider but small range, small amplitude of magnetic entropy. So the sample formula are this one I discussed before, and the total entropy, if you consider adiabatic process, we neglect here a small part of electronic entropy, but we have main part magnetic and lattice entropy. So when you increase this one, you decrease this one in adiabatic process. And so the interesting formula to quantify the variation of entropy, magnetic or lattice entropy, is to consider the variation of temperature normalized by temperature and multiplied by specific heat. So the definition of magnetic EMC, effective magnetic, is like that. Delta T, the variation temperature you can receive, is proportional to temperature, variation of magnetic entropy normalized by specific heat. So we have a calorific capacity to measure, magnetic entropy to measure, and after you do this as MCA. So the magnetic measurement, so you done experimentally, you done effectively the access to MCA through this formula. This is integral, and practically we measure, for example, by using magnetic magnetization curve, we measure the change of magnetization versus field at a different temperature. And so we have this series of data, and of this data, we process to the numerical integration of this integral. And after that, we deduce, after some computation, we deduce the magnetocaloric effect of your material. Or because it is a calorimetric phenomena, we can also directly access by calorimetric measurement and to compute the change of adiabatic temperature. So the sample equipment we use in the lab are synthesis of materials, characterization of material by XRD, X-ray diffraction, and so measure the direct magnetocaloric effect by calorimetric measurement like that, or indirect by magnetization measurement like that. So we use this machine, and Mohamed know well this type of machine. So now I focus on the type of material we consider here, one of the best series of magnetocaloric materials. This is R, M prime, X phosphide. X is for phosphor, arsenic, silicon, germanium. And this material, ternary material, comprises two metal atoms. One, for example, is the coordination of one atom is tetrahedral one coordination by X atoms. The second one is coordination by 5 X element, phosphor, for example. And this series of material having a common staking polyhedra can crystallize in 3 types of structure: hexagonal, orthorhombic, or less dense tetragonal one. So we consider mainly this type of hexagonal of iron 2p hexagonal structure. So the atoms in this structure enter in a 3f and 3j structure. And this is a picture of this structure, but you can see directly that you have layers. This is hexagonal. So we have layers of 3f atoms, for example, brown, and 3 G atoms, for example, manganese in this 5 coordination states. So we have a layered material. And interestingly, in the iron 2p type of structure, the iron here in 3F has a very little small magnetic moment, but the iron in the intermediate layer has a very interesting magnetic material, high spin state. So you have low spin and high spin state. So we characterize, maybe 20, 25 years ago, we characterized the phase diagram between manganese iron phosphide and manganese iron arsenide. You see that we change only the S atom. And in the intermediate range of composition between orthorhombic, tetragonal, we have the hexagonal type of structure, type like iron 2p. And we discover that there is a ferromagnetic range of composition and antiferromagnetic and also paramagnetic distorted high temperature. And for example, if we examine by using neutron diffraction to characterize this material, we have this type of three-dimensional pattern, low temperature ferromagnetic. This is typically this type of pattern. Antiferromagnetic is this range of temperature. So we have an additional line characteristic of antiferromagnetic. And in the disordered state, we have effectively this last range of pattern with the Hodge diffusion process. And when you look at the change of the magnetic state, we see that we saw that the material, hexagonal material, is accompanied with a marked change in terms of magnetoelastic transition. For example, the ASL parameter for a given composition drop down, and parallelly at the transition, at this transition, the C-cell parameter increase a lot. And effectively, this is a magnetoelastic effect, characterize all the composition with this transition. And we have no magnetoelastic effect in this effect between antiferromagnetic and paramagnetic. Means that this is characteristic of the change of ferromagnetic to antiferromagnetic or disordered state. And the main interest is that when we refine the crystal structure of this material, that this transition is mainly accompanied by the change of a magnetic polarization on the iron side. The manganese side is not modified, not very much, but iron magnetism drop down. Okay, and the analysis of the magnetic structure is not more or less, it is more or less complicated. We have a helical system for the magnetic manganese magnetic side and oscillating for the iron. But what we saw that this is the drop down by Mossbauer spectroscopy analysis, the drop down of the polarization of the iron. And what we refine the value of the internal field of iron, we see that effectively at the transition, the magnetic moment of iron decrease abruptly, means that this is the main aspect of this transition. The tetrahedral site occupied by iron is very sensitive to the ferromagnetic or antiferromagnetic state. And parallel bond structure calculation of the parent compound, manganese iron arsenide, when we apply pressure, for example, we transform the tetragonal to the hexagonal one. And we see that for the bond structure calculation, you see that there is almost no change about the magnetic moment on manganese, but a marked decrease of the magnetic moment of iron. Means that in this system, the very sensitive site is a tetrahedral site. Okay. Okay, now we have measured effectively the magnetocaloric effect of this material, and so we have plotted isotherms in order to integrate the value of the change of entropy. And for different two compositions we analyzed, we saw that under a magnetic field, for example, 1 Tesla, we have a marked change in the magnetic entropy and corresponding to a marked change of the magnetocaloric effect. And in reference to the gadolinium, that is a reference compound in your science, this material is twice or 3 times better than gadolinium, the reference material. So we have a very marked change of magnetic entropy and also effectively a marked change of magnetocaloric effect. So I move now to the earth of my talk. I consider these materials and these materials, let me say, these materials is part of the phase diagram, the complex phase diagram between manganese ruthenium arsenide and manganese rhodium arsenide. And the manganese rhodium arsenide, let me say, I look for no, this one. Okay, I go back. I miss a slide. So in the manganese ruthenium arsenide and manganese rhodium arsenide system, a very complicated one, you see, in terms of magnetic property, we have a high temperature, Curie temperature for the pure manganese ruthenium arsenide, and a very complicated, complex magnetic structure in the range of manganese rhodium arsenide. And this is iron 2p type of materials. And so we have effectively the 2 layers type of stacking of magnetic entities. And manganese occupies 3G 5 coordinated atoms, and rhodium, the non-magnetic rhodium, and principal non-magnetic rhodium and ruthenium occupy the other side. So you have, in principle, magnetic and non-magnetic layers. So the result is that manganese ruthenium is a simple ferromagnetic material, okay, with a very high Curie temperature and manganese very highly polarized, high spin state. And I said that the manganese rhodium is very complex with a successive different antiferromantic, maybe antiferromantic structure. So in this type of structure, we have to consider that there are 3 types of frustration factors. First, I say that it is a stacking of layers, in principle, magnetic and non-magnetic layers. 2D stacking along the 001 direction, okay, high spin and low spin layer. In the structure, we have a triangular arrangement of the magnetic atoms, for example, and this is also a subject of frustration, for example, Jafet-Kittel type of frustration. And so we have to consider again that in the tetrahedral coordination, where we have situated ruthenium and rhodium, we have a short manganese, short metal arsenic bonds. And we have effectively a very low spin configuration in the tetrahedron. So these are details about the magnetic structure of this right side of the phase diagram, manganese ruthenium rhodium arsenide. And we have only in the intermediate range of temperature appearance of ferromagnetic ordering. And this ferromagnetic ordering has been characterized by magnetization measurement. So you see that different field versus temperature, we have this type of magnetization curve. And versus the strength of the field for given temperature, we have this type of distribution of magnetization curve. And so we have effectively metamagnetic state with a critical field. And this is the most sensitive metastable region. And so we have measured that the high spin manganese polarization corresponds to 3.5 Bohr magneton. But in this range of temperature, interestingly, rhodium is reversely polarized. Rhodium in principle non-magnetic, but the 4D band is polarized with anti-parallel to the resulting magnetic moment of manganese. So when we measure now versus temperature the different magnetization curve to extract the change of the magnetic entropy, we have this series of plots, and so we report the variation of magnetic entropy versus temperature, and so we see that we have two aspects. At a rather low field, we have a magnetization and also variation of entropy in this range of temperature. Then when we apply a larger field, we have also change, marked change of magnetic entropy. Means that this corresponds to the change of this antiferromagnetic to ferromagnetic range. And so in this range, we have two types of sensitive behavior. This is a ferrimagnetic material, but here we have a magnetic antiphase that it is very sensitive to the application of the field. Means that we have characterized, so we have characterized the ferrimagnetic range of temperature, and we have also characterized the change of magnetic entropy due to the low temperature regime. And if we apply the Clausius-Clapeyron equation, we have a good fit, in theoretical good fit, exactly the good correspondence between experimental and theoretical analysis. But this material can be said to have a reverse magnetocaloric effect, because when we apply, for example, magnetic field at low temperature, we stabilize a ferromagnetic. And in the other range at higher temperature, at a temperature above 200 Celsius, for example, when we apply a magnetic field, we increase the polarization, we reduce the magnetic entropy. This is a direct magnetization effect and direct magnetocaloric effect, and this reverse magnetocaloric effect. This material is very complicated, and so we observe two magnetocaloric effects. So when now we substitute rhodium by ruthenium, for example, this is close to the pure rhodium material, we have a negative magnetocaloric effect and positive magnetocaloric effect. And when we progressively substitute ruthenium by rhodium, we decrease the negative, and we also observe still the positive magnetocaloric effect up to this range of composition where we have only the ferromagnetic transformation to paramagnetic, and under magnetic field we can extract a positive contribution to magnetocaloric. So this is a positive effect, but the amplitude of this effect is very small compared to the negative one here. This is the main trend. And I like to go back to the effectiveness of the importance of the tetrahedral coordination of the rhodium. We change rhodium by ruthenium, we increase the number of external electrons by 1. Okay, so we have only 1 electron more. This is for S1. Okay, 1 4D electron, and we have this very important change of cell parameter. Means that there are there is a very important magnetoelastic effect accompanying the magnetic behavior. And this is effectively due to the specifically to the tetrahedral coordination. No much change about manganese occupying the pyramid, but ruthenium or rhodium occupies the tetrahedra. And we have determined asymmetry factor of tetrahedron. The asymmetry factor means that this distance between yellow arsenic and pink arsenic change, and the ratio between this distance, planar distance, and perpendicular to plane distance is very marked change of the asymmetry of the tetrahedron. And with the substitution rhodium by ruthenium, we have this criteria that change a lot. Okay, and this is also trend by DOS KKR CPA calculation, bond structure calculation, in the so-called ferromagnetic and antiferromagnetic state of, we estimate, for example, for this intermediate region, we have a change, market change in terms of distribution of state at Fermi level. Means that it is a very sensitive phenomenon accompanying the distortion of the tetrahedra and playing a marked role on the magnetic properties. And from this calculation, it has been determined that the change in terms of difference of electronic property, total electronic property, difference energy in between ferromagnetic and antiferromagnetic is very marked. Means that all this type of transition is mainly governed by the change of coordination of what happens when you put ruthenium, rhodium, one electron less or one electron more in this tetrahedra, or we change arsenic to phosphor, for example. Means that this site is very important in terms of stability and metastability of magnetism for this type of material. Okay, now I like to move to the final presentation. So I consider one more this material, and I will to conclude on the structural input of electronic configuration of the 3F tetrahedral site. For example, we have considered what you see before, the manganese, ruthenium, manganese, iron, phosphor, manganese, iron, arsenic system with hexagonal metastable magnetic system. And we have a parallel system, but with the orthorhombic structure when we consider manganese, phosphor, iron, and manganese, cobalt, phosphor. We have exactly similar phase diagram, magnetic phase diagram, but it is orthorhombic and this is hexagonal. So we have a metastability because the layer system of the FETP site, and this is a random 3D structure. And effectively, when we analyze the magnetocaloric property of this metastable type of structure, for example, in this range of composition, we have also very important magnetocaloric effect. And the change of magnetic entropy is quite 10 times less for this 3D system. Means that one of the very important parameters to consider is the difference of stacking of the magnetic species and very different entropy variation between 2D and 3D character. So now I consider a promising material for application, and we like to replace arsenic. That is not a very frequent material for chemistry, for example, for environment. And it has been possible to stabilize this type of hexagonal material when we substitute a part of phosphor by silicon, for example. And we have a more interesting material in terms of application. So to stabilize the magnetic structure in terms of iron 2p hexagonal system, we have to modulate the ratio manganese iron and phosphor silicium 2. And we can stabilize this series of materials. And so we have operated by doing that a new way of mass production by using high frequency melting. This is very interesting. So we can receive with different compositions this type of material with a small amount of impurity because it is not the ideal ratio between manganese and iron, but we have also get pure, very pure material with a different ratio manganese, iron, phosphor, silicon. So we have a lot of very interesting sample. And one more, I go to the magnetoelastic effect because once more, similarly to the manganese, iron, phosphor, arsenic material, here we have also this type of a change of cell parameter at the transition, ferromagnetic to paramagnetic transition. You see a drop down of the C cell parameter and the drop down of the S cell parameter and increase of the C cell parameter at the magnetic transition. But no magneto-volume effect. Interestingly, no magneto-volume effect means that this is characteristic of the deformation of the tetrahedral site. The tetrahedral site deformed, but there is almost no change in the volume. The same for another type of composition. We have also drop down, increase of the C cell parameter. And so we have also plot the asymmetry factor. So it means that we consider the deformation of the tetrahedral site containing mostly iron, for example, iron entering the tetrahedral site. And also characteristic of this type of transition, magnetoelastic, magnetocaloric, we have this type of change in the asymmetry factor. Last plot, very abrupt change as the transition. So we have measured effectively the interesting property in terms of application, magnetocaloric, and we have plot this type of isotherms for different compositions, for example. And you see that for some type of sample, we have a edge metamagnetic characteristic. And the result is that depending on the composition, it's very sensitive to the composition, we can get very interesting material with high change of magnetic entropy, middle and lower change of magnetic entropy. And for example, so we have to be careful about the repartition of the manganese and iron and phosphor and arsenic on the two type of sites. Okay, for example, for this type of composition, this 50-50 silicon phosphor, not exactly pure, but the magnetocaloric effect is very, very intense. So we have also determined the adiabatic temperature of this type of material. Adiabatic temperature means that this is a range of temperature when the magnetocaloric effect is very effective. And this is very interesting because it is close to room temperature and it is for some tenths of degree. So really these materials are ready for application. So I go to the conclusion. So we have studied this series of iron 2p materials with two types of magnetic element, manganese mainly, occupying the 5 coordination site, and iron in the sensitive tetrahedral site. So interestingly, is hexagonal magnetic type of structure is very interesting in terms of magnetocaloric because the layer aspect and metastability of ferromagnetic arrangement is accompanied by abrupt magnetoelastic effect, but no magneto-volume change at the transition. And the amplitude of the magnetocaloric effect is governed by the fact that we have two dimensions taking alternate along 001 with manganese layer and iron layer, for example. We have in plan frustration arrangement of the magnetic system, means that we have some metastability type of Yafet-Kittel type of arrangement. And we have a short, for example, iron to phosphor distance bond, leading to low spin state, and so very metastable magnetism of this layer of containing iron. And so the characteristic asymmetry factor give you good interest in the term of metastability. So the best choice of this material considered to occupy manganese anthracite mainly by iron and in the tetrahedral and manganese in the pyramidal. And compared to the non-free-end arsenic compound, this material can be applied. Thank you very much. It's okay.
Okay, so thank you very much, Daniel, for the nice presentations and for giving us, some key parameters behind the magnetic and magnetocaloric properties in this very interesting families of materials. So I will be the next speaker. I don't know, Daniel, if you can introduce, you can briefly introduce me.
Sorry.
So I am the next speaker. Can you briefly introduce me to the audience?
Okay.
Okay, just briefly.
I have to introduce the next speaker. Okay. The next speaker is very performant man, very intelligent man. And I work with him for 4 years, 5 years, maybe 4 years. And he made, Mohamed made a very high performance, very brilliant interest in many aspects of the science, not only to prepare the material, but to improve the knowledge of different type of magnetocaloric behavior, for example. And also he has demonstrated a very urgent interest in terms of machine. And he is the right man knowing the material, knowing the science and fundamental science of magnetocaloric material, and also the application in terms of machine. And very interesting progress have been made when he was, for example, in Canada, and discover also new materials and new application. So I let you to present the very modern aspect of magnetocaloric material.
Okay, so thank you very much, Daniel, for the nice presentation. Okay, so ladies and gentlemen, welcome to this session on magnetocaloric refrigeration. So the title of my presentation is quantum materials for not only hydrogen, but also helium storage. So at the beginning, I will to give you briefly some evidence about magnetocaloric effect, magnetic refrigeration, and some relevant advanced magnetocaloric materials. Then after, I will present some interesting result obtained with in relation with magnetism and magnetocaloric effect obtained in some very promising magnetocaloric compound that can be applied in cryogenic refrigerations. These materials particularly belong to two interesting family of oxide. The first one is sorry, I'm looking for the pointer. Okay. So the first one belongs to the raw earth manganate, and the second one to raw earth vanadate. Then I will finish by conclusions and perspectives. So as already introduced by Daniel, magnetic refrigeration has attracted a worldwide interest, particularly over the past 2 decades, of course, due to its higher efficient, eco-friendly character. So with magnetic refrigeration, we can also cover a wide range of application, going from heat pumps to cryogenic refrigeration, including, for example, the liquefaction of hydrogen and helium. So this technology is based on the Magnetocaloric effect. Donc Daniel already discussed the physics behind the Magnetocaloric effect. But what I can say is that this Magnetocaloric effect can be directly measured by a system of thermocouples, as you can see here, or indirectly determined from specific heat measurement and monetization data. However, due to the challenging character of calorimetric measurement, the monetization method is widely used to determine the Magnetocaloric effect, particularly in terms of the entropy change. So in this case, all what we need is to perform some magnetic isotherms around the ordering point of the materials, and after, the entropy change can be determined by numerically integrating his isotherm using the well-known Maxwell equation. There is an interesting point that I want to mention, is that the temperature of magnetocaloric materials make more efficient and serious magnetocaloric device. So fortunately, this magnetocaloric effect in a refrigeration process can be amplified by using some specific thermodynamic cycles called IMR cycles, active magnetic refrigeration cycle. And in a magnetocaloric device, each IMR cycle breaks up into 4 steps. The first one consists to maintain the material increasing its temperature. Then, after a high transfer fluid, for example, water, flows from one side to other side of the materials to evacuate heat. Then, after the material is demonetized, decreasing its temperatures, and finally, the same high transfer fluid that flows in the opposite directions to evacuate cooling energy. So after each IMR cycle, the temperature of the cold end decrease, and that of the hot end, increase to reach a steady state after a certain number of IMR cycles. This is the principle of magnetic refrigeration. So currently, the gadolinium metal is the material used in the vast majority of magnetic refrigerator. However, the gadolinium is very, very, very expensive. In addition, it oxides easily. Okay, so the utilization of gadolinium as a refrigerant in a wide range of application, a wide range of commercialization is out of questions. Okay, so to deal with these drawbacks, a huge effort was made by the magnetocaloric community, leading to major advances in the late 90s, particularly by Pisharsky and the late Carl Schneider. In fact, both scientists discovered a giant magnetocaloric effect in this family of compound germanium silicon based materials that can be used as a refrigerant in room temperature application. And as you can see here, a few years later, other interesting materials from both performance and economical point of view were reported, including this very interesting family just deeply discussed by Professor Daniel Fauchard. But today I will not talk about materials that can be considered for room temperature application, but I will more focus on materials for cryogenic temperature range that is also very important from practical point of view. Okay, so for more information about magnetic refrigeration as well as magnetocaloric materials for room temperature applications, I refer the interested reader to this review paper recently published in Applied Physics Reviews. Okay, So why materials for cryogenic application? In fact, this sort of materials are also highly important from a practical point of view, so they can be used in some specific application, such as the, for example, the liquefaction of hydrogen, helium, space industry, and scientific instrument. Here is shown a magnetic refrigerator dedicated to the liquefaction of hydrogen. Recently, unveiled by a Japanese team a few years ago. So, in the developed magnetic refrigerator, a magnetic garnet, a magnetocaloric garnet, okay, shown here, is used in an IMR cycle to achieve the refrigeration process. However, as you can see here, this family of garnets in vial moderates magnetocaloric properties, particularly in terms of the adiabatic change that reach only 1 to 2 Kelvin under a magnetic field change of 1 Tesla. So in this context, it is necessary to search for more advanced and performant materials for cryogenic application. And in this way, this family of oxide, which are rare earth manganese and rare earth vanadate, could be serious alternative to garnet due to their outstanding magnetocaloric properties in the temperature range under 50 Kelvin. So in the following, I will try to present some interesting results in relation with the magnetism and the magnetocaloric effect in some selected compound belonging to both families. And I will start with the rare earth manganate multiphysics. So in this family of multiphysics, this family of materials has attracted a worldwide interest, during the recent years, because mainly of the strong coupling between their magnetic and electrical ordering parameters. For example, in this famous work published by Guerrero and co-workers in Nature, it was clearly shown that the electrical polarization of the terbium compound can be easily switched by using not electrical field, but by using a relatively low magnetic field of about 2 Tesla, opening the way for the implementation of this family of multiphysics in spintronic device. So this is very important. So if you look here, this family of materials usually crystallize in a very complex orthorhombic structures composed of octahedra and pyramids. So in these crystallographic structures, particularly the pyramids share their edges to form chains along the z-axis of the crystals, okay? While the formed ribbons are linked by pairs of pyramid, as you can clearly see in this figure, or this figure. The pyramids, the ribbons are linked by pyramids in the AB plane, while the rare earth elements shown here occupy the empty seat surrounded by octahedra and pyramids. So this is the crystallographic structure of this family of multiphysics. It is worthy to mention that the competition between different exchange interaction in this compound involving both rare earth and the manganese lattice lead to a wide variety of phase transition, as can be clearly seen in these figures representing the specific heat as a function of temperature. So consequently, in these materials, an uncommensurate antiferromagnetic state involving the manganese sublattice occurs at a temperature of 45 Kelvin. So this incommensurate antiferromagnetic state give rise to a ferroelectric order and these materials at around 38 Kelvin. On the other hand, this incommensurate antiferromagnetic state transform into a commensurate antiferromagnetic state at 33 Kelvin, then again to becomes incommensurate at the temperature of 20 Kelvin. Concerning the rare earth elements, their magnetic moment, they usually order at temperatures below 15 Kelvin. Also, there is an important point that I would like to mention concerning this family of materials. In fact, the magnetic moment, the magnetic moment of the manganese sublattice are strongly antiferromagnetically coupled in the A-B plane, forming zigzag as shown in these figures. So this make the contribution of the manganese lattice to the wall magnetization of the materials marginal. Consequently, in this family of compound, the wall magnetization is contributed from the rare earth element. So consequently, the magnetocaloric effect is also directly contributed from the ordering of rare earth element magnetic moment. Also, the strong, interaction between the manganese and rare earth element magnetic moment lead to a giant magnetic anisotropy, as can be shown in this figure with clear, hazy, and hard magnetization axis. So from this figure, we can see, for example, that along the hazy axis, the holmium and terbium compound, involve a large magnetization values, while along the hazy axis, the magnetization is very low. So this means that large magnetocaloric effects can be expected in this material by magnetizing them using external magnetic field along their hazy magnetization axis. Also, the strong anisotropy between their hazy magnetization axis and the hard magnetization axis would lead to additional thermal effect that can be obtained not by magnetizing and demagnetizing these materials, but by rotating them in a constant magnetic field, which is very, very important from a practical point of view, because with such rotating magnetocaloric effect, you can make more efficient, compact, and simplified design for magnetic refrigeration. So, this family of multiferromagnetic is very important from a practical point of view. So, in addition to large conventional and rotating magnetocaloric effect, this compound usually present an insulating behavior because they are magnetoelectrics. This will enable us to prevent thermal losses caused by eddy current when magnetizing and demagnetizing these materials in magnetic refrigeration systems. Also, the strong coupling between magnetic and electrical ordering parameters in this compound will enable us, for example, to control the magnetization and accordingly the magnetocaloric effect by using electrical field instead the external magnetic field, which is also very important from a practical point of view. Also, these materials are chemically stable because they are oxide. Then also due to the to several degrees of freedom existing in this family of materials, there is a possibility to build multifunctional devices. Sorry. Okay, so here is given the magnetocaloric effect in terms of the entropy change along the main crystallographic axis of the holmium compound. As you can see here, the entropy change generated by this compound present a strong anisotropy, we can see that these materials involve a giant magnetocaloric effect, particularly along its AZ axis corresponding to the B direction. This giant magnetocaloric, sorry, I am searching for the pointer. Okay, this giant magnetocaloric effect is located over the temperature range around 10 Kelvin, which is in the helium, while along the hard axis corresponding to the C direction, this materials, as expected, involves moderate magnetocaloric effect in terms of the entropy change. Here is another interesting magnetocaloric oxide that can be considered for cryogenic applications. This material is the terbium manganese. Here is shown its entropy change along the AZ axis corresponding to the A directions, the intermediate axis corresponding to the B directions, and to the hard axis corresponding to the C directions. So similarly to the aluminum compound, these materials involve also a giant magnetocaloric effect in the temperature range around 10 Kelvin. However, in contrast to the aluminum compound, the terbium manganese involves giant magnetocaloric effect and a relatively low magnetic field. So this is very important from a practical point of view, because such relatively low magnetic field can be reached by using permanent magnets. Okay. Along the hard axis, so as expected, the entropy change is marginal. So this difference in the magnetocaloric effect between the terbium and the aluminum can be mainly attributed to the difference in the magnetic behavior of their magnetic moment. Magnetic moment, presents a ferromagnetic-like behavior, while in the aluminum compound, this magnetic moments, present a paramagnet, like magnetic behavior. Also, as we can see in, so as can be also seen clearly in this figure, the terbium compound involves a giant anisotropy of magnetization. This also would explain the marginal value of the entropy change along the C axis. So as I explained before, in addition to this conventional magnetocaloric effect, this family of compound present a giant anisotropy of magnetization and magnetocaloric effect. So in addition to the conventional magnetocaloric effect that can be obtained by magnetizing and demagnetizing these materials, additional caloric effect can be obtained by, as shown here, by rotating their single crystal between the AZ and the hard magnetization axis. So in this case, the associated entropy change, the rotating entropy change, is simply the difference between entropy change along the AZ axis and the entropy change along the hard magnetization axis. Okay. In this slide is shown the rotating adiabatic temperature change in terms of both entropy change and the adiabatic temperature change reported for terbium and aluminum under a magnetic field of 2 Tesla. We can clearly see that terbium compound involves better performance in terms of both entropy change and adiabatic temperature change. So, for example, in a magnetic field of 2 Tesla, the rotating adiabatic temperature change shown by terbium compound is 5 times larger than that of aluminum materials. It is also worthy to mention that the rotating adiabatic or the adiabatic temperature change shown by terbium compound is more or less 5 times larger than that shown by garnet materials that are usually used in magnetic refrigeration at low temperatures. So this will open the way for the implementation, particularly of terbium compound in cryogenic magnetic refrigeration. So as I explained before, such as difference between the magnetocaloric properties of terbium and holmium compound are mainly attributed to the difference in the magnetic behavior of terbium and holmium magnetic moment, in addition to the strong magnetic anisotropy shown by a terbium compound as clearly seen in this figure. There is another interesting point. In fact, in addition to all these factors, the specific heat of terbium compound is much lower, as you can see here, than that inviolate by the holmium compound. And this is mainly due to the fact that the magnetic moments of terbium compound are more ordered, so making lowering the contributions from the magnetic specific heat. Okay, so for more information about this family of materials, particularly the physics behind their magnetic, electrical, and magnetocaloric properties, I refer the interested reader to this review paper recently published in Crystals. And now I move to the another interesting magnetocaloric family that can be considered for low temperature application. So in this part, I will present some result obtained with the terbium vanadium compound. You know that this compound, the terbium vanadium compound, belongs to the rare earth, to the family of rare earth vanadate, that is still attracting a worldwide interest, okay? Particularly because of their fascinating, not magnetocaloric property, but their fascinating optical properties, since they can be used for example, as polarizer or as laser materials in several devices. So this family of compounds usually crystallize in a tetragonal zircon-type symmetry at room temperature, as shown here. Then this tetragonal structure transforms into an orthorhombic symmetry at temperatures below 40 Kelvin. This crystallographic transition is usually associated with a Young-Taylor effect due to the strong coupling between the electronic order of rare earth element and the crystallographic structure. Such a transition is very, very important from a fundamental point of view because it determines the magnetic, electrical, the magnetic, the ionization, the magnetic anisotropy, as well as the rotating magnetocaloric effect in this family of compound. In fact, when lowering the crystallographic symmetry from tetragonal to the orthorhombic structure, we observe a marked change in the crystal electrical field configuration. And this change in the crystal electrical field configurations lead to a large ionization, usually along the A-axis, associated with a strong anisotropy, magnetic anisotropy, and also magnetocaloric anisotropy. Okay, so what about the magnetic order? Now, usually this family of materials involves a weak magnetic order even at very low temperatures. And when it exists, the rare earth vanadate compound usually experience a magnetic order at temperatures below 4 Kelvin, as can be clearly seen here for the dysprosium compound. In the case of terbium vanadate, a non-ferromagnetic ordering takes place at temperatures below 1 Kelvin. Now I will show some results concerning this compound. So here is given the magnetization as a function of temperatures for the terbium vanadate compound reported along both the A axis and C directions. So as can be seen in this figure, the magnetizations involve G and anisotropy with the magnetization axis along the A directions, and on the other hand, a rapid magnetization, we can hear around 33 Kelvin, we can observe a fast change in the magnetization. And of course, this fast change in the magnetization is due to the lowering of crystallographic symmetry from tetragonal to the orthorhombic structure that take place exactly at 33.1 Kelvin. And of course, this structural transformation associated with a cooperative and Taylor distortion give rise to, as can be seen here, a large magnetization along the A axis and a strong magnetic anisotropy in these materials. So this crystallographic transition, which is associated with the entire cooperative distortions, is confirmed by this Raman scattering data reported in this figure, where we can see that under the temperatures of 33 Kelvin, we can see clearly splitting in some energy levels. Okay. Here is given the entropy change as a function of temperatures in the terbium compound along both the AZ axis and the Hardmanization axis. So particularly a giant Magnetocaloric effect is observed in these materials at very low temperatures. Particularly temperatures around 5 Kelvin. For example, in the magnetic field change of from 0 to 2 Tesla, the entropy change reach a value of 20 joule per kilogram Kelvin. But more importantly, this giant Magnetocaloric effect remain approximately constant over a wide temperature range, okay? As shown here, particularly under sufficiently high magnetic field. This is very important from a practical point of view, particularly when using some specific cycle to achieve the refrigeration process. For example, the Eimer and the Ericsson thermodynamic cycle. And of course, this wide range, this large working temperature range under high magnetic field lead to a record diffusion capacity for terbium vanadate. Okay, here the refrigerant capacity of this compound is compared with some of the best Magnetocaloric materials that can be considered for cryogenic applications. The refrigerant capacity is really a very important parameter because in addition to the Magnetocaloric effect, it takes 2 minutes.
2 minutes.
I will finish.
Okay.
Yeah, 2 minutes. I will. Thanks, Professor Zaz. Okay, so this refrigerant is very important because it takes into account both the Magnetocaloric effect in addition to the temperature, the working temperature range. In other words, the refrigerant capacity measures the energy that can be transferred in an Eimer cycle between the hot and cold ends. Also, as expected, you can see here that the material present a strong anisotropy of the Magnetocaloric effects. So accordingly, the materials also involves large rotational rotating Magnetocaloric effect that are similar to the conventional one. Okay. Of course, this rotating Magnetocaloric effect, as shown here, can cover a wide temperature range, going from 50 to 0 Kelvin. So for more information about particularly the information on how the crystalline field acts on the magnetic and magnetocaloric properties of the terbium vanadate compound. So please, you can take a look at this very, very, very interesting paper just published a few days ago in Physical Review Materials. This work was done in close collaboration with my colleagues from Taiwan, from Sherbrooke University, and from the Bulgarian Academy of Science. And now, sorry, Professor Zaz, I come to conclusions. So as shown in this presentation, some of the raw earth manganese and raw earth vanadate involve excellent magnetocaloric properties at cryogenic temperature range, opening the way for their application in the liquefaction of hydrogen and helium, for example. Okay? Particularly, the terbium vanadate compound involves a large magnetocaloric effect over a wide temperature range, which is highly appreciated from a practical point of view, particularly when using IMER and Ericsson cycles. Also, these materials show high level of rotating magnetocaloric effect in the temperature range under 15 Kelvin, opening the way for the amplification, the implementation in more efficient, compact, and simplified magnetic coolers. However, the big challenge remains the growth of single crystals in a large quantities. But fortunately, textured powders and their magnetic field will be a serious solution, since this oriented powders would play, would behave like a single crystals. So that's all, folks. Thank you very much for your attention, and I would be very happy to answer if you have any question. So thank you very much.
Thank you very much, Professor. We have, I think, 3 other presentations before discussions.
Okay, so yeah.
3 other presentations.
Okay, so
you can present. You can start by presenting your journal.
Yeah. Okay. So with the Professor of Professor Daniel Fouchard, we are editing a new special issues on the Magnetocaloric effect and its application. This special issues is organized in close collaboration with the Crystal journals. So for the audience, if you have any interesting papers, please send us your proposal. You can directly contact me, or you can also contact Professor Daniel Fouchard. So now we have Professor Zaz, you are here. So we have the 20 minutes or 30 minutes discussion.
We have 3 presentations before going to discussion.
Okay, okay, good. So and the next the presenter is Faisal Al-Masdouqi, who is a PhD student working with me on the kinetic of hydrogen in some intermetallics. This will be a very interesting topic also for Daniel Fouchard. So today, Faisal Al-Masdouqi will present some, preliminary result dealing with the stability of hydrogen in the family of long-time iron silicon-based materials.
My PhD project. My project is a collaboration between University of Science Rabat and University International Rabat, supervised by Professor Mohamed Louidi and Professor Mohamed Bali, with a team composed by Professor Ben Youssef Abdillah, Professor Al-Kanz Abdullah, and Professor Monqashi Omar. So the subject of my project is to study the stability of the hydrogen in the magnetocaloric material, lanthanum, iron, silicon, hydrogen. So the first or principal motivation about my material is his magnetocaloric properties for cooling application. So like we know, the old technology about cooling is based on gas cooling. This gas is so negative for the environment. So research wants to replace this gas with magnetic material. In our case, the lanthanum, iron, silicon have a good potential for this kind of application. So here I present the elements of my material. So the material have a lanthanum, a rare earth, the iron, a transition metal, the silicon, a semiconductor, and the hydrogen, a non-metal. The magnetic character is for the iron with ferromagnetic character. The structure of my material is the cubic complex structure of NaZn13 with 120 atoms in the unit cell. The material have two kinds of iron. The first one is the icosahedral structure, and the second one is into the first one. So for an application in cooling magnetic, the material should have a high isothermal entropy change and a high adiabatic temperature change and the Curie temperature beside room temperature. So like we see in this table, the material have a good magnetocaloric properties, but the Curie temperature remain low for cooling application. In this case, we add the hydrogen into the material to increase the Curie temperature. So the material is usable for cooling application. But the major problem of adding the hydrogen into the material is the diffusion. So the material become inhomogeneous with two regions. The first one is condensed by the hydrogen and the second one without hydrogen. The impact of this diffusion is for the Curie temperature. So like we see here in this graph that the Curie temperature has been split by two temperatures, and that is so negative for cooling application. Many solutions have been proposed like doping by the manganese or saturate the hydrogen into the material, but this kind of solution decrease the magnetocaloric properties and the material remain useless for magnetic cooling. So in my PhD project, I will study the mechanism of the diffusion of the hydrogen into the material. I will use the physical simulation methods like the density functional theory, the kinetic Monte Carlo, and the molecular dynamics. So my first work of my PhD projects is to study with the DFT the properties about the material and his hydrate, to extract the impact of the hydrogen into the material and his stability. The first result that I have extracted is the density of stage, the anisotropy, and the electronic density. So here I present the density of stage, so we can see that the two materials have the same character, and it is the metallic character and the ferromagnetic character. And we can also see that when we add the hydrogen into the material, the density of states have slightly changed. So the second result that I have extracted is the anisotropy. So we can see that the two materials have magnetic anisotropy. And we can also see that when we add the hydrogen, the AZ axis magnetization and the hard axis magnetization have been changed the direction. The last result that I have extracted is the charge density. I extracted the charge density to investigate the bending of the hydrogen into the material. So like we see in this picture, the hydrogen is bending with the iron without the silicon. So when the silicon is beside the hydrogen loses some bend. So we can conclude that when we increase the concentration of silicon into the material, the hydrogen loses some bands and decrease his stability. So thank you for your attention.
Okay, so I would like to thank Faisal for this nice presentation. The next presentation will be given by Dr. Rashida Al-Amouri, and he will talk us about some magnetic properties in a family of permanent magnets.
Hello, my name is Lamour Rashida.
So Rashida Al-Amouri, the floor is yours.
Energy Sciences at Mohammed V University of Rabat. I'm also affiliated to Materials and Nanomaterials Center at Master Foundation. Today I'm going to present one of our works entitled improved magnetic properties of M-type strontium hexafluorides through nanocomposites. A permanent magnet is a material which is initially magnetized and then creates its own persistent magnetic field without the need for continuous electric power, and thus no heat generation. Up to now, there are major families of permanent magnet materials, ranging from fluorides, known for their low cost and low efficiency, to rare earth-based magnets which offer a high performance but very expensive. Nowadays, rare earth-based magnets are well known as the strongest type of permanent magnets, although the risk of supply of rare earth elements increased progressively, which required worldwide efforts to develop new materials without rare earth elements or containing little or heavy rare earth elements. On the other hand, fluorides have some interesting properties such as good chemical stability, easy synthesis route with low cost, significant saturation magnetization, and moderate coercivity. These properties make of this kind of materials promising candidates to replace rare earth-based magnets in a wide range of applications that require low magnetic stored energy. So in this work, we aim to improve the magnetic properties of M-type strontium hexafluorides through nanocomposites. To prepare our nanocomposites, we start by preparing the strontium hexafluorides and cobalt spinel fluorides nanoparticles by using the standard coprecipitation methods. Then the prepared nanoparticles were mixed physically using an agate mortar for 1 hour and then calcined at 1000 degrees Celsius for 3 hours to achieve strontium hexafluorides, cobalt spinel fluorides nanocomposites with different molar ratio. For the rest of this presentation, we will refer for the parent strontium hexafluorides and cobalt spinel fluorides as SFO and CFO, while we will use CS5, CS10, and CS20 to refer the nanocomposites with 5%, 10%, and 20% of the soft phase. From the XRD patterns, we can see clear that the CFO crystallizes in the cubic spinel structure, and the SFO crystallizes in the hexagonal structure with space group P63MMC, while the XRD patterns of the nanocomposites show the presence of both cobalt spinel fluorides and strontium hexafluorides phases with no peaks of any secondary phase. The SEM images of the SFO nanoparticles show a hexagonal platelet morphology, while for the nanocomposites we see the presence of bigger and smaller particles, which can be attributed to the presence of cobalt spinel fluorides and strontium hexafluorides nanoparticles. And from the EDX analysis, we can see clear that there is no elements other than cobalt, strontium, iron, and oxygen in our samples. To evaluate the magnetic properties, we plot the magnetic hysteresis loop at room temperature. As we can see from the parent hysteresis loop, the strontium hexafluorides have a larger coercivity, while the cobalt spinel fluorides show the higher saturation magnetization. From the hysteresis loop of the nanocomposites, we see clear that there is a good single magnetic phase behavior, which is a good indicator of the exchange coupling mechanism. And to evaluate the performance of the prepared sample for the permanent magnet applications, we plot the maximum energy product as a function of the soft phase content. We can see clear an enhancement of about 26% of the maximum energy product for 5% of the soft phase compared to the pure hexafluoride phase. As a conclusion, the standard coprecipitation rule followed by physical mixing were used to synthesize the nanocomposites. The exchange coupling mechanism have been proved in all nanocomposites, and an enhancement of the maximum energy product was obtained for 26% of about 26% for 5% of the soft phase. Before finishing, I would like to thank all my collaborators in this work from Master Foundation, Mohammed V University of Rabat, GreenMat Laboratory, and the Faculty of Sciences Simlalia in Marrakesh. And thank you.
Okay, so let's thank Rashida for the next presentation by Umayma Shdil, who will talk about some magnetic and magnetocaloric properties of a very promising magnetocaloric oxide.
Hello everyone, I'm Shdil Umayma, PhD student at the International University of Rabat, supervised by Professor Mohammed Bali, and we are working on new refrigeration technology that is more respectful of the environment and less energy consuming. This is the case with magnetic refrigeration. This technology has multiple advantages, such as the high thermodynamic efficiency generated by the quasi-reversibility of the magnetocaloric effect, and also the absence of air pollutants. Magnetic refrigeration is based on the magnetocaloric effect, an intrinsic property of certain magnetic material. It can be defined as the thermal response, heating or cooling of a magnetic material during the variation of their magnetic state, magnetized or demagnetized, induced by an external magnetic field. It's the result of magnetic entropy variation of the material. There are a very large number of magnetocaloric material which have been studied since the discovery of the giant magnetocaloric effect. Among these material we can find gadolinium, but in contact with water and air, gadolinium and other intermetallics oxidize easily, resulting in the degradation of the thermodynamic performance and the lifetime of the magnetic refrigeration devices. For this reason, research activities have been directed in recent years toward the manganese oxides. These oxides will be the subject of my doctoral thesis. In this presentation, I will present the thermodynamic performance of the RSR-MnO3 oxide in a functional magnetic refrigeration system. I choose to study this family of materials due mainly to their excellent magnetocaloric properties around room temperature, the high chemical resistance, and also the lower cost of the constituent elements. Before the simulation of this oxide in the efficient IMER cycle, the theoretical prediction of the magnetocaloric properties is very important. Using the molecular main field theory and the thermodynamic laws, its adiabatic temperature change and the total heat capacity are calculated as a function of temperature and the applied magnetic field. And as you can see in this figure, under a magnetic field of 1 Tesla, for example, this oxide represents a adiabatic temperature variation of 0.8 Kelvin. For refrigeration and heat pump application, this magnetocaloric effect can be amplified by using specific magnetothermal cycles called the active magnetic regenerative cycles. This IMER cycle consists of 4 steps, which are illustrated in this figure. The temperature of the hot source and the cold source gradually change until each reaches an equilibrium temperature after a certain number of cycles. To determine the temperature difference between the hot and the cold source, a numerical modeling with the one-dimensional approximation of the heat exchange between the magnetocaloric materials and the heat transfer fluid is necessary. The model equations depend on the geometry, the characteristic of the fluid, and the magnetocaloric properties of the material. To validate our model, we made a comparison between our numerical results and those found experimentally by the developed the prototype in 2012. The regenerator considered in this experimental study is constituted of parallel plate of gadolinium. In this first figure, we can see the temperature evolution of both sides, hot and cold ends of the materials, as function of IMR cycle number. The obtained maximum temperature span is about 32 Kelvin. This result is qualitatively in a good agreement with that experimentally found, and it confirms the reliability of our numerical model, which allow us to visualize the thermodynamic performance of the oxide. Under the same work condition, the PRSR-MnO3 oxide show a maximum temperature span of about 12.5 Kelvin. But by increasing the magnetic field, there is a possibility of increasing the performance of this oxide. For example, for field equal to 8 Tesla, this oxide can generate a span of 33 Kelvin, like the gadolinium at 1.45 Tesla. The challenge now and our current work is to find how we can reach this theoretical limit of this oxide without going through a very high magnetic field from a fundamental and physical point of view, and also at the level of the preparation of materials. Thank you for your attention.
Okay, thank you very, very much, Umayma, for the beautiful. So I think now we have the time for a discussion. Okay, just I would like to underline that Professor Daniel Fouchard has some troubles with the connection, and he would like to thank all the audience. He would also thank the organizing committee for the nice organization of this conference, and particularly I would like to thank Professor Yusuf Zaz. So now the session is open for the discussion. I will try to answer now some question. I don't know, we have some question. Okay. Okay, I will try. Yes, okay, you have a question here. Okay, okay, the first question is from, okay, okay, good. Okay, so the first question is from Fuad, okay, Fuad Al-Halou. He asked if the magnetic refrigeration can be done for air conditioning in an isolated room, for example, in and out grid area using strong battery, for example. Okay, okay. So thank you very much, Fuad, for this very interesting question. Really, I cannot see the relation between magnetic refrigeration and batteries, but I will answer your question concerning the the ability of magnetic refrigeration to be applied in air conditioning. Yeah, of course, the magnetic refrigerations can be, in addition to the domestic refrigeration, for example, the magnetic refrigeration can be, implemented in the air conditioning machines. So, and in this case, for example, the air can be used as a high transfer fluid. I remember while I was working in Switzerland, we have developed, a magnetic coil machine that can be dedicated to the air conditioning. So the answer is yes. There is another question from Said Al-Wahabi. Okay, Said, he asked why the latest entropy is not neglected, and also why we increase the entropy, the magnetic entropy, the entropy lattice decrease. Okay, so thank you very much, Said, for this very interesting question. And maybe just to answer your question, I need to share with you the screen. Okay, so I will share the screen. Okay, I will share my, okay. Okay, so just to answer the question from Said, in fact, the Magnetocaloric effect is an intrinsic properties shown by some magnetic materials. Taking, for example, a ferromagnet or a paramagnet, when the magnetic field is applied, the magnetic moment become aligned along the direction of the magnetic field. This make the materials more ordered from a magnetic point of view. So in this case, the function state corresponding, that can be associated to the magnetic order is the magnetic entropy. So consequently, the magnetic entropy decreases. Okay, so we have a magnetic order. Then after this magnetic order decreases the magnetic entropy of the materials. In adiabatic conditions, the fall entropy must remain constant. Okay, so this decrease in the magnetic entropy is associated or lead to an increase in the lattice entropy. When we talk about lattice entropy, we talk about the phonon or the atoms. So in this case, the atoms begins to vibrate more and the material heat up. Okay, so now in the opposite directions, when the magnetic field is removed, now the magnetic moment return to their random directions. Okay, so in this case, the magnetic entropy increase and the lattice entropy decrease, then the material cool down. So the magnetic refrigeration consists to take advantage of this thermal effect produced by the material when it is magnetized and demagnetized by an external magnetic field. Okay, so now the question is, what about the why we neglect the electronic entropy? In fact, the Magnetocaloric effect now is mainly due to the coupling between the magnetic moment and the atoms. Okay, when we change the order of the phonons, the vibration of the phonon also changes. But we cannot really, the electronic entropy cannot always be neglected, okay? Regardless of the nature of materials. For example, we can neglect the electronic entropy in materials with localized electrons, like in our earth element, for example. But in the case where the electron present an iterant character, in this case, of course, we cannot neglect the contribution from the electronic part. Okay, so this is my answer to Said. There is, okay, just I will look at other questions. Okay. Affiché. Le partage d'écran est en pause. OK. Le partage d'écran est en pause. Okay, so are you hearing me? Okay. Okay, just I will take. Are you hearing me? Can you hear me? Okay. So. Professor Yusuf Zaz?
Yes, yes.
Okay, you heard me. Okay, so
yes.
Okay, so
you can answer questions from Q&A.
Okay, yeah, okay, good. So
authors
there is another question from. Okay, so there's another interesting question from take very small value of external magnetic field. Okay, so I think this question is for Daniel for sure, but it's okay, I will answer. Okay, so thanks, Rizlan, for the question. So usually, you know, in magnetic refrigeration, low magnetic field, you know, are highly appreciated from a practical point of view. Why? Because such low.
Professor Belli, we don't hear well your question. We can't repeat it. Please repeat the question. You have a problem of connection. Please repeat the question. The connection, your connection is lost. Please unmute your mic.
Okay, so thank you, Professor Zassau. I think if you can, okay, there is, I think you have time to answer some other questions. I am Ghanayat from Algeria University. What is the lowest cryogenic temperature reached by your systems? Okay, so welcome Adil from Algeria. I mean, you know, in magnetic refrigeration, there is, systems that can be dedicated to the refrigeration at room temperatures and to the cryogenic applications. So concerning the refrigerations close to room temperatures, while I was working in Switzerland, we have developed, a magnetic refrigerator dedicated to the applications around room temperatures. With this cooling machine, we can easily reach temperatures below, 0 degrees Celsius. Okay. However, I am not really building systems for magnetic refrigeration at the cryogenic temperature range. I am working on materials, okay, that can be used as a refrigerant in this very interesting temperature range. Okay, so thank you again, Adil. Okay, what are the advantages? So there is an interesting question from Zahra Nifah. What are the advantages and disadvantages of magnetic refrigeration? Very interesting question. You know, let's start with the advantages of magnetic refrigeration. In fact, magnetic refrigerations offer us, usually present a higher thermodynamic efficiency. For example, with magnetic refrigeration, we can reach, more than 70% of Carnot thermodynamic cycles, while in conventional refrigerations, let's say 30 to 40% of Carnot efficiency can be reached. Okay, so advantage number one is the higher efficiency. Okay, and also with magnetic refrigeration, we can completely eliminate the harmful synthetic refrigerant, okay, for example, CFC, HCFC, and HFC, usually used in conventional refrigeration. You know, that sort of synthetic refrigerant are harmful for both our health and, you know, the environment. In fact, they contribute largely to the global warming, and some of them are responsible for the destruction of ozone layers. Also, with magnetic refrigeration, we can make more compact systems. We can use this technology to cover a wide range of applications, going from room heat pump to cryogenic temperature range. We can also recycle all the materials used in this technology. We can recycle Magnetocaloric materials, recycle permanent magnets, you know, and much others. Okay, so now the drawbacks of this technology. In fact, the main drawbacks of this technology is related to the you know, this technology is it's emerging and is very, very expensive. Okay. So since in addition to you know, Magnetocaloric materials, we need to use, for example, to produce much higher now enough magnetic field, we need to use some
Excuse me, Professor Bali.
Expensive permanent magnets called.
Excuse me.
Yeah.
You can give.
Yeah. Go ahead, Professor Azaz.
To PhD student to answer their question, the question related to them.
Okay, yeah, of course. So if I don't know if there is any question to the student.
You can ask a question as.
Okay, I can ask a question. Okay. Okay. So okay, I have a question. I don't know if is here. The first presenter.
Khawla is there.
Khawla, but Khawla will present later. Okay, Umayma. So Rashida is here. Rashida Amouri.
Yes.
Okay, I don't. Rashida, if I cannot see Rashida.
Yes,
I can see Rashida. Okay, so I have a question for Rashida Al-Amouri. Why, you know, what make your the composite? Okay, so can you please switch off your micro?
Okay.
Okay, so I have a question for Rashida. What make your nanocomposite permanent magnet important when compared to the neodymium-iron-borne materials, for example? Yeah, Lamori is here.
Hello?
Yeah, hello, Rashida.
Can you hear
Please
me?
go ahead.
Okay, as I said in the presentation, our permanent magnet materials, we are not compared our oxides with rare earth-based magnets. Because as I said in the presentation, it depends on the applications, and we are looking for low energy applications. Because as we all know, as the permanent magnets have a higher energy product, it can be used in wind power, for example, or magnetic levitation. Or, however, our permanent magnets are used mostly in automotives and speakers in mobile phone. So when comparing our nanocomposites, we compared the obtained magnetic properties with the parent phase. We cannot compare the obtained properties with those for rare earth-based magnets.
Okay. So thank you very much, Rashida, for the answer. I don't know if there is any question for Rashida concerning the her presentation. Otherwise, I have one question for Umayma. Umayma Shadid. So, are you here? Yeah, Umayma is here. Okay.
Yes, sir.
Okay, Umayma, so thank you very much for the nice presentation. So my question is, how you manage to reach this theoretical limit for the Magnetocaloric effect? You can answer in French.
Excuse me, it's, official language of the conference is English.
Is English, okay. So, okay, Umayma, you need to answer in English.
We will try to reach the theoretical limit of this oxide going through a fundamental point of view, and also at the level of the preparation of materials by making a kind of pressure and also other effects such as strain or doping with the other rare earths such as gadolinium or erbium, helium, and also by adding other secondary phases such as the oxide, nickel oxide, or oxide of and also making some strain. We are looking in making strain on this oxide and doing magnetic measurements with pressure and see how if we can find larger magnetocaloric effects.
Okay, okay. So thank you very much, Umayma, for this answer. And by the way, later Hamza Bouhani will show how the strain effect can be used to engineer the magnetocaloric properties in some magnetocaloric materials. Okay, so I don't have. Okay, so okay, so now we move to the second part of this session, and the next speaker is Khawla Al-Wali from École Nationale Polytechnique, who is a pioneer in the field of magnetic refrigeration, particularly the IMR cycle. So, Khawla Al-Wali, welcome. The floor is yours.
Hello, welcome to my presentation on numerical modeling of active magnetic regenerators. I've divided my presentation into three main parts. First of all, I will talk about the concept of magnetic refrigeration and armor cycle process. Second, we will look at the civil works on numerical modeling of one-dimensional armor models. And finally, I will show you the recent detailed models which have been developed over the last decade. Magnetic refrigeration is one of the green refrigeration technologies that has attracted more and more attention. The concept of magnetic refrigeration is based on the magnetocaloric effect, which occurs in some materials when they are subjected to applied magnetic field changes. The armor cycle has four basic processes. The first one is the adiabatic magnetization. The second is the warm blow at applied field. The third step is the adiabatic demagnetization. And the last one is the cold blow at zero field. Most of the numerical models previously developed were one-dimensional, presented as computational code using different languages. Several numerical methods to predict the performance of the armor has been investigated previously, such in Ismaili's models, Trisak, Rodot, and Kawanami. However, these researches were performed with different conditions and assumptions. Engelbrecht improved previous numerical simulation models of active magnetic regeneration, and compared the predictions of the new model with experimental results. Another important study was performed by RISA, who proposed a methodology based on numerical approach for optimizing the design of the magnetic refrigerators. Torregrossa Jamie proposed new finite difference model that optimally combined explicit and implicit techniques for solving one-dimensional transient heat transfer in active magnetic regenerators. Comprehensive numerical and experimental assessment of packet bed was performed by Trevisolli. It was concluded from the results that further work was required for improvement of the modeling of active magnetic regeneration and its evaluation. In addition to consideration of the internal irreversible heat transfer and viscous losses, there was the need to incorporate the demagnetizing losses and heat losses. Peter Sang was the first to implement a complete two-dimensional model of parallel plates. The model uses a finite element method to solve for fluid flow profiles and temperature gradients in the solid and the liquid. With the constant increase in computational resources, three-dimensional models have been progressively developed. Starting from the complete one of Bouchard, presented three-dimensional model which solved the fully coupled problem. Another numerical study was conducted by Apria, wherein simulations were performed using two-dimensional models of active magnetic regenerators fabricated from 6 different magnetocaloric materials. Recently, Musica developed an open-source direct numerical simulation solver that enabled simulation of active magnetic regeneration cycles. They showed that the model could be applied to regenerators with different geometries and properties, as well as to other caloric technologies. An interesting numerical study was also conducted by Mumford and Palm, who investigate and compare the performances of different light armors with the purpose of determining the extent of magnetocaloric materials improvement required for a magnetic refrigeration system. It is straightforward that one-dimensional models are not able to account for the real geometry of packet bed regenerators. However, a monodimensional model is suitable for design and primarily performance predictions. The open-source direct numerical simulation solver is of great interest, since it opens some interesting perspectives for the development of innovative regenerators for magnetocaloric refrigeration and also for any other caloric technologies. Thank you for your attention.
Okay, so thank you, Khawla, for the nice presentations about the used IMR models in magnetic refrigeration. And now we move to the presentation by Zakaria Matallah, who will talk about the design and the future design of a future heat pump for aerospace applications. So Zakaria, the floor is yours.
There is such a device that transfers heat using phase change process and with a very minimal thermal gradient. Hi, my name is Zakaria Matallah. I'm an energy engineer and PhD student from the University of Science and Technology of Renewable, and in this presentation we will try to investigate the design of the future heat pipe for aerospace application. So in order to present this topic chronologically, the outline will be structured in this manner, starting with the motivation behind this work, the general context, and for the last but not the least, investigating micro heat pipe system, and finally we'll make a conclusion. In the recent years, electrical equipments are becoming smaller and faster, which makes them generate a lot of amount of heat. So there was a lot of recent emphasis on heat dissipation. Microheat pipe is being looked as one of the emerging technologies in thermal cooling and has a set of features which can we classify them as follows. High thermal conductivity compared to the standard thermal conduction process, very low thermal gradients to transport heat, It's a passive device, relatively small in size and weight also. Makes it desirable component for cooling small devices. This presentation will focus to give a better understanding of the heat exchangers by two-phase process, and also the path we'll pursue in our PhD project in order to design the future cooling device for the aerospace application. So to do such a thing, it's necessary to start investigating the heat pipe for its small scale, micro heat pipe precisely, and then upgrade it to the other scales in order to understand deeply what's going on inside of it and how and what are the limitations that governs those heat exchangers in our real life. There is a lot of families of heat pipes, but the working process is a little bit the same with some small exceptions. The first one is the capillary heat pipe, which is a heat transfer device that combines the principles of both thermal conductivity and phase transition to effectively transfer heat between two solid interfaces. The heat input vaporizes the liquid working fluid inside the weak structure in the evaporator section. Then this latent heat flows toward the condenser to release heat to the cold environment. Then the liquid condensator returns back to the evaporator using this porous media named weak structure, which provides the sufficient capillary pressure to make sure that the liquid arrives to the evaporator section so that the evaporation condensation process still continuously operates. Another type of heat pipe called thermosiphon, which has the same operating process, but the only difference is that the liquid is returning back by the gravity without any use of such a capillary structure. Loop heat pipe possesses all the main advantages of the conventional heat pipes, but owing to the original design and special properties of the capillary structure, are capable of transferring heat efficiency for distances up to several meters at any orientation in the gravity field, which makes a desirable device for thermal cooling in aerospace application. Here we have some applications of the heat pipes family. Thermal management of electronics. We can use heat pipes to cool processors in the phones or laptops. Thermosiphons are used in solar collectors. Loop heat pipes are used to cool satellites. And finally, heat pipes also are used in the heat, ventilation, and air conditioning systems. Microheat pipe system. Microheat pipe is a non-circular channel with sharp edges to provide the sufficient driven pressure to the liquid by the increase of its main curvature at those edges from the condenser to the evaporation, so that the liquid arrives to the evaporation section. We have the animation of how the microheat pipes work. They are used in several systems like sensors, electronic watches, temperature warning systems. Also are used to increase the inherent thermal conductivity of silicon for such a task. The aim of this presentation is to prescribe the main path of the PhD project by understanding the heat pipes in the microscale, to really get a comprehensive knowledge of the phenomena that occurs like Marangoni effect due to the large change in the surface tension in a small tiny time. Also to master the limitations of the heat pipes in general, which could occur when a bad operation of the microheat pipe is made, like dry out or floating, as an example, or when the vapor reaches its sonic velocity, and this kind of limitations we call sonic limit. Thank you for your attention.
Okay, so thank you very much, Zakaria, for the nice presentation. And the next speaker is Hind Benzidi, who will talk about the storage of hydrogen. So Hind, the floor is yours.
Today it will be an introduction of cryogenic storage of hydrogen. So, as we know right now, the world is standing on the brink of an energy crisis. Our demand for energy are increasing day by day. However, on the other hand, the resources that we are utilizing to fulfill are limited and they cannot expand, and furthermore, if we use them as we use it now, they will soon disappear. Nevertheless, we are not stranded yet. We still have plenty of alternatives that we can try to use to stave off the energy crisis. Among all of these alternatives, hydrogen fuel cell as stand as the most promising alternative. So why hydrogen? Hydrogen has the highest energy per mass of any fuel, and however, its low ambient temperature density results in low energy per unit volume. In many ways, hydrogen is the perfect fuel and the most efficient to produce and produces no emission when used in a fuel cells or combustion engine. Therefore, requiring the development of advanced storage methods that have potential for higher energy density. So, hydrogen is considered to be an ideal energy carrier in the future. It can be produced from water by using a variety of energy sources such as solar, nuclear, and fossil, and it can be converted into useful energy form efficiently and without environmental effect. Hydrogen can be also converted directly to electricity by fuel cells with a variety of application in transportation and stationary and power generation. The storage of hydrogen is the key of enabling this technology for the advancement of hydrogen and fuel cell technology in application, including power, portable, and transportation. So, physically, hydrogen it can be stored as either as a gas or liquid. But the storage of hydrogen as gas typically require high pressure. However, the storage of hydrogen as liquid require cryogenic temperature because of boiling point of hydrogen at 1 atmosphere pressure, which is minus 252 degrees Celsius. Also, hydrogen can be also stored on the surface of solid by absorption or within the solid by absorption. These last methods are under research and development. The first one, which is the physical storage of hydrogen, it is only the method that are work now in the industry. In its liquid form, hydrogen has a density of 70.8 kilogram per volume, which is make it advantageous for liquid storage compared to gases. But the main failure is the importance of the secondary system necessary to reach liquid form. The hydrogen must boil to a pressure of 10 bar at a temperature of about minus 253 degrees Celsius. This involves tanks with very high thermal insulation and therefore likely to maintain the hydrogen at this temperature and avoid the loss by evaporation. Finally, cryogenic application extend beyond its present day-to-day usage. and one important aspect of its storage of high density liquid hydrogen to liquefy hydrogen, it must be cooled to cryogenic temperature through liquefaction process. Hydrogen is most commonly transported and delivered as liquid when high volume transport is needed. In the absence of pipeline tracks transporting liquid hydrogen are referred to as liquid tanker. So thank you for your attention, and I will be available for your at the question session to respond to your question. Thank you.
Okay, thank you very much, Hein, for this nice presentation about the hydrogen storage. And we'll move to the last presentation in this session. So in the last presentation, Hamza Bouhani from Lorraine University and Mohammed Fifth University will show us how the Stern effect can be used to tailor the magnetocaloric properties in some oxide materials. So Hamza, the floor is yours.
Hi everyone. My talk today is about engineering of the magnetocaloric properties of epitaxy-oxide thin films by swinging path. As we all know, cooling is used daily for the preservation of food or medicine, for the reliability of electronic devices, as well as for the well-being of people. Based on a compression extension cycle of a gas, it presents some disadvantages: difficult integration in embedded systems and strong environmental impact, as well as the considerable consumption of energy. It's therefore necessary to develop alternative technologies in the field of solid-state physics. One of these technologies is the magnetic refrigeration, an emerging phenomenon which can open to innovating and potentially low-carbon technology. It's based on a phenomenon known as the magnetocaloric effect, which is the observation that magnetocaloric materials change their thermodynamic properties when subjected to an external magnetic field. In this work, I will present a new material that belongs to the multiphysics family, praseodymium vanadate, a material that presents discouraging magnetocaloric properties of its bulk form, but wouldn't prevent us from tailoring its magnetic and accordingly the magnetocaloric properties, since the material have a rich phase diagram with strongly correlated spin, charge, orbital, and lattice degrees of freedom, and is very sensitive to external stimulation. For that purpose, we have grown several PVO thin films on different substrates with different thickness, using pulsed laser deposition in order to investigate the effect of strain on the overall magnetism. A series of PVO thin films deposited on a 001 oriented STO substrate revealed a hard ferromagnetic-like behavior, as the magnetization here can be described as an addition of soft and hard magnetic contribution. Coercive field is about 2.8 Tesla, very close to the bulk value, the bulk which is a strong antiferromagnet. And saturation magnetization is very low, about 0.29 Bohr magnetron. And by applying a compressive strain via LSAT substrate, the magnetization saturation is markedly enhanced when compared to PVO and STO, reaching about 3.1 Bohr magnetron at 10 Kelvin for magnetic field applying in simple plane, and 4.86 Bohr magnetron at 3 Kelvin. In addition, the coercive field is largely reduced to attain about 0.3 Tesla at 10 Kelvin, as shown in the table, and keep decreasing to reach about 0.05 Tesla at 3 Kelvin to become nearly a soft magnet. A field-induced first-order metamagnetic transition from antiferromagnetic to ferromagnetic state as a result of strong competition between praseodymium 4F and vanadium 3D spins is observed in the magnetization versus the applied magnetic field. Such competition often leads to giant magnetocaloric effect in strongly correlated materials. We carefully then calculated the magnetic entropy change from magnetic isotherms, taking into account the impact of hysteretic phenomena and using the well-known Maxwell relation. While it was very hard to observe the magnetocaloric effect in PVO on STO films due to the low magnetization and the overlap between isotherm curves, a giant cryogenic magnetocaloric effect was observed in PVO on LSAT films. We reached an unusual value of 56.8 joules per kilogram Kelvin, which is higher of the most of the in magnetic field of 5 Tesla, which is higher of the most of available materials working in the same temperature range. The magnetocaloric effect is also giant in moderate applied magnetic field, which means we will reach a value of 90.72 joules per kilogram Kelvin using only permanent magnets. Our theoretical calculation based on density vectional theory predicts correctly the anisotropy and the ground state as the G-type antiferromagnet, and confirms also the competition between ferromagnetic and antiferromagnetic interaction at low temperatures. As a conclusion, we have demonstrated that the magnetocaloric effect will be easily tailored via thin-film approach. A good choice of thickness, substrate, and crystal orientation enables us to markedly enhance the magnetic moment, dramatically decrease the coercive field, and also take advantage of the competition between ferromagnetic and antiferromagnetic interaction to give birth to giant cryogenic magnetocaloric effect. This finding would open the way for the implementation of PVO thin films in more efficient and eco-friendly magnetic refrigeration applications, and may also pave the avenue for a new application taking advantage of the possibility to tailor the magnetic coercivity in those films. For more details about the work, please read our recently published paper in Applied Physics Lectures. I'll be available to answer all your questions of the section, the discussion section. Thank you.
Okay, thank you very much, Hamza, for this very, very interesting work. And now the session is open for a question. And I have a question for Khawla Al-Wali. Khawla is with us here?
Hello. Hello, everyone.
So, hello.
Do you hear me?
Hello, Khawla. Welcome. Yes, yes, we hear you. So I have one question, Khawla. My question is, so which IMER model is more appropriate, and in which conditions? One model, two models, or three models?
Which? I didn't hear you. Sorry, I didn't hear you. I have a bad network.
Okay, I mean, my question is, which IMER model is more appropriate to calculate magnetocaloric performance in a cooling machine? 1D model, 2D, or 3D, and in which conditions?
All the models are appropriate, but their models are more sophisticated. For example, the one-dimensional models are suitable for design and primarily performance predictions. However, detailed models are unable to take into account the most of the real geometry. But I think that the direct numerical simulation solvers, which use an open source, it's more appropriate for the simulation of the armor circle.
Khawla, I don't know if there's any
Do you hear me?
Yes, we can hear you.
Okay, so thank you very much, Khawla, for your answer. I don't know if you have any additional question to Khawla.
Okay.
Okay, so okay, nice. So thank you, Khawla. I don't know if Zakaria Matalla is with us.
Do you hear me?
Okay, so Zakaria, are with us? Yeah?
Yes, yes. Do you hear me, sir?
Yeah, I hear you. So thank you very much for your the nice presentation. My question is, in the Moroccan, what is really your target in the Moroccan context? So we are developing a heat pipe for aerospace application. So you are working with some industrials or a Moroccan government, or it is a fundamental work?
No, it's a fundamental work at this moment, but maybe in the future will be extended to be work with some kind of companies in this field of area.
Okay. Okay. Okay, thank you, Zakaria. Any question for Zakaria? Okay. Okay, thanks, Zakaria. Hind Benzidi is with us.
Hello.
Hello, Hind. So nice to hear you. So there is a question from the audience for you. The first question is from Zahra. From sorry. Environment. Okay. Okay. Negative flow in the use of hydrogen. So there is three questions for you. So the first question is: are there any negative effects on the environment following the use of hydrogen? It's a question from Saim.
Yeah, for negative effects for hydrogen, so we imagine that there is no negative effects if we use renewable energy for hydrogen production. So that means that we don't have any negative effects. That's because we use only water and to produce hydrogen. Using water splitting, using photocatalysis or using photocatalysis, I mean solar cell. And finally, we got only water. So so it is a cycle. It is a closed cycle that we use water and we get water in the end. So if hydrogen is produced from free carbon free, so it will be no effects, no negative effects. Okay, is that answer?
Okay.
Huh?
Okay, so thank you, Hind. There is another question from the audience for you, and okay, so how to protect? Okay, and okay, what is the subject? Okay, there is another question from Tessul Huda: how to protect the environment from the use of hydrogen? Okay, I think you already answered this question. And there is a question from Faisal Mehdi. The question is, what are the use of hydrogen energy in modern technology?
Another technology. So hydrogen, it can be used for transportation, for cars. There is hydrogen cars. There are some train using hydrogen. Actually, there are some trains that work on hydrogen in Germany. There is some there is a project that's called Observer that use hydrogen to travel around the world just by using only hydrogen. It's called Observer. So it uses for transportation, and also it can use it for stationary. It's because we can produce electricity from hydrogen. So all what we use now using the electricity, we can use it using hydrogen because we can produce the electricity from hydrogen. And also it's used for spatial application. And special because it's use cryogenic temperature, so actually it works for spatial transportation, and also some medical sectors due to the cryogenic temperature.
Okay, so thank you very much, Hind, for his answers. And Hamza Buhani is here with us. Are you here, Hamza?
Hello, yes, I'm here.
Okay, so welcome, Hamza, and thank you very much for the nice presentation. So yeah, I will check if there is any question for you.
Yes.
Okay. So I have your materials. Your thin films exhibit a lot. Okay. Sorry. So you hear me, Hamza?
I wasn't hearing you.
Okay. Okay. So if you look at your materials, the prepared thin films exhibit a large magnetic hysteresis, and in this case, the utilization of Maxwell equation is not appropriate. So in your look, how you managed this issue?
Regarding the hysteresis issue, I would like to mention that first of all, the hysteresis was considerable in the case of PVO thin films grown on STO substrates, but in the case of PVO on LSAT substrates, the magnetic hysteresis was largely reduced. Nevertheless, we have paid particular attention to the calculation of the magnetic entropy change using Maxwell relation, since there is some hysteresis effects. So for that purpose, we did some isothermal loops when measuring the magnetization versus the applied magnetic field. So after each measurements, we take the systems to a higher temperature to kill the magnetism, and then measuring the magnetization at selected temperatures once again. So in this case, we make sure that the remaining magnetization from previous isotherms is suppressed. So this ensured that the calculation of the magnetoentropy change is reasonably. Are you hearing me?
Okay, yeah, okay, so thank you very much, Hamza, for the answer. And just so you think that by applying, my second question is that you think that by applying strain effect in materials, regardless their natural scan, enhance the magnetocaloric effect in these materials, or this is specific for the material you study?
I think that this approach could be applied to other materials because, in fact, the strain effect is represented here by the selection of the substrate and also by the crystal orientation. Because growing material with specific crystal orientation, for example, for the case of PVO on STO substrate, our recent measurements demonstrates that the magnetization of PVO on STO when the crystal direction is 111, it's the magnetization is largely enhanced compared to the case of 001 oriented STO substrate. So the orientation plays an important role here, as well as the thickness. The thickness also plays a crucial role because for the case of PVO on LSAT substrate, we have grown 40 nanometer thick of I think, yes, 41 nanometer compared to 100 nanometer of PVO on STO. So in the range of over 30 to 40 nanometers, the magnetization is at highest levels.
Okay, so thank you very much, Hamza, for the nice answers. So now the session on magnetocaloric refrigeration is over. So thank you very much for attending this session, and I hope to see you next year in person. So I would like also to thank the organizer and particularly Professor Yusuf Zaz for the nice organization of this very interesting and outstanding conference on renewable energies. So thank you very much for your attention, and see you next year in person.
Thank you very much, Professor Mohammed Beli. Thank you very much for your colleague, Professor. Thank you for Professor Dinar Kushan. Now we close this session and we go to the next the last session today: wind energy, electric production, and grid integration. I don't know his Professor.
Well, Professor Zaz, actually, this is Shakib Alawi. I'm going to replace Dr. Bashirin by hosting this session.
Dr. Professor Rashid is there.
Professor Zaz, can you hear me?
Yes.
This is Shakib Alawi, so I'm going to replace him.
Okay.
For this session, okay?
Okay. Welcome. Professor Ali Al-Alawi, Shakib Al-Alawi.
Yes.
Yes, is from INSA Fez, INSA Euromed University Fez. You are welcome, and Go
Thank you. Thank you very much. Thank you very much, dear colleague, Yusuf Zas. So I am going to host this session about wind energy and its integration with the grid. For that, we have Dr. Nikita Christianis, who's going to give us a presentation. I would like to introduce Dr. Christianis, but I hope that I will do it right and give him some justice because he has a very rich and exceptional resume. So here I go. So Nikita Christianis is a doctor engineer in control systems from the University of Galati in Romania. Okay, he received a doctoral degree in electrical engineering from the University Le Havre in France. He's a professor emeritus at the University of Le Havre, Normandy, and the professor emeritus at the University of Galati. He's a former GUE 8, Global University 8 General Secretary. He's currently member of a European Association for the Development of Renewable Energies, Environment and Power Quality, member of IEEE France section, of IEEE Power and Energy Society in the USA, of EEA Club in France. He has been recently appointed the president of joint company called Normandy Interactive and Global Engineering Consulting. He is actually a research investigator in renewables and renewable energy, and he is a PhD supervisor in GREAH Lab, Groupe de Recherche en Électrotechnique et Automatique du Havre, France. So here we go. So Professor Nikita, I hope I did pronounce your name correctly. And so I give you the floor.
Hello, do you hear me?
Yes, we do hear you.
Yes, thank you very much for your invitation. You see me, I think.
We see you, yes.
Okay. I want to share my file.
Yes, there is a screen share in green, I think in the bottom right of your Zoom window. Écran partagé, if it is in French, as it is in my case.
Oh, j'ai bien compris, mais je n'arrive pas d'avoir la main sur ça. Le matin, j'ai eu désactivé. Bon, enfin.
Maybe you have to maximize the window or something.
Just a moment.
His name is Christian, not Christianis.
Well, I read, my apologies for the mispronunciation, but I read what
Don't worry.
What was written.
Christian Nikita.
Do you see my...
you can move your mouse to the top or the bottom, depend on the version of your Zoom. Move the mouse to the bottom.
Oui, but je ne vois pas.
Or on the top, move the mouse to the top. That after that the menu appears.
Oui, j'ai understand, but quitter la vidéo minimisée. Ah, ok. Perhaps here.
You are on Zoom screen.
I see you, but panelist, I have the participant. I have on my screen my PowerPoint, but
on the bottom, you move your mouse to the bottom. There are many choice. You choose the green button with region, share screen or partage écran.
Est-ce qu'il a la main ou c'est écran partagé?
Oui, mais je ne vois pas cette... Bon, je vais relancer encore une fois Zoom.
Je pense qu'il a la vue réduite. Il doit refaire la vue. Il doit agrandir la vue. You have a small view of Zoom. Click
Affichage,
on...
ah oui, OK.
Oh, yes.
Passer à mode plein écran.
You should switch to the full screen.
Écran partagé. Okay, I think you know, I think you have now.
We have now.
We have the full screen.
Now we can see it.
Now, please just switch to the full screen mode.
Okay. You have a screen now?
Yes, perfect.
Perfect. It's good.
So sorry for this misunderstanding, but in the morning I prepare the Zoom file. So hello everybody once again. Thank you very much for your invitation. So can I start my keynote?
Yes, please go ahead.
Okay, thank you. So I will present you this keynote modeling and simulation methods for optimized location and size of distributed generators systems. And I present also a little appendix about hybridization concept for horizontal axis in wind and tidal system using real-time emulation method. So this work is realized with my previous PhD student, Dr. Ahmed Alameri and Dr. Mohamed Ashglaf. As you know, I work in Université Le Havre Normandie, un groupe de recherche en électrotechnique et automatique du Havre, research group in electrical engineering and automatics from Le Havre. So just a little, I have a little problem. Just a little presentation about these labs. There are three research teams: electrical energy systems, operational safety of industrial systems, and one team that ties two previous related teams, renewable energy and systems. So the main field of research and application, smart grid, production of electrical energy from wind energy, tidal energy, photovoltaic fuel cell, etc. So some research axis in transport and real-time control for industrial application. So my speech will be structured in some steps. For the beginning, in the case of modeling and simulation method for optimized location and size of distributed generator system. So you see in the screen that I propose you some discussion of general discussion, not very long, about electrical power system, distributed generation. I will see with you the main research objective, what are the optimization methods, some results, and finally some idea about using real-time emulation, hardware the loop simulation, and our perspective and future works. As you know, for the power system analysis in the past decade, distributed generator DGs has become one of the fastest growing technology, and is expected that that development to continue. Interconnecting DGs to an existing distribution system is means to increase and fulfill the yearly electrical energy growth in demand. Distributed generator could provide various benefits such as power quality enhancement, loss reduction, voltage profile improvement. However, the planning and operation of distribution network are facing different challenge when more DG, distributed generator, is connected. The network planner should consider the positive and negative effects of distribution generators when an efficient network is designed with a high penetration level of DG. So therefore, why the optimal location, sizing, and type of DG can give guidance to designer on and the operator to achieve the performance of the grid. Finding the optimal size and location correspond to optimizing the operation and planning of electrical distribution network, taking into account capacity of distributed generators units as constraint. That's for right, accurate solution for optimization problem is more important to operating planning that also the time of calculation. On the contrary, near optimal speed up time calculation to solve the problem for operation can be useful also for DSO distribution system operators of real-time operation. That's for why, in addition to planning for size and placement of distributed generator required, the type of this kind of new sources must be considered. For example, wind energy differs for the other sources, and a large scale now of onshore and offshore wind farms could be give some problems that arise when these kind of sources for a high level of power to be in consideration. Because the improper placement of VFAR, for example, could increase the real power losses in the distribution system. This is the old problem about this. There is no, it's a problem. The problem that in the last year arrives, and that's why we try to find some optimization methods and for size and for placement of DGs in grid. That's why I present you some selected main methodology that we used. This will be a little complex because I selected that we consider the main technologies that could be used in this case. That's for why, for the beginning, we try to present you the scope and the main objectives of our works. The first objective is to explore the application of a number of approaches in the area of power system analysis. The second objective is to develop linear models suitable for the prediction of optimal distributed generator size. Since the active power has strong coupling with the voltage angle in the power system, we consider that the method called fast predicted linear model should be used to estimate the real power losses. Moreover, faster and acceptable accuracy calculation must be efficient tools for grid operator to assess the power system with the large scale DG connected. The third objective is to investigate the impact of DG size of, on a real power losses into grid. Since fast predicted linear model cause error in estimating optimal DG size, we must extend the methodology to analyze multi-DGs unit based on, for example, wind energy resources, as well as finding the optimal placement of each DG as a part of the future or actual network. The four objectives of our work concern the requirements for integration of DGs in the actual grid. And for this, we try to find optimal solution, global and local solution, a solution for power system integration. And it will be, if you want, the last part of the research objective to be accomplished. The final objective is finally to demonstrate that we'll can use the mathematical tools, very complex in mathematical tools, to find the optimal size and the location of this kind of new sources. So, for example, in this slide, we show that we can use the famous, well, we can say the sure complement. There's an algorithm that we tested with several IRSEC benchmark test system, and we compared the result with the Newton-Raphson method or fast decoupling method in order to find more time for computation, to give to the operators and to the people that manage this type of energy, to find with the command control unit the optimal solution. we introduce new in this approach what we call a new algorithm run length encoded that is extracted from representing data using meta files. So this method is proposed for to transform the dimension of the matrix very hard to implement and manage in computing in vector. So instead of two-dimension matrix, we will try to have a vector that could be managed more easier. Another method for optimization that we use in for integrating multiple distributed generator is to linearize the power flow and we obtain what we call the simplified power laws method. This is know this kind of simplification. So linear equation modeling will be used in our approach to simplify power loss calculation. This calculation, in this case, this calculation with simplified power losses calculation could accelerate the processes to predicate optimal DG size. So each location of DG at load basis has optimal size, and the objective of calculus will be minimum power losses. We also use, because this is a modern method, the genetic algorithm technique. We obtain good results. Two optimization technique we develop, local and global optimization, using also the linearized calculation for real power losses. This algorithm is implemented to find the optimal location and side for also for DG unit in the grid. For this, we develop our algorithm using the mathematical complex mathematical aspects is fitting formula and so on. We also use the anterior point optimization method in order to also to gain the memory, CPU memory, and time computing. And finally, we try to use the performance tools, that is the Kalman filter, that will be compared with another the previous element that I show you. So perhaps it's difficult to understand for the beginning our approach, global approach. We'll try to find what will be the mathematical tools to select the location of distributed generations, or the size of the DG size, the size of DG or distributed generators. So, for example, using the Kalman filter, the obtaining results show that the developed estimation method could save more than 60% of required execution time when compared to an existing method based in Newton-Raphson method. This time-saving advantage is achieved at the expense of only a small error in estimation, both the minimum power losses and DG size. I regard the time. So this is one simulation for the 5 IRSEC bars. So some results. So for example, here we tested the time reduction using the SURE method. SURE method testing in we've tested by 4 systems, and we compare the result with Newton-Raphson method and fast decoupling method that I told you before. The results show good accuracy with less memory and time. Here we have the results. Another results, we make the comparison results of iteration between, we can say in comma, normal and run length encoding method. So the number of iteration decreases. So we have what we call the time reduction for this kind of method. So results here that we see on the slide show the efficiency of RLE algorithm because we reduce consequently the iteration numbers. So we note also that the time required to implement this calculation is decreased, and in this case we can optimize the CPU execution time, and the number the calculation will be done with less memory. So in this slide we have different results where the distribution generator are located differently. For example, here we have 14 buses losses with different DG location. So and we could make this comparison with the linear method Newton using algorithm Newton-Raphson. So there are some difference that we'll see after this slide. That this difference, for example, the obtaining minimum power loss point of each DG placement represent here the optimal DG size. So we can, it can be noticed that the system behavior follows the system input. So the size of DGs. This comparison between Kalman filter and Newton-Raphson method could be interesting for the performance comparison for different locations. So we have two objectives where we can place the new farm, wind farm, and where and what will be the size of wind farm. It's important because we can fortunately we can compare with power losses. Another result, for example, here, results of optimal size and location of multi-DGs by genetic algorithm. For example, for this 14 I-third basis, maximum losses in line before DG is about 4.2 megawatt, and after placing DG is about 1.7 megawatt. So it's important to find the site and location it is possible in a real time. So for this, we must have more time for calculation of this complex element. The time, okay. Some word of impact, for example, wind farm in on electrical power with when we have also variable load simulation. Because the growth of electrical demand increased and the need of wind energy sources increased, but we must handle it. The size and location of wind farm is selected depending on the analytical model explained a little in my intervention here. We try to simulate 5 wind farm about 45 megawatt, and the results are very interesting here. Sorry. The results are interesting because for example, for the case of the 5-bus system, the fluctuation of the wind power output due to the wind speed variation could change the calculation of total real power losses within 30–40%. So in this case, the less computation time compared with the global optimization with genetic algorithm could give good results, like you see in this part of this slide. So where we have loss without farm and loss with farm, we see that if the location, the size is well done well, calculated, we can reduce the power losses. In conclusion, for this part, there are a lot of methods that are we propose in this work. So starting from linear power analysis and simplify loss model and using Kalman filter or genetic algorithm or interior point, so we can find fast GG size, global optimal location L size, and for the last cases, less computing time. That's for why it's a little complex to present directly this result. So we try to obtain some steps, step by step, to arrive for global and local optimal location, size also, and for multi-DG unit with a flexible constraints and with less computing time. So for this part, this work, evidently, that in this slide, I make a little resume about impact of distribution generated and wind energy into grid. There are some results. For this, in order to have validate this method, so we have online. We must have. We have to work with monitoring operation of grid. So we will try to make this algorithm with our colleague from one university in Romania, one university for Germany. So my iPhone said that I have 30 minutes. So there are a lot of things about this. For the second part, I make very quickly. It is possible?
Perhaps now, because you have just 2 or 3 minutes, if you can.
3 minutes. So some problematics of hybridization concept for horizontal axis wind and tidal system using a real-time emulation method. What is research? What objective you see here? We try to study what we call hybrid wind and tidal power generator system. So for this, we are based in the function similarity of wind tidal turbine horizontal axis. So we use what we called the concept of electromechanical coupling of hybrid wind tidal power system. We dared to have one idea with some colleague of Ina University from South Korea. As you see here, the principle of this concept is based on the integration of the mechanical torque generated by the rotation of tidal and wind turbine in the same transmission shaft. So you have, fortunately, the possibility to validate, and we validate the feasibility of this concept, electrically speaking, because this concept is difficult to realize from mechanical part. you know that we have in our laboratory, in Guerrero laboratory, what we call an experimental performance structure. Hardware is a loop simulation. And here you have this experimental platform that you have here the platform, electrical platform in our laboratory, and this side we have the little platform realized by our colleague from INA University. So the principle is here. If I have present you some results, yeah. So obtain it in experimental simulation. So we'll see that we can emulate two turbines. In the left side, we have wind turbines. Right side, we have tidal turbine, and we have camshaft with asynchronous generator, double feed asynchronous generator connected to the grid. So the results are obtained also with what we call in accelerated time, because the problem from the wind and the tidal sources, there are a lot of data, and we validate algorithm that allow us to decrease the number of data with evidently some errors in the output power, but we have these tools to realize finally for a little power rate this control strategy. So
please, Christian, if you could conclude.
So thank you. Thank you very much. And sorry for how many minutes?
Yeah, it's time, but we have some questions.
Yes, okay.
Thank you, Professor Nikita, Christian, my colleague. Effectively, we have some questions. I will go to the followers. Our colleague from Algeria, Adil Ghanayat, have the following question. Is there any material interaction factor or correlation that may include interaction between number of turbines in a farm?
Yes, there are surely the interaction of the wind turbine on in the frame of the farm.
Excuse me, Professor Rashid.
Yeah.
Yes.
You want to move the questions at the end?
Yes, after three presentations.
Yeah. After this quickly answer, we will move to presentation. Yeah.
Okay.
So there are. It is possible. Okay. So I'm waiting from the discussion to the end of the session.
Yeah. We'll move the discussion after the presentation of
three presentations. Only three
presenters. Yeah. We will move directly to next presentation entitled "Control if wind turbine based on DFIG to eliminate the imbalance in the electricity networks." It will be presented by Usama Malawi or Hamza Afol. I think Usama Malawi.
Good morning. Before starting, I am Oussama Malawi, a fresh graduate electrical engineering and a master's student at Centrale Supélec of Paris. So we are gathered here to discuss a paper entitled Control of Wind Turbine based on the doubly-fed induction generator to eliminate the imbalance in electricity network. Here is the summary of this presentation. In general, the introduction of wind turbine in an electrical network does with respect to the active power that it can inject. How can we look at the wind turbine on the one hand in relation to maximum power that it can inject, and on the other hand to eliminate the imbalance electricity in network. The imbalance appears if the phase or amplitude conditions are not verified, and it is generally due to the imbalance loads. The consequences are overheating of the equipment, degradation of electrical insulation, reducing the life of the system. So one of the solutions is to involve wind farms in eliminating this imbalance. Due to the high demand of electrical power and to protect the environment from greenhouse gas emission, the use of fossil fuel must be limited. It is essential to move toward renewable energies. Wind energy has experienced a very rapid development in the recent decades. This is why we're going to interest to this renewable energy. There is two types of wind turbines, vertical and horizontal axis. And the horizontal represent more efficiency. The technologies, there is a fixed speed wind turbines and variable speed wind turbines. The advantages of this energy is clean, friendly, renewable, sustainable, and profitable. The disadvantages are the noise and the inconsistency of the wind profile. So the doubly fed induction generator, at its name suggests, this machine can be powered by two different sources. The stator is generally connected to the network, while the coupling of the rotor can be done in several ways. This machine can reduce the volume and the cost of converters, reduce the losses through the converters, improve system performance, and independent control of active and reactive power. The vector control. To simplify the representation of the doubly fed induction generator, we represent the stator and the rotor by three windings offset by 120 degrees from each other. These are the general machine equation of the voltage and the flux. The transformation of power causes the flow of the flux to be oriented along the direct axis only. So to control the active and reactive power of the stator, we must act on rotor currents. The vector control based on the orientation of the flow of the stator allow an independent control of the active and reactive power. The machine side control. Knowing that to control the stator powers of the doubly fed induction generator, it is necessary to act on the component of the rotor current according to the axis Q for the active power and according to the axis D for the power reactive. The simplicity and the speed of setting up while offering a good performance are advantages of the proportional integral. This is why we're going to use PE correctors to control the currents of the doubly fed induction generator. For the grid side controller, by applying the parks, the quadrature axis current is used to regulate the voltage of the bus, the DC bus, and the direct axis is to regulate the reactive power. The currents are controlled by two PE correctors. The PQ theory is used to calculate the active, reactive, and imbalance component. This theory is based on the instantaneous power defined in the time domain and which rely on the Clark transformation to make the passage from the reference mark ABC to the reference mark alpha beta. Here is the simulation model that we used, and here are some of the results. Here is the loads imbalanced. The loads are imbalanced, but the wind power system is able to eliminate this imbalance. Here, the current going out from the CCR follow the reference to eliminate the imbalance. The DC voltage follow its reference and remain constant. The spikes of the current here are very harmful for our transistors. The coefficient of performance remains almost constant and reach its maximum with a very negligible error in negligible. The stator current injected in the network proportionally the profile when. Here is the discussions we just saw. and this is the conclusion, it can be concluded that the MPPT method is able to control and eliminate the imbalance over a wide range of parameter change. The control target for the entire wind energy system have been met. At the end of this work, perspectives of application of the MPPT and the predictive control on other systems are considered. The limit of PE characters to meet the requirement and desired performance during the transit regime of the doubly fed induction generator, and try to replace them with other characters that are more performant and more robust. Apply the predictive control on the 3-level MPC converter and expand this control to handle different objectives at the same time and find the link between them. So at the end, I would like to thank you for your attention.
Thank you, Mr. Usama. We move directly to the following presentation, which is entitled Effect of Filtering on the Quality of the Energy Produced by a Wind Power Conversion Chain by Aisha Wahabi et al. Are you here?
Hello, Honorable IRSEC 20 Organizing Committee. I present this study to you to show the effect of passive filtering on the quality of the energy produced by a wind energy conversion chain. Objective. The objective of this work is to study the effect of RL filters on the performance of a variable speed wind power conversion chain. Problem. Thyristor, TRIAC, etc. have enabled the higher power development of the wind energy, but these components, as we know, cause energy pollution. Method. For this, we have created a model of the whole chain. Then we compared the performance of the transmission before and after using the filter by using MATLAB simulating software. Description of a wind energy conversion system with a doubly fed induction generator. The wind chain generally includes the turbine, the multiplier, and the DIFI-IG, whose stator circuit is directly connected to the network. A second circuit arranged to the rotor is also connected to the network via power converters. Here we show that the kinetic energy of the wind is captured by the turbine, then transformed into mechanical energy, which is transmitted to the generator through the multiplier. Finally, the generator supplies the electric energy to the network or the electric load. Improvement of the efficiency of a wind power chain driven by a DIFI-IG by adding RL filters. To carry out this study, we modeled and simulated the entire wind energy conversion chain. We obtained the following diagram. After the model of the complete conversion chain after adding filters RL is as follows. Simulation results. After some adjustment, the system worked correctly. We will be particularly interested in the voltage at the DC bus terminal because it is a good indicator of the power transmitted. Comments and conclusion. According to this study, we see that the addition of filters effectively improved the quality of the DC base voltage. The reactive power, which is an indicator to the efficiency of the chain, has increased also. Our model can be refined by inserting voltage and power regulation loops in order to minimize the fluctuation. Thank you for your attention.
Thank you, Mrs. Aisha. It was very clear. Now we move directly to the next presentation, which is entitled Control of a Wind Energy Conversion System Based on DFIG Using a Fuzzy Hybrid Controller in Case of Wide Mechanical Parameters Uncertainties. It will be presented by Nabil Dahri or Mohammed Usaid.
Hello, it's a pleasure presenting to you my work on the control of a wind energy conversion system based on a doubly fed induction generator using a fuzzy hybrid controller in case of wide mechanical parameters uncertainties. In this presentation, I will proceed following the present outline. First, I will explain the motivation behind working on a robust controller to overcome mechanical parameters uncertainties. Afterward, I will describe the fuzzy hybrid controller proposed. Then, I will present the simulation results, in addition of comparing these results with other controllers proposed in the literature. Finally, I will conclude the presentation. In response to the rising requirement for energy, a lot of studies have been done to improve the efficiency of the wind energy conversion systems. These studies have found that for each wind velocity, there is a specific generator angular speed in which the maximum mechanical power is extracted as it is shown in the figure in view. The specific angular speed at which the generator must rotate is calculated by the maximum power point tracking algorithm. Hence, a suitable controller is needed to regulate the generator's angular speed depending on the reference value delivered by the MPPT algorithm. The majority of controllers need a complete knowledge of systems' electrical and mechanical parameters for good control performance. However, some degree of uncertainty almost exists in the approximation of these parameters value, whether from an inaccurate approximation or from the aging of the system's components. Few research have been done to deal with mechanical parameters uncertainties. Moreover, some of robust controllers proposed in the literature to
السلام
overcome
عليكم.
parameters uncertainties have noted
سليمان
that a
محمد.
number of these controllers suffer from a persistent chattering
سلام كيراك بخير. قول لي واش عطيتك ان دوكيمون باش
overcome wide
يتبعوه الدراري
mechanical
ولا؟
parameter uncertainties with better performance in terms of time response along with the elimination of the chattering problem. General form of a controller of wind energy conversion system based on a doubly fed induction generator is a cascade of two subcontrollers, an external and an internal controllers. As we are dealing with mechanical parameters uncertainties, the internal controller will be replaced by a PE controller, while the external controller will be replaced by a fuzzy controller that is an intuitive and robust controller, totally independent of the system's parameters. This is the complete control system. The fuzzy controller has two inputs, the generator's angular speed error and the rate of change in the error. The output of the fuzzy controller is the amount of change in the electromagnetic torque reference. Each of the two inputs and the output has 5 fuzzy sets. The table in view resumes the different fuzzy rules linking the inputs with the output. Simulation of the proposed controller is made in MATLAB Simulink environment. A comparison in the performances of the fuzzy hybrid controller, the classical PE controller, and some controllers presented in the literature is done in this section. 3 simulations have been done. In the first one, the moment of inertia and the viscous friction coefficient are kept to their nominal values, while in the second one, they are increased from their nominal values by 20% and 60% respectively. And in the third one, they are decreased from their nominal values by 40% and 60% respectively. The controlled angular speed in the first simulation is presented in the figure in view. In nominal conditions, the proposed controller is 3 times faster than the classical PE controller. The controlled angular speed in the second simulation is presented in the figure in view. As we can notice, there is no persistent chattering in the angular speed. In the conditions of the second simulation, the proposed controller is 3.5 times faster than the PE controller. The controlled angular speed in the third simulation is presented in the figure in view. As well, there is no persistent chattering in the angular speed. In the conditions of the third simulation, the proposed controller is 3.6 times faster than the PE controller. To evaluate better the performance of the proposed controller, a comparison has been made with H infinity and Cron controllers presented in the literature. The fuzzy hybrid controller is found to be 5 times faster than the H infinity controller and 3.3 times faster than the Cron controller. To conclude, the fuzzy hybrid controller proposed is a robust controller and sensitive to wide mechanical parameter uncertainties. It is characterized by its faster response and its ability to eliminate the persistent chattering from the quantity control. Thank you very much for your attention.
Thank you. Now we can move to the questions. I have a list of questions. If we take, for example, a question from Selma Ilhadi. She has a question to Mrs. Wahabi. For amelioration of reactive power, are you talking about the reactive capability of the machine, and if it's the case, how it's possible? Salma Ilhadi, you are here? You hear me?
I hear you, but the presenter, I don't think that.
No, not Salma Ilhadi. Wahabi.
I'm here. Hello.
Aisha Wahabi, you hear me?
You hear me?
Yeah. Can you answer the question, Aisha, or you want
can you repeat, please? Can you repeat, please?
Yeah, yeah, I will repeat.
The question?
Yeah, for amelioration of reactive power, are you talking about the reactive capability of the machine, and if it's the case, how it's possible?
No, no. I'm not talking to the reactive power. Je peux parler en français, s'il vous plaît?
No,
Yes.
no, the conference is English.
It's different. I am talking to the reactive power about the bus, the DC bus, not for the asynchronous machine. It's different. It's very different. It's clear?
Yeah. I think we will move to another question. The same from Salma Ilhadi too. And the question is to Malwi, Mr. Malwi. Are you here? Are you there, Mr. Malwi?
Yes, I am here. Can you hear me?
Yeah. Why are you usually using PI corrector instead of PID correctors that are more performant?
So for this question, first of all, I would like to thank you for this organization. So it was well organized. And for the question, so I wanted to say that we use the PE corrector because it's more efficient and it have like just 2 parameters to identify, so which is like easier to implement in our work here. So which is gonna give us the static error, which is the 0, and this is what we are looking here to just at the outside of the inverter, we must like make the signal, the current which going outside, like following the reference, and the PE corrector will give us this performance without needing to do the PED correctors.
Unfortunately, we can't hear Selma Ilhadi. Perhaps if she can talk to us, she could give us their idea about the answer. We have another, yeah?
Yeah, I allow her to talk. Salma Ilhadi.
Salma Ilhadi, yeah? What, you have any remarks about the answer?
Hello, could you hear me?
Yeah.
So for the answer, yes, it's clear. So I have an idea why, because I have usually a question why these are PI correctors who are which is used and instead of PID correctors, but he has told me the answer. I got it. Thank you.
Thank you too. It's okay. Another question from Salma Ilhadi to Professor Christian Nikita. The question is,
I am here.
How do you take into consideration the intermittence of wind energy and the capacity of the penetration of grid that matters for this kind of energy, as well as complements and losses? I think three questions.
It's finally in my keynote, I highlighted this your question. The question is the response is very complex because we know about the income all time that a new generation of the energy in the node of grid could be planified for the conventional energy. For tidal and for wind and tidal farm, we can also for the high level of power planify the location, for example, in function of the wind potential or tidal potential. But it's important, it's a new challenge now. It's important to have a optimization of this a new. I dare to say a new challenge for to obtain more energy from renewable. So for this, it's mandatory to find what is the level of power to include in the classical grid and where we can connect this power. So I respond, I think, your question. The level and of power and the size of the wind farm and the location is very important now because the power is important. We can, in France, we have, like in Morocco, we have a lot of wind farm with the level of the nuclear unit power. So this is a new challenge, difficult to realize because time to time to connect in the right place wind farm is not all the time possible. So if not, we can have less power obtained from wind farm or tidal. So that's for why we try to find new methodology to obtain where is the local and global location and what will be the size, corrected size, to minimize the power losses, active power losses.
And for Christian, and for losses, have you taken into account the effect of losses?
Effect of
losses, les pertes.
Yes, yes, sure.
Mm.
Sure. The losses, we can calculate the losses in function of the running of the point of operations. So yes, we can, because there are the losses of the electrical generator. It's important. So if we have a 40 or 100 generator, we can have important losses, but we can with difficulty to calculate, because the variability of the wind, it's the variability give different level of electric generators losses. So that's why we can have a tolerance for the big farm. I respond to you for the first question that you asked me. There are evidently effects if you have a lot of wind turbine in the same place, but if you have plenty wind farms, this effect will be decreases, because the losses of losses corresponding of this the losses corresponding of a lot of turbine will be less. That's for why we propose also time to time to configure it. It is possible, if it will be possible. There are some results about this, to combine, to have a hybrid system, wind energy and tidal energy, because probabilistically speaking, there are one chance to 1,000 to have the lack of wind or the lack of the tidal variation. That's why we can complete when we have no wind, we have tidal, and vice versa.
You think they are complementary? It's yeah.
Yes.
Mr. Ismail Droghi, why have you choose the hybridation of tidal and wind and not PV, for example? I add my question, if your study will be correct for hybridation wind PV, for example.
Yes, there are hybrid system with photovoltaic, with another source, because the wind farm offshore, the installation of wind farm offshore is made on the offshore platform, very expensive. So we are thinking that we could utilize the same platform to have one wind turbine, and in the water a tidal turbine. It is possible. So the mechanical structure of the platform could be utilized for two sources of energy, wind and tidal. That's why we try to develop this concept of what we call perhaps a little complex electromechanical coupling of wind and tidal turbine. It's there are some realization in Japan and some experimentation in South Korea. So we plan to develop with this colleague another hardware in the loop simulation bigger of corresponding of the 10, 20 kilowatt.
I have a fundamental question. What's the main criteria you use for optimization the DG location? What's the first criteria you use to optimize the location of DG? For optimizing DG, it's distributed generators. Distributed generators. What's the main, the first criteria you use? It's economic or technical, or it's an economical criteria or technical economy criteria?
No, it's a technical.
Ability, for example,
technical criteria, and we try to obtain more time with the performant algorithm, more time to calculate, to compute, and more time. It's is the it's millisecond, 1,100 millisecond. So, but for the operation is the classical grid, in order to substitute the problematics of the variability of wind turbine, you must give the time, more time, to older classical sources to complete the balance of the production and the load, because there are two, but there are two variation. This wind variation and low load low variation. In the classical algorithm, if I say classical algorithm like this, in the classical studies, so we consider that the load is constant. Now the load is not constant. We considered also that the sources are controlled without variable parameters like wind, for example.
Intermittency.
Okay.
Thank you.
I completed my response to your question, Rashid, with the three presentations that I estimate that are very well point the wind energy conversion. If I allow me, I can say that the free presentation could be the results could be made together, because the first presentation eliminate the imbalance of the electricity network. The second improves the filtering of
harmonics
conversion, and the second introduce fuzzy for the control. I have a question for all the three intervening. If you want to respond, you consider for your approach, because there are some common element, the same generator. You considered, I think that the grid, the network is perfect. There are no disturbance in the grid. So as I say, donc, because there are the important impacts of grid disturbances to double feed induction generator. So will be interesting to see what are impact of the grid to the generator and the wind system. This is a new challenge. It's a new challenge because we consider that the grid is perfect. The grid is not perfect. Maybe
we will discuss after because I want to place a question for Aisha Wahabi. Are you hear me, Aisha Wahabi?
Hello,
Do you hear me?
Yes.
In your DC bus voltage,
Yes.
Voltage reaches 0. Is it normal? In the car,
yes.
I remarked that the voltage becomes null, becomes 0. Is it normal?
I think it's normal because there is more fluctuation included by the converters.
But I think you have capacities and you have regulation now.
No, there is no regulation.
For DC bus.
No, there is no regulation. There are the filters. I have the filters, mais avant l'onduleur et le redresseur.
It's a question to study because it's perhaps little abnormal to have 0 on the DC. It's like a short circuit.
Perhaps in the case, Aisha, perhaps in the case we is a little time, a very little time that you connect the left side and the right side of your electronic power electronics. So time to time we can have this zero connect.
Circuits. Yeah. Thank you.
Yes, I think.
Other persons, have you another question?
To have this.
Yeah.
But
followers and panelists, if you have a last question before we move to the second list of presentation.
No, I have no other questions. Thank you for invitation. Thank you for your presentation, and I hope to see you and I hope to work with you if you need some idea. Thank
you. Surely we will be in touch. Thank you, Christian, for your presentation, for your participation. And to save some times, we will move to the next presentation, which is entitled Multi-Objective Particle Swarm Optimization for Controlling Active and Reactive Power in a Wind Energy Conversion System.
Okay.
Mustafa Shatwani. Are you here? Mustafa Shatwani, Yusuf Errami, Abdullah Taif Ubadi, and Ismail Sahnun. If you are not ready, we can move to the next one. Alors, Mustafa Shatwani or Yusuf Errami or Yusuf or Abdulatif Ubadi or Ismail Sahnun. Have any one of you heard me? We will move to the following presentation, which is entitled Control of the Wind Turbine with DEFI Connected to the Grid by Sabra Ahyatan Jalal El-Bahawi. Are you hearing me? Sabra Ahyatan or Jalal El-Bahawi? Now we move to the next presentation, which entitled Application of the Contact Net Protocol for the Movement of Agents in a Smart Grid Containing a Wind Farm. Ikram Saber and Mohammed Busta, Karima Al-Hamoumi.
Hi, Dr. Rashid.
Yeah.
I am here.
Mister, you are Mister?
Yes, I am here.
You are Mr.
Shtwani Mustafa.
Shtwani Mustafa.
Yes.
Yeah. Donc you have a presentation to
Yes, ID 9004. 904.
Perhaps I want.
I think that you will be
Yusuf Zaz, Professor Yusuf Zaz. Professor Yusuf Zaz.
We will launch it. Please wait for a moment.
Attends, IRSEC conférence, IRSEC support. Attends. We have
Okay.
Al-Mustafa Shtwani.
Okay, thank you.
You can present your presentation.
Shtwani Mustafa, I'm a PhD student at University Shuaib Dukali in Jadida, Morocco. This work is about multi-objective particle swarm optimization for controlling active power in wind energy conversion system. Our work is organized as the following structure. First, I will start by an abstract containing the problematic, and the second point, the equations modeling the wind energy system are established. Third, the indirect control vector scheme is designed. Fourth, the particle swarm optimization is established. The fifth point is about simulations and results. And finally, I will conclude by a brief summary of results and some perspectives. The objective of this work is to maximize the extracted power by MPPT and to control the active and reactive power of a rotor side converter for defeat by applying the indirect vector control. However, this control shows its limit performances when the parameters of the generator change. For this task, we suggested the multi-objective particle swarm optimization. Here shows one of the existing configurations of the wind energy system based on the fig. As you can see, the generator is driven by a wind turbine through a gearbox to adapt the slow rotation speed to a high rotation speed of the fig. The stator is directly connected to the grid. However, the rotor is connected to the grid via two bidirectional converters, the rotor side converter and the grid side converter. To model the wind turbine, we should define two important quantities, the produced power and the rotation speed. So the generated power is defined by equation 1, where Cp is the power performance coefficient and is expressed as equation 2. This coefficient is influenced by beta, which is the pitch angle, and lambda, which is the tip speed ratio, and is expressed by equation 3, and the rotation speed is expressed by the dynamic equation 4. These stated equations are used to model the wind turbine as shown in this figure. The equations 5, 6, 7, 8, and 9 are obtained by Park transformation, and they are used to model the generator. Maximum power point tracking is generally based on two strategies, the MPPT with regulation of the rotation speed and without regulation of the generator speed. At Cp equals Cp max, we define TSR optimal, for which we impose electromagnetic torque Tm equal Tm optimal as shown in equations 10 and 11. The expressions of the used PI controller gains are given in equations 12 and 13, and this figure shows the MPPT strategy. Vector control has two strategies, the direct and indirect control. In this work, we use the indirect field-oriented control. To control the active and reactive power, we suppose that the stator flux is constant and oriented according to the d-axis, and the stator resistance is neglected. By considering this hypothesis, the active power is controlled by the quadrature rotor current component, and the reactive power is controlled by the direct one, as shown in equation 18. Control powers, we should control the rotor currents as presented in equations 19 and 20. For this task, we use two PI controllers where their gains are computed by poles compensation and are expressed as shown in the equations 23 and 24. This figure shows a screenshot of MATLAB Simulink, which is designed based on the previous equations. The velocity of each particles is expressed as equation 25. However, the position of the particles in multidimensional space is expressed by equation 26, where W is the inertia weight factor and is expressed by equation 27. However, the other parameters are defined as below. To design the PSO controller, we define the fitness function as the weighted sum of errors as shown in equation 28, and we use the integral absolute error performance criterion as presented in equation 30. This figure shows the PI controller with PSO. The steps of searching procedure of PSO summarized in the following flowchart. This figure shows the mechanical speed of the wind turbine computed by two techniques. As you can see in the below figure, the response time is ameliorated by PSO. This figure presents the stator active power, and the below figure shows that the response time is reduced from 10 milliseconds to 17 milliseconds, and the static error is improved and is very close to zero. It is the same for the reactive power. The time response is ameliorated and the error is also improved. The below figure presents an unit power factor computed by the two techniques. To test the robustness of the proposed control against parameters variation, the resistance and inductance rotor are changed by 100%. It is observed that the PSO presents better robustness than the classical PI. Finally, these listed objectives are achieved, and we have observed that the PSO techniques reveals better performances than the classical PI. As perspectives, we can establish another technique and compare it with the PSO and study the grid faults. Thank you for watching.
Thank you, Mr. Mustafa Shtwani. Now we will move to the next presentation, which is control of the wind turbine with defect connected to the grid by Sabra Ahyatan Jalal El-Bahawi. Donc, you can present your work.
Ladies and gentlemen, hello everybody. I'm Sabra Ahyatan from University Abdel Malik Saadi Faculty of the Science, Tétouan, in Morocco. It is a pleasure to be with you at the 8th edition of the IRSEC 2018 conference. So my presentation is titled When the DFEG Control of the Wind Turbine Connected to the Grid. First, we will start with the scope and the motivation, then the introduction, stand-alone wind farm system DFEG modeling, after simulation circuit and the results, finally the conclusion and the perspectives. We made a study on the dynamic behavior of the DFEG characteristic analysis and the effectiveness and optimal performance to access the impacts on the output variable of the wind farm contain many wind turbines. 4. Evaluate the capability and their impacts for the pitch, angle, currents, and voltage stability of the double-fed induction generator. If we take a step back from the environmental state of our planet, one thing quickly became clear. The majority of the world's problems are in fact energy problems. The depletion of the fossil fuel pollution, ever-increasing population growth, growing demand for energy accessibility and application in modern electronic power converter have paved the way for the maximum use of the renewable energy source worldwide. The development of this resource, wind, solar, marine, hydro-biomass, in modern power generation system has increased exponentially due to the emission mainly from the combustion of fossil fuel, oil, gas, petrol, etc. Their consequences are very harmful for our planet. The purpose of this research to focus on the DFAG generator for have an exact view of distribution and the degree of fluctuation presented in the pitch angle current and voltage curves. The production of the electricity from conventional energy source is a major source of the greenhouse gas emission leading to the global warming. Dynamic model for a DFEG wind turbine can be indicated in the term of the equation of a P system. The stator winding is connected directly to the grid, while a bidirectional power converter feeds the rotor winds, allowing variable frequency operation and the rotor currents. This power converter is made up of two back-to-back IGBT bridge rotor side converter or SC and grid side converter or JSC, linked by the DC bus. The wind turbine is also equipped with the blade pitch angle controller that limited wind power capture and rotational speed for the high winds. The system mechanic contains of the drivetrain and the aerodynamic rotor. The model of the rotor expresses the mechanical torque extracted from the wind defined by the actuator disk theory. This torque is transmitted to the DFEG rotor throughout the drivetrain. Is represented by the well-known two masses model. In our model, two rotating mass, the aerodynamic rotor and the DFEG rotor are elastically connected via Springer characteristic by the stiffness and the damping factor of the decoupling. The four equations are indicated in the direct D quadratic Q for the stator voltage coordinated motion from the term synchronous speed, where U represents the voltage, E represents the current, W represents rotating speed, fluid the dynamic magnetic flow, R represent resistance, and L inductance. Indexes D and Q stand for the direct and the quadratic components, and the indexes S and R refer to the rotor and the stator respectively. PW is expected power from the wind, Rho is the air density, F the blade radius, and the omega beta is the wind speed. Cp is the power coefficient and is given as a non-linear function when the parameter tip speed ratio. Lambda is the blade pitch angle. Beta is the calculation of the performance coefficient required the use of the blade element theory. The model is based on the DFEG consists of 8.15 megawatt wind farm wind turbine of 12 megawatts connected to a 25 kilovolt distribution system export power to a 12 kilovolt grid. The schematic represents and analyzes the simulation 1 over a period of 16 seconds, and by showing the graphs of the pitch angle, active power, and the DC link capacitor voltage and the current of wind turbine. Most of the variables of interest stated above are represented in the PU value, where the base power is nominal power of each wind turbine. From the figure 3, the pitch angle starts to oscillate right after the distribution. Nevertheless, it can be seen the oscillation decays after 5 seconds, and the system is stable. However, the rotational speed decreases as well to a value below 1 pu, which means the generator rotor of the wind turbine doesn't rotate and its rotated value anymore. The behavior shows that the rotational speed is highly dependent on the wind power. From figure 4, can see that the DC link capacitor voltage show small fluctuation on the rotor active power and output power caused by the wind speed variation. It also remarks in the figure 5 and 6 that the wind farm VEBC voltage and the EBC current is the sum of the voltage and the current of the wind turbine. That means that the grid source converter is controlling wind farm DC voltage by maintaining it to set a constant value and also accusing the active power exchange from the generator to the grid. The results show the dynamic failure of the DFEG ensure the electrical distribution with the wind in terms of the grid voltage and the frequency fluctuation. On the other hand, it shows also use a view on the wave over obtain the study on the dynamic behavior of the DFEG characteristic analysis and its effectiveness and optimal performance to access the impacts on the output variable of the wind farm contain many wind turbine, which means that the adequate study for choosing the type of the control suitable of the DFEG is necessary. The continuation of the purpose of this research is to make investigation for a new type of control suitable for the DFEG control based on a new hybrid system, and the simulation of the intelligent control system will be improved and energy management among all the components of the
Encore
hybrid
demi-heure.
can look at for the references. Thank you for your attention.
Thank you, Mr. Sabra Ahyatan. Now we will move to the next presentation entitled Application of the Contact Net Protocol for the Movement of Agents in Smart Grid Containing a Wind Farm, Ikram Saber et al. You can present your work.
Hello everybody, I am Saber Ikram, a PhD student from ESTFS, TSI Laboratory, and I am thanking you for giving us the chance to present our work entitled Application of the Contract Net Protocol for the Movement of Agents in a Smart Grid Containing a Wind Farm. The plan of our presentation will start with an introduction, a smart grid definition, multi-agent system definition, contract net protocol applied to wind production, simulation of our work, and the conclusion. The traditional main power grid has served humanity for many years, but as is known, it presents many failures due to its complex infrastructure, unpredictable disaster, industrialization and urbanization, as well as other problems. The reasons to invest in renewable energies and to build intelligent electricity grids as the smart grid. And when we say intelligent, we mean about all the management, which must be robust, independent, as well as distributed, things which present the main characteristics of multi-agent system. In our presentation today, we will present an application of contract net protocol based on multi-agent system to manage the movement inside a simplified smart grid containing a wind farm. So, when we talk about a smart grid, we talk about a solution for reliable integration of distributed energy resources and resilience issues, also defined in American literature as a group of interconnected loads and distributed energy resources implemented with other power supplies in an intelligent and secure manner. And when we talk about a multi-agent system, we talk about a compromise between at least two independent agents having information allowing them to achieve an objective or autonomous decision-making entities. They are known for their ability to react in the environment, their intercommunication within the network, and their great autonomy. In addition, multi-agent systems are known by collecting information about neighbors and their status using their own skills, knowledge, and the amount of data they can access to. The contract net protocol is a technique invented to solve communication problems in distributed networks. It is applied to microgrid of all types, and it gives very good results on the cost side and management and speed of data processing. This protocol is applied essentially to perform negotiation tasks while using exchange messages in a bidding process illustrated in the figure opposite. In this protocol, the agents can play two roles, a manager or a bidder role. So, the initiator is the manager who is occupied by commissioning a task or demanding a service, and the participants are the bidders, who are the elements of the network which can collect managers' call of proposals and make them proposition depending on the call nature, and their answer can be a success or a collapse. As we mentioned before, our smart grid will be a wind farm, and every node in our network is representing a wind turbine. Agent's role will be to forecast energy production in every wind turbine. To ensure this responsibility, agents have to move freely and easily inside the wind farm, which is the main objective of our work. In our program setup, we use 6 main scripts: the agent scripts, the smart grid scripts, which represent the wind farm, the initiator script, which is the manager, the wind turbine script, which represents the main tasks, the simulation scripts, and the experiment scripts. Considering our Python implementation of the contract net protocol, it consists of classes which are respectively the smart grid, wind farm network, the wind turbine, the agent, initiator, and simulation. Our scenario is developed to test the version of the contract net protocol for agents movements between wind turbine inside a smart grid network containing a wind farm. We choose to use in that scenario two agents that can move freely and easily inside a wind farm between three wind turbines that are memorized in the beginning toward another wind turbines that are memorized at the end. So he can use his special order priority and his speed to spread the movements inside that wind farm in the opposite order of his priority. The main objective of that is to show the capability of every agent to bid and contract for the movement to forecast for every wind turbine. The grid extracted from our simulation illustrates the initial positions of the agents and the wind turbines. We choose a network wind farm of 5 rows and 5 columns, 25 wind turbine. This is the grid extracted from our simulation. All the nodes are respectively wind turbines, and for the first positions of our agents, there are 0.0 for the first agent and 4.0 for the second agent. Considering our wind turbines, we will start with the one in the position 0.3, the second is in the position 4.3, and the third is in the position 2.2. As for the agent, they have to move to these wind turbines and to another ones depending on our script. This is the table extracted from our simulation of the program. So as we can see, in every simulation step, our agents could provide mini movement to move between the first three wind turbines that we talked about previously and the other ones, depending on the need of the forecast of the production of the energy in each and every moment inside our smart grid. The simulation of our work shows that the bytes are very clear and separated from each other, which explain that the speed, capacity, and rest time for every agent is respected in our scenario, and every byte comes at a specific time and don't collapse with another. This property is very important of good work of a smart grid. Our application of the contract net protocol for the movement of agents in a smart grid containing a wind farm has shown the ability of agents to manage objectives and accomplish tasks as moving to forecast energy production inside a wind farm, which means that the agents are independent and intelligent and have a well behavior to manage a movement between wind turbines. Thank you for your attention.
Professor Rashid, turn on your mic, please.
Thank you. I was speaking without mic. Thank you. This is Ikram. Now we will move to the last presentation, which is entitled Type 2 Fuzzy Logic Control of the Double Feed Injection Generator Wind Turbine by Mr. Riyad Rabi, Salim Guerrero, and Abdelghafour Harzani. You can present your work.
Hello, my name is Riyad Rouabhi from University of Msila in Algeria. Today, I have to present my work with the title Type 2 Fuzzy Logic Control of the Double Feed Induction Generator Wind Turbine. The plan of my work starts with preface, problematic, and objective. Secondly, modeling of the double feed induction generator and their converter. Thirdly, type 2 fuzzy logic controllers. After simulation, then results. And lastly, we finish my work by conclusion. As preface, the increasing of the consumption of electrical energy with fossil fuels, for example oil and natural gas, has traditionally provided adequate costs, and this results in many problems such as the crisis of energy and more recently climate change. Several countries are increasingly turning to the use of clean and renewable energy sources. As a result, wind power appears prominently among other forms of renewable energy, not as a replacement for conventional resources, but as a complementary energy to the traditional energies. Wind energy is not degraded. It is an energy that produces no atmospheric release or radioactive waste. As problematic, the importance of wind power generation has led people in the field to conduct extensive research to improve the efficiency of these systems through better energy transfer and good quality of energy produced through the choice of optimal system architecture and adequate control techniques that will be able to compensate for the effect of parametrics and external disturbance in the system. The objective of the work is, firstly, to present the modeling of the synchronous machine with the double power supply and their converters. After synthesis of nonlinear control law with improved performance in the field of wind energy conversion, and finally present the simulation results obtained when applying this command on the system that is driven at fixed speed. The electrical stator and the rotor equation and the power equation impacts from of reference are given as follows. After the mathematical development, we obtain the stator model in the matrix form as follows. Variable speed, when the power conversion system based in ADM require that use of stator converter that power the machine rotor. The main objective of this converter are to wave the voltage of the DC bus to supply it to the rotor winding and to allow the application of commands to control the power generated by the stator of this machine and inject them into the networks. Type 2 physiological controllers, we have a good quality of electrical energy produced by a wind power system based in double feed induction generators, and it is an attractive solution to achieve high performance results in variable speed wind power conversion system based on the DR power synchronous machine. As simulations, to apply this command to our system, we use the same indirect vector control structure without power loop with a change of PI regulators by fuzzy regulator type 2 of the same types. As results obtained by the simulation clearly show that the type 2 fuzzy logic control always allows perfect decoupling between two components of the stator power, active and reactive, and we also obtained that a good tracking precision of this power generated at their desired values. And we also obtained that a good tracking precision of this power generated at their desired values. As conclusion, the aim of this work concerns the steady modeling and control of wind energy production system. For this, a modeling of various components of the system was carried out. These models have been used for the development of several control techniques to ensure precise and continuous control of the stator power generated while guaranteeing stability and speed of tracking with zero static error. This results in high system efficiency and optimal production quality. As a research perspective, we consider firstly the possibility integration of storage system and the technical and economic optimization of conversion chain after the study and application of other higher level converters such as 3 and 5 levels. And finally, establishing a model of the double feed induction generator taking into account the magnetic saturation. And thank you for your time and attention.
Thank you, Mr. Riyad Rohabi. Now we will move to discussion. From a question I read on the list, we have a question to Ikram from Abdelbari Ardwan. The question is, can you explain what will the agent? Ikram, you hear me? Ikram, do you hear me?
Hi, I am hearing you. Do you hear me?
Yeah. The question is,
Yes.
can you explain what will be the agent?
I didn't understand really the question. What he exactly means. What will be the agent in what?
Abdelbari Ardwan, you hear Mrs. Ikram? If is it the case, you can write your question clearly.
Exactly. Because I didn't really understand like what he means. What will be the agent, like what he will be doing, or will he be, or what exactly he means.
I think Abdelbari Erdwan is hearing you and will write his question.
Okay.
You said movement agent. He will write, you said movement agent. I think it's about that. Yeah, I think for smart grid.
Yeah, we say that we have, for example, here a wind farm. So for our wind farm, there are wind turbine. So with every wind turbine, we will have an agent that can forecast their energy, their state of production, and he can communicate and move between the wind turbines and communicate with the management of all the smart grid. So I think this is his question. So I don't know if he understands me or he needs more.
Yeah, we wait for reaction from Mr. Abdelbari to talk us if he is okay or he wants to explain more his question. And now there is a general question. The person here, I think, ask all the panelists, can you thank you for explanation of the DEFIG wind turbine. I think a lot of persons have spoken about DEFIG. If one of them can explain the DEFIG for our colleague Safa Mskin. We have Sabra Ahyatan. She talked about DEFIG. We have Riyad Al-Wabhi from Algeria. He talked about DEFIG too. Could you, I think Mustafa Shtwani too? No. Mustafa Shtwani, it was about active and reactive power. In wind energy, yeah, it's a little near the DEFIG. In fact, DEFIG is an asynchronous motor who operates as a generator and with a rotor, linked to the grid through two converters, two static converters, one inverter and one rectifier. You know that when an asynchronous motor has a speed greater than the synchronous speed, he can produce an electric energy. But his velocity, his speed, is remains near the synchronous rotation. For an operation about speeds little different to the synchronous one, the control of the side, the grid side converter and the machine side converter allows this operating. You can complete if you have any complementation to add.
I think you're right, Professor El-Bashtiri. Well, I think that a lot of PhD students and colleagues look about double feed induction generator because it's a realistic now solution in wind turbine. We can, for example, for 1 megawatt, we can apply control of 10% for good and robust power electronic. So this is, I think, what you say also, good choice of this kind of generator. But we must, we don't forget that this variant, this generator must have what we mechanical connections with shaft. The turbine shaft is that are moving is very slow slow rotation. So the GR is a little one of the problem of these scenarios. And you know also that the gearing is very expensive, about 15% of the whole systems. So time to time we can think about synchronous generator with advantage and disadvantage. I think that this solution and all the presentation without the presentator of Mrs. Ahiaten was a presentation concern also that the command is must be a little complicated because the system is non-linear. So we linearize the system, so that's why I think there are a lot of discussion about the control with fuzzy, with fuzzy logic, with swarm optimization to eliminate it is possible, it's not but eliminate, to reduce the effect of non-linearity of a lot of elements that compose the wind chain. Thank you.
Thank you, Professor. I think it's a question of sleep. Alors, now in the operation of motors, the sleep is near zero, and when it is a little different, we have to control converters in the rotor. If there is no other question, we will close this session and we will move to the Professor Yusuf Zaz, because the closing ceremony, it will be in 1 minute.
Thank you very much, Professor.
Yeah. Yeah, see Yusuf. Okay.
Thanks Professor Christian
Thank you.
Nishita. Christian
Mhm.
Nishita. Thanks for all participants. In few minutes, in about 15 minutes, we'll do a closing ceremony. Closing ceremony. Just I will invite all participants. We invite all participants and keynote speakers to be with us in a few minutes to give some information about this edition, statistics and evolution, and to have your feedback in order to enhance the quality of your conference IRSEC. In the same time, in meanwhile, you can visit the exhibition another time. I will can share with you the exhibition. The exhibition, you can access to the exhibition from the website of the IRSEC. Okay, I will go. For that, I share my screen. Screen share. I will go to website of IRSEC 20. Access to virtual exhibition from there. You hear me? Excuse me. You hear me? Do you hear me?
Yes, Christian, Nikita, hear you. I hear.
Okay, okay, thank you. In the main screen, we have two buttons, two links, welcome booth and exhibition booth. In the welcome booth, we can find information about IRSEC. We have Discover Us. Discover Us, we find some information about IRSEC and about exhibition. For example, if you chat with our advisor, we can chat with our advisor. Take chat. Hello. Or we can use voice chat if the advisor is available. Can download documents related to IRSEC. For example, the interesting document of list of exhibitors. Can find it there. Exhibitors list. A PDF that contains all exhibitors in IRSEC. We can visit. We can see photos from previous editions. Photo souvenir from previous editions. Videos of this and previous editions, and useful links. Now we go to exhibition hall. As you see, we can't go from exhibition halls to the reception and vice versa. In this exhibition, we have two halls, the hall number 1 and the hall number 2. We can access from hall 1 to hall 2. We can access to, for example, this booth of Ms. Rabat solar team. Discover us. You can see videos of this booth. Gallery, send us or chat with advisor. I don't know if it is available. Hello. If it is available, you can perform video chat or voice chat. We'll go to another booth now from the second hall. GIZ can discover GIZ booth. Discover us. I think there are many videos from.
Bien essentiel pour la santé et le progrès technologique, l'énergie.
The videos as provided by exhibitors. You can download documents, many documents to download, offered by exhibitors. The same thing as you are in the real booth. You can find the advisor. You can find you can talk with an advisor. We can download. You can have documents from the exhibitor. We can see photo gallery and much better, much more. We can have some links, useful links to be used. Social networks and so on. Can see another booth. Now we can, for example, the booth of University of Mohammed VI Polytechnic University. The same thing. Discover us. You find. Can chat with an advisor. I don't know if it is hello. This information, what is your email, is an information to see asked by the advisor to know the person who yes. Hello, my yes. I don't know if it is possible. We'll try. Yes. Are you available to chat? Use voice chat. Voice chat, please, or video chat. Here in my email, I use my Gmail. I'm connected here, yes. Please voice chat. please activate voice chat, please. Voice, please activate video chat. Chat. He's not there. Okay. We'll back to other services, videos, gallery videos of university.
Future African leaders, the university is a
Polytechnic as a professor, and especially on
food security. City envisions an urban environment that advances.
I'm connected in Zoom. Okay. Exhibition hall, University of 5, 5, or Alto Eco, another company. Discover us, gallery, I think videos. They don't put much information, sufficient information in this. But I think this, we visit this one. Sun, clean energy, discover us, videos. Galleries, I think that the first time that we organized in Morocco virtual exhibition in this manner. In few minutes, we will thank you very much for following us in this demonstration. In few minutes, we will start the closing ceremony related to IRSEC 20. Please don't leave. Hello, everybody. We start the closing ceremony related to IRSEC 18. It was a really great occasion that we will meet all of you in this edition, virtual edition, organized from 25 to 28, and 23 and 24 November was dedicated to tutorials and other activities. Our strategic partner, Mazen, under the aegis of Ministry of Energy, Means and Environment, and GIZ, Morocco-German cooperation, and the 3 universities, University of Mohammed V, University of Mohammed VI Polytechnics, and University of Ahmed Sadi, Faculty of Science Tétouan, EMC Cluster, and ENAD Tétouan. In the opening ceremony, was honored by the presence of the talk of the Minister of Energy, Mr. Aziz Rabah, Director of R&D, Mazen, Dr. Hisham Bouskri, the head of GIZ Morocco, Mr. Philip Shatterman, the President of University of Mohammed VI Polytechnic, Mr. Hisham Al-Hatay, the President of University Mohammed V, Professor Mohammed Ghashi, President of University Abdel Sadi, Professor Mustafa Situ, the Dean of Faculty of Science, Professor Abdulatif Mukrim, and both head of chairs of this conference, Professor Mohammed Saidi, and this conference is composed by 3 workshops and 4 sessions, special sessions, and 3 tutorials. The first workshop was proposed and chaired by Mohammed Amin Khalil. I don't know if there is someone from this workshop in this. Amin Khalil, Professor, I don't know if there. You can. If there is someone from this workshop, can raise his hand to identify him. If he is an attendee, we can raise his hand to identify him. Professor Muad also shared the second part of this workshop dedicated to PhD students. I don't know, I think he's with us. Professor Muad, you are available? Professor Muad?
Yes, Professor.
Yes, the floor is yours.
Yes, so I would like to thank you very much for this wonderful days for the conference, online conference for IRSEC. That is the 8th edition. We enjoy online conferences and outstanding professors and the speaker on this hot topic, which is advanced in lithium battery and bion. Especially we learned a lot of things and we had a thoughtful discussion with all speakers and PhD students, researchers, and so on. And hopefully we can continue this workshop in the future and enjoy it on the near future. Thank you very much, and especially I would like to thank very much the organizing committee, and especially Professor Yusuf Zaz and Professor Mohammed Saidi for the organization. And okay, that's all I think. Yeah.
Thank you. The second workshop, which was emerging semiconductors photovoltaic application, was chaired by outstanding Professor Mohammed Khaja Nazardin and highly organized and proposed by Professor Shahzada Ahmed. I don't know if there is someone from this workshop. No, I think. Shahzada Ahmed, yes. Professor Shahzada, the floor is yours.
Hello.
Hello.
Yeah, thank you, Professor Yusuf. It was a real pleasure to organize it, and we were very happy to see the enthusiasm of young people, because a number of questions has been asked, and this is what we want, that young people interact too much, and they learn from our experience. They learn about the new type of research, a new area of research. So we were very happy, because yesterday more than 220, 250 people participants were there, and we were all. I also talked to Naziruddin, Professor Naziruddin. Also, he was very happy that it was a very good interaction, and we like it, and we hope to continue it further in next years.
Thank you very much. Yes. It's okay.
Yeah, it's okay. Thank you.
Thank you very much, Professor Shahzada. Really, it was a very, very high-level workshop, and you had really big effort to bring high-level researchers to animate your workshop. The third workshop, it was proposed and moderated by Dr. Hisham Bouzgri. I think he's not there with us. It's not there. It was very practical workshop with almost all industrials talks, and it was really interesting workshop for the CSP for workers in CSP domain. The fourth workshop, it was energy efficiency in buildings and construction structure. It was proposed by three colleagues, Professor Mohammed Garoum and Professor Najma Arousi and Professor Dr. Zaid Romani. I think Professor Dr. Enrico is there.
Yes.
Professor, yes, the floor is yours.
Yes, it was. I think it was a great success. We have a large number of participants, many discussions, and I would also like to tell all the organizers that I particularly appreciated the format. So these days we are following many virtual conferences since the pandemic, since March, but this one, in my opinion, is one of the best I followed. Also in the format, because the fact of having both recording of some short presentation and instead a discussion, live discussion, and then alternate that. Well, I think it was a very good format.
Thank you very much, Professor Fabrizio. Power to X workshop 5, it was Power to X workshop. It was really interesting with the presence of Professor Mohamed Daoudi, one of the prestigious researchers, Moroccan researchers. I don't know if there is someone from this. Yes. The sixth workshop was digital technology in solar energy. I think there is some researchers from this. As panelists, I see. Let's see. If there is someone from this workshop, please raise your hand. Okay. It was really interesting with Professor Joseph Guerrero, with a very nice presentation. Also the presentation of Professor Saad Michlif is very nice also, and Professor Saad Ahzi he did a very attractive presentation. This work was proposed by Dr. Saad Mutahar, and it's really interesting for the community of solar energy. To the community of solar energy. The first session, the special session, it was about magnetocaloric refrigeration. I think Professor Bali is there. Professor Bali?
Yeah, Professor Zaz.
The floor is yours.
So, okay, so thank you very much, Professor Zaz. At the beginning, I would like to thank the organizer for this very, very nice conference. So the session was really very, very rich and very interesting with a large number of participants. Yeah, so once again, that's all. Thank you very much for the nice work.
Welcome,
okay.
Welcome.
Thank you very much.
Thank you, Professor Mohamed Bali. The second session was biomass and biogas energy in circular economy context. It was honored by two keynote speakers and well chaired by Professor Hassan Al-Bari. I don't know if there is there. No. The third session was wind energy electric production in grid integration. I think Professor Rashid Bishiri and Professor Christian Nashita is still there. Professor Rashid?
Yeah, Professor Zaz, it was a pleasure for me to handle the special session on wind energy, electric production and grid integration in the frame of the IRSEC conference. I would like to thank the organizers, in particular, Professor Zaz, Professor Saidi, and Professor Hibawi. I would to thank keynotes, and finally, congratulations to all participants in this success conference.
Thank you very much, Professor Nishita. Still there? Professor Nishita?
Nikita, you have the mic muted. Your mic is muted, Christian. Votre microphone à l'état off.
Okay. Sorry. Thank you very much. You hear me?
Yes.
Yes, thank you very much, Professor Zaz, for your excellent organization in this crisis of pandemic problems. So I think that it's a great success for your organizing committee, for your colleagues. Thank you, Professor El-Bakhteri, for the kind invitation. And I think is a great success this event, because we see a lot of presentation with the young student, PhD student, and researcher, and we can discuss about the new challenge of electric production and grid integration for wind energy. Thank you very much.
Thank you, Professor. The first session 4, it was photovoltaic in Morocco. It was proposed by Amin Ben Nouna and Professor Amin Ben Nouna and Professor Al-Baghdadi. I don't know if it is there. No, I think Professor Ali Haji is there. Professor Ali? Professor Ali? I will promote it. Okay, you can use your mic, activate your mic. Professor Ali Hajjaji. Professor, Ali Haji, Professor Ali Haji.
Yes.
Yes, the floor is yours.
I would like to thank you for your effort in organizing the conference and for inviting me to that special webinar. I hope the participants had a good time with the three of us and learned something about the interesting sector of PV applications in Morocco. So I hope we'll have a chance to meet again next year, inshallah, without the pandemic of COVID this time. So we'd have a chance to meet in person, nice participants, and would like to thank all the participants from other countries than Morocco.
Thank you.
We will have a chance to meet you all physically in Morocco next year, inshallah.
Thank you very much. Thank you very much. The first tutorial, it was energy storage tutorial, introduction of geochemical energy storage technologies. Professor David. Professor Fuad Gamus, I think, is there. The floor is yours. Professor Fuad, please activate your mic. Fuad? Professor Fuad? He's there, but his mic is... Professor Muad, I think, can give a word about this tutorial. Okay. We go to the next workshop tutorial. It was about predicting materials and device structure by materials, theory tools, computation, and design. It was proposed by Professor Mehdi Selmani. I don't know if he's there. No. The third tutorial is building information modeling. It's it's 6 days tutorial. It will continue Monday, Tuesday, and Thursday, and Wednesday. It was for limited participants. Thank you very much for GIZ for supporting us to cover this this interesting tutorial. Thanks also for all TPC members. Even if there are no review process for this edition, they continue supporting us, they continue promoting IRSEC, calling students, PhD students to participate. It's really interesting, and it's the real team of this conference. We organized also a virtual exhibition. Thanks for our sponsor and for the exhibitors to thinking about this virtual version of exhibition. List of exhibitors. The exhibition is still online. We can visit our booth real exhibition online. We'll keep it for a few days after the conference. Thank you very much for all organizing committees who help us to organize sessions, in proposing workshops, managing sessions, promoting conference in social networks and for mailing lists. The organizing committee chair is Professor Abdelaziz Hibawi is with us. He will give a word about his opinion, and thank you for his floor is yours.
Thank you, dear colleague. As an organizing committee chair, I would like to extend my highest respect and most sincere gratitude to the joint efforts of the all participating keynote speakers, session chair, tutorial trainer, guests, and attendees. I believe that we all have excuse me, there is a problem with my Mac. I would like to extend my highest respect and the most sincere gratitude to the joint efforts of the participating keynotes, speakers, session chairs, tutorial trainers, guests and attendees. I believe that we all have benefit from the quality of the keynote talks. Our most cordial congratulations to this success are addressed to them. I trust that the discussions were fruitful. It is our great honor to spend the past 6 days with colleagues, researchers, and PhD students from different countries. With your participation, the conference successfully finished all its sessions. I hope to see you in the next edition physically, face-to-face. Keep safe, and thank you. The floor is yours, Mr. Zaz.
Thank you very much, Professor Abdelaziz Libawi. Now I will give some statistics about this edition. 59% of participants was from Morocco and 41% from foreign countries. Total number of participants is 1,344. But participants of today is not included because we don't have access to data only after closing the webinar. Countries, we can find that Algeria is the first country, 22% of foreign participants from Algeria, 17% from France, 9% from US, and so on. And you can find list of countries there that they participate in this edition. Total of about 80 countries, but additional countries sure will be added today. We don't have yet statistic about today. Thanks for our partner, this event will help us. Real thanks to Madam Nadia. I don't think is there. You can give a word if you want, Madam Nadia. The support, our technical support. He's not there. Yes.
Mr. Zaz?
Yes, the floor is yours.
Thank you very much. I'm very glad and very happy to have been part of this event, and I really thank you for this opportunity to this event. And many thanks to you all. Thank you.
Thank you very much. I think Professor Saidi is there.
Yes.
Professor Saidi.
Hi. Hi everybody. It's a real pleasure for me to give a few comments on the occasion of this closing ceremony. I would start by addressing my heartiest and most sincere thanks to the some people from the organizing committee. I would start by the general co-chair, Professor Zaz, and the local organizing committee chair, Professor Hibawi, for the wonderful job organizing all the technical sessions, especially in the very hard and very tough situation of this current pandemic. And I think that the number of participants we have in this edition is a big, I would say, witness and a clear witness of the huge success we have achieved all together, all the organizers, the participants, and also the keynote speakers that really have brought a very important added value through the different contributions in the different sessions, workshops, and tutorials that were really key for the success we achieved in this edition. And I think also that the big number of participants that took part in the different sessions is also a clear indicator of the huge success this edition achieved. Beyond the pandemic, including, I think, within the what we call the new normal, the conference or the new other editions or coming editions of the conference will certainly be affected in some way, because we talked today about the importance of involving in some way virtual conferences with some in-person conferences in the new normal. That would certainly bring a very important benefit for the coming editions. The other thing I would mention here is also the partnership we would have with other organizations such as IEEE, because IRSEC was since the very beginning, since the very first edition, was supported and technically sponsored by IEEE. I think that we should raise the conference to a higher level of partnership and cooperation with IEEE, especially with IEEE Power and Energy Society, which is, I think, one of the societies that could be very interested to adopt in some way and to support in the framework of strategic partnership this conference. There are other aspects. Probably the conference in its first edition should develop further, and probably this is one of the ideas we have discussed some time ago with Professor Zaz and some other partners in this conference. We can probably open up the conference to some other fields or applications. More specifically, since the conference is focusing and targeting sustainable development through sustainable energies or renewable energies, but sustainability is also key for other applications, more specifically smart cities, where we have different, I would say, topics covering smart cities in some way. Actually, smart grids and even renewable energies and renewables in general are part of the smart cities. But certainly we can really open up the conference to other, I would say, opportunities within different, I would say, platforms and frameworks to include this dimension, to include this kind of topics. I would not forget also to thank all the participants, which were also key to the success this edition had, and I look forward to a very, I would say, lasting and fruitful cooperation with all the participants, all the partners of the conferences. It's very, very first edition. Once again, thank you so much, and I'm looking forward to meeting you in person for the next edition, inshallah, after this pandemic. Stay healthy and safe, and take care.
Thank you very much, Professor Saidi. I think I give the floor to any panelist who want to give a word. Professor Badevi. Professor Badevi?
Yes.
Yes, the floor is yours.
Thank you, Professor Zaz. I would like to express my thanks to all the organizers of this very relevant and very interesting conference in this field of renewable energy. I hope the next year we'll be able to meet together in very good conditions. I mean, in presence, not remotely, and I hope that most of the conferences and most of the papers presented in this conference could be published and available for the most of the participants and most of the students. And I hope see you next time in good conditions. Thank you.
Thank you, Professor Baghdadi. I give the floor to any panelist who want to give his opinion or a suggestion or recommendation.
Yeah, thank you, Yusuf. So I just am encouraging the participant to publish in the special issues in electrochemical energy storage and from our colleagues. So it's really encouraged to publish in the special issues especially for the IRSEC Conference 20. Thank you very much.
Thank you very much. I forget to mention that there are about 5 journals that will publish papers from this edition. Even if you don't have regular papers, we have videos, and the author of videos are invited to prepare full version of this research to be considered in that special issues. Professor Najma Al-Arousi is there. We can give a word. Najma Al-Arousi. Professor Najma. Okay. If there is someone from attendees want to, you can raise your hand. Hisham Qadrawi. Hisham Qadrawi, can unmute your mic. Okay. Mohammed Musalik. Mohammed Musalik, you can talk. Unmute your mic.
Can you hear me?
Yes.
So first of all, thank you a lot for all your efforts. So as a student of electrical engineering and renewable energy in smart grids at University Mohammed VI Polytechnic, I thank you so much because I had enriched my knowledge about all that like storage systems, and all the renewable energies presentation that some people here had presented. So what I want to say, so thank you a lot, and I hope that I will be in the next conference. So
thank you very much, Mr. Mohammed Musalik. There is anyone who want to give a word? Well, hello.
Do you hear me, my
Yes.
friends?
Yes.
I want to say something. First of all, thank you very much for all the organizers, because it's really a very big success for this big conference, webinar conference. Second thing, I would like to thank all the young people, PhD students, young engineers,
Please
for
present
having
yourself
participating
before.
in this conference. And another remark we have to say it. Look, without physical presence, everything was okay. So next time we will not have this problem of budget when we will ask money for our government or for our university to organize a big conference. We can invite maybe only few people and increase to infinity the number of participants, mainly the young participant. And as I I said, we lost only some coffee and some cookies. Thank you for all of you.
Thank you very much. It's you present yourself.
I am Professor Fouad Lahlou, retired professor from the Moroccan universities, DVD, départ volontaire, but actually I am associate professor with the University of United Nations.
Thank you. Welcome, 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 Professor. There is any other comment or suggestion?
Did you discuss, Professor Zaz? Do you already discussed the city in which we will organize the next edition of?
Yes, we have some proposals. The concrete one was from Marrakesh and Ben Guerir to be between Marrakesh and Ben Guerir, and the other proposal from Tangier. But we have to discuss with the organizers, with partners to fix the city of the next edition. It will be announced soon.
Why not Fez?
Why not? Why not?
Huh?
Why not? I hope that will be Fez. I love in Fez. I think it's a good idea to organize this conference in Fez. We will discuss all partners to fix to select the adequate city to host the next edition. I hope that will be in not virtual but real. Well,
yes, I hope so. I hope so also. But if in the case the organizers decide to organize the next edition in Fez, I will be happy to be involved in the organization committee because I can do some.
Professor Badr, you are already involved in the organization. You are involved in the organizing committee. Are always involved in the organizing committee.
Okay, thank you.
You're welcome. I hope I think it's okay. I close this closing ceremony. Thank you very much. Thank you very much for your engagement, and hope to see you in the next edition in better conditions.
Better conditions.
Bye bye.
Bye bye.